Oh, no, I'm not. What do I do?
Yeah, you are.
Oh.
Hello. Welcome. Yay. All right, we should be live. Welcome to Comic-Con 2023. Yay. We're very excited to have you all here with us. Today we're going to show you the work that we've done in basically the last 2 years. I'm Alex, by the way. I run operations at Comma. And first up, we have Harald, our CTO and head of the Department of Magic. He's going to talk to you guys about our major achievement last year, which was the drive to Taco Bell. Welcome to the stage, Harald.
Hello, good morning. Welcome to Comic-Con. And yeah, so I'm Harald, I'm CTO, and I'll be walking through our drive to Taco Bell last year. We drove to Taco Bell with one of our openpilot cars in mostly end-to-end system. I'm going to be walking through that and just general stuff that research is working on. So, to start off with, I'm going to just recap some, oh, I got a mouse pointer over there. Let me get that one out. To recap basically what I talked about 2 years ago, which is our general architecture for a self-driving system. So our goal at research is to make a superhuman driving agent. So someone that can drive a car better than a human can. And we have a few particular constraints that we're using to do this. First of all, we want to do it completely end-to-end. So by end-to-end, we mean that we want to put in sensor data into a neural network, so like video and potentially other sensors, but predominantly video, and get driving decisions out and have the system drive. The big reason for this is that this gives more flexibility to the machine learning model to learn behaviors and patterns itself without being constrained by, for example, a perception layer or some kind of other hand-coded stuff in between the system. Secondly, it's really important that we build solutions that scale well with compute. A large part of society is working on constantly improving the amount of compute that is available. And when the next generation computers come out and the next generation's GPUs are ready to train models, you want your system to get better as a result of that. And so end-to-end training is one way to get that because there's no hand-coded constraints. But there are some other things we need too, such as a really good loss function and enough diversity in the data. Diversity of the data we have plenty of users, we have much more than we know what to do with. And then also you need a good simple loss function that reflects good driving. So a clear example of the victory of this strategy is recent improvements in LLMs. They have an extremely simple loss function, a generally quite simple architecture, and they have now demonstrated incredible ability over the last few years. 2 years ago when I gave this talk, there were still some serious players doing very classical things in self-driving, but honestly today nobody takes bounding boxes seriously anymore and everyone is moving to end-to-end type systems. So I just want to end this introduction with a quote from Rich Sutton, who has a very relevant blog post from a few years ago where he described this effect. And he talks of the great power of general purpose methods, methods that continue to scale with increased computation even as the available computation becomes very great. And this was before the LLM revolution, and as you can see, he predicted this very accurately. Okay, so that's kind of the basic overview of what we're trying to build. So we can break this system down into three basic parts. First, we have end-to-end lateral control, which is basically just controlling the steering based on the video. End-to-end longitudinal control, which is controlling the gas and the brakes based on the video of the scene. And then the last part is to actually get to the place that you want to go, you need to put in a destination. So humans usually use Google Maps or something like that, and they'll look at the video of that, as well as the road scene to kind of make driving decisions. So that's something we're going to have to do too. And as you can see here, this is how that would work. The model just sees this as well as this, and then it can get you to your destination. Let me open my water bottle here. So, Taco Bell. As a kind of proof of concept of these three parts coming together and showing that with an end-to-end system that has no intermediate perception layers, doesn't have any code related to lane lines or traffic lights, can actually do something like drive from point A to point B, we set ourselves a challenge at the beginning of last year, which is driving from downtown-ish, where our old office was, to a local Taco Bell. It contains just some normal diversity of driving maneuvers, like some right turns and some exits, on-ramps, lane changes, all that stuff. And we said we're going to do that by the end of the year without a disengagement, on our device, on a comma 3, just in a normal production car, which was our EV6, and completely open source. So anyone can see what we did, and by the end of 2022. So we got a very reasonable question. Is that going to be an Elon time or real time? But for those who've been following along, it is real time. By the end of 2022, we have posted, the full drive, all the logs, and all the code. So let's go through how we actually did that. So back to those three parts. Those are the three parts we need to implement, and if they work reasonably well, it will work as a proof of concept, and it will drive us to Taco Bell. So let's start with the end-to-end lateral. This is what the majority of my talk was about last time, talking about the technical challenges involved with doing something end-to-end. What we basically train on is human driving behavior. We train models to predict where humans will drive. We can predict like curvature, yaw rate, or points in space. It's all kind of equivalent. That by itself is not enough to train a system, because you need it to be able to recover from noise and deviations and mistakes. So that's why we had to train it in a simulator, and we have to introduce noise and teach it recoveries. And then for this simulator to actually be able to instill behavior in all kinds of driving and to just scale with compute and data, we need to make sure that this simulator reflects the full diversity of the real world. So we constrain ourselves to using a simulator that's based on real data. And we have a method for doing that, which I explained in 2 years ago, which is by augmenting real data to make it seem like you're moving around. And I tried really hard to get a picture where I didn't look stupid from last talk, but that was actually very difficult. So lateral's done. That was 2 years ago. Back then, it was still kind of in alpha mode. People could choose to opt in or not opt in to end-to-end lateral control. They could revert to the lane line policy if they wish. But today, the only thing we ship is the completely end-to-end policy. There's no logic based on lane lines. It just drives based on human behavior. So that's done. So let's talk about the second part, which is end-to-end longitudinal. So when we designed the lateral system, we always had longitudinal in mind. It was obviously never supposed to be designed specifically for lateral, but we were focusing on the challenges involved specifically with lateral first, but always keeping in mind to expand this to longitudinal later. So most of the architecture worked exactly the same for lateral as longitudinal. Instead of it being yaw rates and curvatures that are relevant to predict, you predict speeds and positions and accelerations, but those together with lateral come into like a complete plan of where to be in 3D space. So we can plug this into the simulator that was successful for lateral, but we immediately start to get some issues, which is our simulator was pretty rudimentary. It used, as you can see here, this is how it would work. We would warp the image basically sideways. Essentially, we were assuming that everything in the scene was on the road plane, and we were warping it to be consistent with that. But that means that everything in the background, all the cars kind of warp sideways. And that actually wasn't that big of a problem for lateral, because the road is what matters most. But for longitudinal, you can see it's a lot more extreme. So we need to do something about these simulator artifacts. The model can't learn intelligent behavior when there is so much artifacts in the simulation. So this brings us to how do we make the simulator better to basically make the background reproject well when we move around, and also other cars. We have a rudimentary SegNet that we use for a variety of things. It predicts a very minimal set of classes, doesn't have any bounding boxes. It just predicts is something part of the road, part of the background, part of your car, or part of other movable things. And you can see that working in this scene right here. So you can quickly start to make some pretty rudimentary assumptions about what these things are and how far away they are, just on what they are. So the road is generally relatively flat and continuously flat and forms some kind of plane. The background often sticks up straight up, and so do most of the cars. So with those assumptions and a very accurate understanding of the road plane, we can actually kind of put in a depth for all these objects based on that. And it won't be super accurate, and especially won't be accurate for things in the background. But the most important things are the things in the immediate background and the cars on the road. And because we have very good road plane estimation, we can actually do this quite well. So you can see this in action here. So this is what it was on what we trained the lateral models on 2 years ago. And then with the new assumptions, you can see some artifacts here, for example. But the models really see a kind of abstract version of this. And so they capture most of the behavior, especially because things on the road are perfectly reproduced, which are, for all kind of driving, the most important. So we plug that all in. We do the same as lateral. We train some models, make them bigger, try some stuff. And that works. You can see here, this is what we posted around the time we started having successful experiments on our EV6, just coming up to traffic lights. It slows down, speeds up appropriately, and it's also surprisingly human in doing this, despite us not having to hand code any kind of smoothness or controls-related things to achieve that. It just knows from human behavior what a reasonable approach to a stoplight looks like when it's either red or orange or green. So again, this is completely end-to-end. There is no traffic light code that achieves this. This is just learn how to do gas and brakes from human driving. So just a little fun side note on that. There is actually traffic light code in our internal code bases, but it runs this traffic light in our meeting room that we can, over the internet, change colors on. But yeah, so that's the only traffic light code in the comma code base. Everything that makes your car stop at traffic lights is learned end-to-end behavior from machine learning models. So that sounded really easy. I just gave you one quick fix to our simulator, and it went from crappy to a little bit less crappy, and all of a sudden we have something that stops at red lights and stop signs. Now, is it really that easy? Well, no, because it took us 2 years, and also no one else has really done this, so it can't be that easy. So I just want to talk about, even though these ideas are extremely simple, and the solutions are also very simple to the problems we're facing, actually implementing this and developing a shippable system ends up having a lot of challenges and several things that cost a huge amount of time. So the first problem is we build an end-to-end system because it's extremely robust. It can learn driving behaviors even if the ground truth is noisy, even if the ground truth is completely wrong. For example, if we were to just take 1% of the driving images and flip them upside down, the models would still learn to drive. If we were to reverse some of the videos, the models would still learn to drive. But the problem comes in when you start to see regressions in some of the edge cases, and it's not entirely obvious. So you need extremely good tests and infrastructure and tools to understand how good your models are and which things affect it, so that you don't have these little subtle regressions that don't cause obvious failures, but overall regress the performance of the system. And over these years, we found hundreds and hundreds of these types of bugs that will completely break some tiny percentages of the ground truth. And every time we improve them, everything gets slightly better. Another thing is all these things rely on extremely accurate road plane estimation. So we need to understand the curvature of the road and the pitch of the road and exactly how high the car is above the road and all those things. Without that, you also start to get pretty serious issues. But I think where we spend most of our time is in the code we delete, the things we refactor to make them simpler, and the bad ideas that we try and then have to reject and completely delete. It's always a continuous fight against complexity. That's what we focus on most on Comma. We want to reduce complexity, keep the solution simple and manageable, because that's how you can have a good chance of finding as many bugs as possible and not being susceptible to this issue where you have this large, robust ML system that we constantly have bugs, give it bugs to, and subtly regress behavior overall. And as a proof that this is a pretty good strategy, we have a really tiny team working on this stuff, and we have a pretty small code base. Yet with that, we've managed to ship end-to-end systems that, as far as I know, no one else has, and especially none that are commercially available. So this is clearly effective. To give you an idea of how tiny the team is, everyone from the research team and infrastructure team, except our newest hire, is giving a presentation today. So that's how small the team really is. So since I spent so little time on what the actual solution was to end-to-end long, because it really was quite simple, I want to give you some ideas on the things that we really did spend time on and that cost a huge amount of time. So first of all, we spent probably over half of last year doing a really big refactor. Now, I'm not going to go into the details of explaining exactly what this refactor means, because the original architecture didn't really make sense to begin with, which is why we had to refactor it. And if I tried to explain it today, I don't think I would understand it myself. But basically, the system that we had shipped to achieve end-to-end lateral planning had many steps. It included student-teacher approaches. It included different types of architecture that worked together. And it had many stages of ground truthing. And it was just difficult to move away from that because it was very effective. It was deployed in the field. And if we wanted to refactor it, we had to make sure that the new, simpler version was just as good. And theoretically, it should have been, but it just took a serious amount of effort and testing and refactoring to get there. But after a little bit over 6 months of work, we managed to do that. We were able to take the training time down from, at the time, around 5 days from beginning to end with all the models we needed to just 2 days. We had 4 models before that needed to be trained, all necessary, that we could reduce to just 2 models. So now it's just a vision model, which takes in scene, compresses it to an intermediate space, and then a policy model that actually makes the driving decisions. And this was somewhere in the middle of last year, or even a little bit before that. And since then, infrastructure improvements and other optimizations have taken this training time down from 2 days to much less than 1 day. And Greg will be talking about that more too. So that's a really big deviation, by the way, from what many other people are training. Training models in 1-2 days is not really that common in machine learning world, but something we feel very strongly about because it allows you to iterate very quickly and correct mistakes very quickly. Whereas if your training run takes 3 weeks, that means, you know, in 1 year you can fix 50 bugs, which is not that great. So that was a positive thing that we spent a lot of time on. There was also some things that we wasted a lot of time on. First one was actually one that seemed like a great idea last Comic-Con, and that we were advertising as something that was going to give good results soon, which is stop lines. So you can do end-to-end longitudinal by just predicting speed and acceleration, or you can kind of find places that the human stopped and then say this is like a place to stop and try to stop for that place. We already had logic for lead cars that tell us how to stop in a place pretty smoothly, so we thought this would be pretty easy to implement. But in reality, even though it's very easy to predict these places to stop with the model, you end up seeing that not all places to stop are built the same. People stop very decisively for a crosswalk, very decisively for a railroad crossing, not so decisively for a stop sign on an empty road, for example. So the end-to-end is a much better approach here, and as soon as we, even within like 2 weeks of trying to replace the stop line logic with end-to-end, we saw it showed way smoother behavior around these things and way more comfortable. So we probably wasted a few months on that. And then the other thing is depth nets. So the solution I showed earlier was basically estimating the depth of the road plane for simulation, making some basic assumptions about the background and other cars, and then reprojecting to simulate. And that sounds extremely simple. That sounds like it's too stupid, and really what you should be doing is have a large machine learning model that predicts accurate depth of everything in the scene, and then you won't have all these weird artifacts that I was showing earlier. So that sounded like a good idea to us, and we spent a few months training models that did this, and they did predict depth relatively well, but they were still quite noisy. They weren't as accurate to understand the road plane. Without the assumption that a road plane is flat and continuous, there was a lot of inaccuracies there, and as I mentioned, that's a really critical part. And also in the things that it should have been way better at, like the background, you start to see these halos around stuff in depth. And then beyond that, you start to even get more issues, which is what's the depth of the light that comes out of a lantern? I mean, there's no real answer to that. The depth of a pixel isn't necessarily a real concept. It makes sense in many cases, but as soon as you start talking about shadows and reflections and all that sort of stuff, it breaks down. And when we were doing stuff with depth nets, we actually were finding a lot of issues related to lighting that were causing problems in the other approach. So we weren't even going to fix those with the depth nets. So after a few months of that, we completely abandoned this approach. So that's end-to-end longitudinal done. As you can see, it was mostly bug fixes, mostly little cleanup. There was hundreds of bugs that we fixed that I didn't talk about, and then some big stuff like these refactors, and then just the slightly improved simulator. And that's what produces the end-to-end longitudinal behavior that we ship today in experimental mode. So that's done. And then the third part, which is we have to actually put the map into the model. The idea here is extremely basic, which is we have some video of navigation feed, just like Google Maps. We show it to the model, and the model can understand which driving actions to make by seeing which the humans made to get to a certain place. Mitchell's got a whole talk about this later, and about the challenges in testing and actually shipping something like that. And as of 2 days ago, we released end-to-end navigation as part of experimental mode. So that's also done. So now we're starting to get pretty close to having something that we think we can try this Taco Bell attempt on. There's a couple more things that we ended up doing. So we've got the model here. That's basically what I've been talking about so far. We have some other controls stages. What we call a planner is essentially a controls layer. And that needed some changes to accommodate high angle rate turns and 90-degree turns. That's in release. That's not in the state that was necessary. Another thing we did is we conditioned the model on aggressiveness of drivers. So the idea was if we classify every driver as either being smooth and conservative or aggressive, we can also tell the model at runtime to drive like a conservative driver or like an aggressive driver. And we did that for the Taco Bell run so that it would drive more like a conservative driver and go slower through the turns and just generally be more comfortable. And then the last thing is we did map-based lane changes. So the lane changes are completely end-to-end. We just say do like a human would, but to trigger the lane changes, we used the Mapbox logic that said in which lane to be and if there's an exit coming up. So that's just 4 commits. That code is still open. You can go look at that code. The logs of the drive are public, and the models are end-to-end as we intended, and there's only a couple other things that we had to change. And so December 15th, we ordered our food from Taco Bell and completed our challenge. So I'm just going to play the video here for a second. I'm going to attempt to speed this up, which is very high risk. Okay, that went pretty well. So as you can see, it starts in the city. There's some just some normal stop-and-go traffic with some traffic lights that it does fine and does the on-ramp here. Then there's a short section on the highway. So you can see that lane change it made there was based on the map-based logic. So OpenStreetMap said you're on the on-ramp, so switch into the lane, and then same here, there's an exit coming up, make some lane changes to the right. Yeah, and then there's just a few minutes on the highway, take the off-ramp. There's some turns here, and I think there's just a final turn coming up, and then we'll see Taco Bell in the view. So just this left turn, and then Taco Bell should be right there somewhere. Oh, there we go. Right, so that was our... Thank you, thank you. So, that was a demo. We make fun of demos a lot because there's a massive difference between shipping something and having a demo of something. And the Taco Bell drive was a demo. Like I said earlier, we wanted a proof of concept of the systems that we intend to ship working together. But that's only the beginning. We then still have to go through the effort of making this stuff actually usable and comfortable and reliable. And that's way more work beyond the demo. So I think we did maybe about a dozen drives, I think, once we had the models that we wanted and all the end parts. There's a whole bunch of reasons why we redid drives. Sometimes we had camera issues. Sometimes openpilot was too slow. Sometimes openpilot didn't take the exit. And actually, I think about 30% of our drives were unusable because there was a whole bunch of trash on the on-ramp that some car dropped. And that was about 4 drives ruined until we waited for the city crew to clean it up. But yeah, so it did it, it can do it, it's end-to-end, but there's still work to be done. So when will it actually be good? So we have experimental mode, people can use end-to-end long. It's about 22% of people that use it today. And it still has flaws, but some people prefer driving with it. So if we look back at the situation of end-to-end lateral control, we can go back 2 years. I found this message in our Slack. Adeeb saying we have 16 point a lot of numbers of people who were using laneless at the time. And currently, we're already higher for end-to-end long. So that's pretty promising. What you can also see in this image is how our metrics changed over 2 years from Slack messages to a real dashboard and something that we can track over time. So some interesting things to point out. End-to-end longitudinal is very relevant at low speeds. And you can see here that the engagement numbers are significantly higher at the lower and mid speeds than without end-to-end longitudinal. But then on the highway, there's still stuff that we're trying to improve. If the model decides to drive too slow, people will generally disengage and drive faster. So that's one of the things that we're working on fixing for end-to-end long. So this engagement minutes is a bit higher than it is for normal driving. Normally, it's about 25 to 27%. And in miles, I think now we're hitting about 55 to 60% of miles are engaged of openpilot users. So that's the majority of our users driving is driven by openpilot. And then that's 2 of the 3 parts. And then the third part is navigation, which is released 2 days ago. So when will it be good? Well, if the past is anything to go by, which it should be, then in the next 2 years, we'll be getting these numbers to 100%, and all cars will be driving to Taco Bell. Thank you. So that's what we've done so far. I'm going to talk a few quick notes about what we're working on next. So we keep talking about end-to-end. We even have hats that say end-to-end. And end-to-end machine learning is really the core of what research stands for. We want the models to do as much as possible, internally, to make everything as simple as possible, and have all the difficulty be dealt with by the gradient descent of the model training. This is an extremely effective strategy, and the last few years have really driven this point home with things like GPT-4. So we still have a simulator that's hand-coded physics. We estimate the depth with some rudimentary assumptions. We reproject. That's not great. We want to have machine learning models that can simulate for us. That's something that Yassine will be talking about later. We still have classical controls. the controls is quite smart and does a lot of learning, which Vivek will be talking about later, but it's not machine learning, so that's something that we can improve. Eventually, we will need reinforcement learning. It's normal for the model to need to do some driving with your car to get used to it. That's how humans drive too, and should improve over time. So that's something we're looking into. And then finally, a little bit more long-term, every time one of our users disengages, they're giving a signal that they would prefer to drive than openpilot. That's something that we want to feed back on, because that means our system did something uncomfortable or undesirable. And so in the future, we want to feed those signals back directly into training and have the models learn to optimize how to make the people happy. So, and then if we zoom out a little bit more, we can think, what's an even more general and more end-to-end approach than just focusing on driving? So driving is a subset of robotics. There's, ADAS systems are some robotic system. You have even a bit more niche. You have like these self-driving race cars. But, there's also just general purpose robotics. And they share a lot of things in common, interacting with the real world, understanding actuators and, friction and physical limits. And that's something that, as self-driving systems improve, will become more and more relevant there too. And this, at first, may seem a bit weird to think like that you can make a more effective system easier with a completely general approach than you can with something hyper-specific. But just to give recent examples again, anyone who's making machine learning models specifically to be a medical doctor or a lawyer is now completely outshined by GPT-4, and nobody that was working on GPT-4 was specifically optimizing for that. They made a general purpose language model, and it beat everything specific. And so it's not unreasonable to think that that's how robotics will play out too. So we want to keep zooming out and thinking, are there general purpose robotics methods that will be very effective in self-driving in the same way as general purpose language models? We're good at domain specific things too. So along that axis, on stage we've got Billy and Silly. They're a little side project that we've just been working on. The Comma 3 is a great development platform. It has good compute for machine learning. It has a screen, microphone, sensors, kind of everything you need in a robot, very similar to a human head. And the only thing that's missing to do robotics experiments is to put some wheels on it. So we do sell those wheels. It's very much a dev kit, but we've been having fun with it over the weekends to just kind of experiment with some kind of robotics types things and see how well the Comma 3 holds up, and if there's anything interesting we can learn from that. So I think it was a couple weeks ago, some of the research engineers went to a hackathon with Billy and Silly, and they won second place doing just some things with LLMs talking and taking a picture of you and printing it. So more on a little bit of fun robotics with Comma 3. We're going to do a hackathon at the office. There's going to be some kind of indoor navigational challenge. Can we use machine learning to navigate indoors? Is that similar to driving outside? That's the kind of stuff we want to explore. We'll probably have some like obstacle course indoors and have people try to get some kind of speed run through that. It's going to be the whole weekend at the end of September. We'll do like 20, 30 people. If you want to come, you should apply, and we'll select 20, 30 people from that, and we'll post more details about that later. It's going to be at our office, which is super cool. We moved into a new office last year. It looks a bit like a compound and has a fountain. So if you're interested in a robotics hackathon, definitely check it out. And that was it from me. So let's move over to questions.
All right, I'll be doing some walk-around Q&A. Does anyone have any questions? All right, we'll start up here.
So I was just curious for the navigate on openpilot. I saw that in the video it was doing fully autonomous lane changes, but as far as I'm aware, like looking in the code and on my own custom branch, I don't see that it's actually it's only using the blind spot sensors on my Toyota 2020 Toyota Corolla, but it's not using the rearward facing camera. So if it's only using the blind spot sensor, but the blind spot sensor is not like 100% like effective.
Right.
So how safe would it be to do those lane changes with just?
So it's still an ADAS system, so you're expected to pay attention any time. So, for example, in a Taco Bell drive, you can see that I'm checking the blind spot monitors for those lane changes.
Yeah.
And I mean, that's kind of what we're imagining. And also, this is true for all of openpilot driving for the foreseeable future.
Okay.
You need to supervise it. So yeah, the expectation is we can make lane changes when we think it's a good idea, but there's still some burden on the user. But that aside, in the future, we are going to use both the interior-facing camera and the blind spot monitors to check this. So it should become more reliable when we move to that. But we haven't shipped that yet.
Oh, okay, gotcha. And just one more small question, like, does that work on every, because in the DBC file, I don't see like lane change or the indicator status. So
yeah, that's going to be car specific, and then the
car.
interior facing camera will be on all cars, obviously.
Any other questions down here?
Hi, 2 questions. Did you go to the retreat after you delivered Taco Bell Drive?
So it's planned for October. But it's real.
It's always planned for October. And the second question, as far as I understand, the end-to-end long doesn't give anything specific attention to speed limits, right?
No, it doesn't.
So like, I'm from Europe, and like, I know that here you can make a pretty good guess in States, like what the speed limit is going to be. In Europe, it's a mess.
Right. So
like,
I mean, that's going to change in the future.
Cool.
Just like European users need to pay attention lane changes to speed limits, openpilot will too, and in the future we'll add that as an input. It's just not the priority right now.
For depth prediction in the simulator, have you considered or tried out using neural radiance fields or anything similar to that before?
So I didn't train the depth nets. Yassine did those. But just generally speaking, we didn't see a future in that approach. The concept of depth just doesn't scale towards the end. And so even if we had perfect depth nets, we didn't see a solution. So we were actually dealing with a lot of issues, which is, so you've got headlights of your car, they illuminate the road in front of you. And when you start augmenting the video, you need to augment those lights too. And a depth net can never help with that. And that's the real reason why we gave up, not because we were confident, obviously you can get better and better models, but not that we can solve this concept of depth to make a good simulator.
Hi. Is the model trained entirely on simulated data, or is there any fraction of real-world camera data too?
So it's trained entirely on simulated data, but the simulated data is all real video that is augmented.
Okay.
There is no actually simulated. There is no like pure simulation data,
I see.
like Unity or something like that.
Anyone else down here? All right.
Yeah, thank you for the presentation. So, you know, I think a lot of the questions around like, hey, this doesn't seem like it's ready for like general public driving prime time, but this is still quite an impressive system. Are there narrower applications that are now much closer to being kind of production ready?
Twice or?
Yeah, with end-to-end self-driving. So say, for example, you can't drive on a public road, but could you drive around a mining site, for example?
Oh, I mean, I guess, but yeah, we're just not really interested in that. We want to make a really good ADAS system and kind of expand on this robotics AI future, I guess.
Can you talk a little bit more about some of the techniques for the end-to-end nav with the map? Like, for instance, keeping it at like a static zoom level versus zooming in as you get close to turns?
There's a whole presentation about that later this morning, and we'll go in a lot of detail. And that's why I glossed over it very quickly. Okay,
I have some more questions, if that's okay. Can you talk about maybe some of the challenges with disengagement analysis for cars that don't have OP long? You know, how do you detect it's a disengagement for just a failure of the stock ACC versus an actual openpilot, you know, long?
I mean, we know whether they're using stock long. So I mean, obviously we know that context when we're looking at the disengagement, right? We know if it's their system or not. So that's not an issue. There's actually some disengagement analysis talk coming also later. I think Weixing will give some insight into that as well.
Okay, one more question related to that. You know, is the training data that you should get more useful from cars that have OP long enabled, or you know, do you still use it for cars that don't have OP long enabled that are using the stock ACC?
So training data, the way we train the models now, not necessarily, but as a kind of feedback for us as the engineers to understand how the system is being used and where it's failing, it's more useful when you have OP long. But again, it's not training the models, it's training us, but I don't know, is that that's kind of the same thing in the end.
Okay. Thank you so much, Harald. All right. How many of you have used openpilot in a car? Raise your hand.
Wow.
All right. Great. Those are the kind of numbers I was looking for. Well, if you've used openpilot, you might be familiar with our next guest speaker, Adeeb. Welcome to the stage, Adeeb.
Nice talking.
Adeeb is the head of openpilot and our newly appointed chief product officer. Congratulations. Just gonna transition.
Yeah, I think we need to switch back. All right, good morning, everybody. Welcome to Comic-Con. Thanks for coming out to San Diego. It's good to see so many of you are users. So like Alex said, oh, it's not full screen. All right, I'm Adeeb. I'm the Chief Product Officer here at Comma. I lead the openpilot team, and I'm going to talk about how we actually ship openpilot. So we have a saying at Comma. We say the difference is shippability. We've been saying this since the beginning. It's a pretty important core tenet of Comma. Everything we do is designed to be shippable. We don't, as Harald showed, we don't really spend time on things that we don't think we can ship. We always develop something to be at least have an intermediary that we can ship first, even if we can't ship the very final system. So Harald showed you a bunch of cool things that the research team develops. They tell the car where to go. But then what do you do after that? You've got these really fancy machine learning models. They tell the car where to drive, how fast to drive, and they can even navigate now. But how does that get to you in openpilot? So first we need some hardware, and this is what comes in your car. It's a lane keep camera. It's got a very tiny amount of compute. So unfortunately we can't run openpilot on it. It's also got no video output, so we don't get a raw camera stream out of it. And it's different in every car. So that means for every car we'd have to not only reverse engineer the messages to read the state from the car and send the actuation. We'd also have to figure out how to interface with it, possibly get a camera stream out of it, and figure out how to run it on that processor. So this one has a Mobileye chip. So instead, since we can't use this, what we do is we ship the Comma 3. We launched this at last Comic-Con, and it has everything you need to run openpilot. It's got 3 cameras. It's got a Snapdragon 845, so every single one has the same processor, whether you have a Toyota Corolla, a Hyundai Sonata, or a Honda Civic. And it's got enough compute to run modern machine learning models, and it interfaces with every single car exactly the same way. And the way we do this is we take PCBs into our office, and Comma 3s come out. So the first step in this process is something called circuit spoke. The original Comma 3s you may have bought towards last year's Comic-Con, or 2 years ago, were made by a manufacturer called Circuit Hub. We replaced them with something called Circuits Book that's in our office. Ever since we moved, we've been running Comet 3s there. They come in with bare PCBs, just like that. And then they run through this line. We have a jet printer, a pick and place, an oven, and some fancy AOI. And then they get headed off to the production room right over there. And then it goes off to assembly. You can see a bunch of Comet 3 boards here. Lots of stuff on them. And then they get provisioned, stress tested, and you order them at shop.com.ai. We fulfill the next day. We fulfill every day. So now we've got some hardware. Next, we need to run on a car. So we know self-driving is entirely a software problem, but now we explain why we need to start with hardware. But fortunately, we don't need to build a car. Modern cars are more than good enough. They've got lane keeping, so we can control the steering by using the same inputs, and the same with the gas and the brakes. So here's the Toyota Prius, a very early supported car for openpilot. So for each car, we need hardware to attach the Comet 3. That's a little bit more specific than the Comet 3. So every pinout on the camera connector that I showed previously is different. So we have a little bit of special hardware for your car, but the compute isn't. And then we need some special software for your car to read and write to it. And we've done this about 250 times for the 250 officially supported cars, and there's many, many more in community-supported forks. So this is the car harness. This is the end that goes into your car. This is the end that goes into the Comet 3. Each car and brand, each brand and model tend to need a different wiring harness. They provide power and access to the CAN bus, and that's how we talk to the car. We have 34 different harnesses that cover our 250 supported cars. So now that we're attached to the car, we need to be able to read and write from it. So each brand, again, has its own messages that need to be reverse engineered after we've already connected to the car. And then we read a bunch of signals like speed, steering angle, whether the car's at standstill, the steering torque that you're putting on the wheel. We read out a whole bunch of things, and then we need to be able to send steering, gas, and brakes to your car. All right, now I'm going to talk about something that's pretty exciting, openpilot safety. So this is something you don't expect, or you might not expect. You have a machine learning model that tells you where to go. We have a planner, we have a control stack. But how do you constrain that output? How do you ship this in a continual way where you don't have to think about these things in this stack? How do we abstract out the safety from this? So we have something called the openpilot safety model, and it guarantees a couple things. So first it says that the driver must always be able to take control of the vehicle by stepping on the brake pedal or the cancel button. So this means you're able to engage openpilot and take control whenever you want. And then we have this next point, which means essentially openpilot can't react or do anything too quickly for an attentive driver to not have enough time to take over. So we enforce this safety, and through that, openpilot is able to pretty much make whatever decisions it wants, and it's constrained by the safety model as long as we do a good job of enforcing that. So there's some pretty good standards around this that allow us to formalize the safety model, give it specific actuation limits, and give us a good way to think about safety. So ISO 15622 gives us some good guidelines for ACC. And then there's another ISO standard, 11270, for lane keep. We recently updated our safety documentation with some of these actuation limits so that they're more formal. You can go in, you can read these documents. They're very readable. They're like 15-page PDFs. This stuff is very accessible. And then you have ISO 262, which is just kind of a general framework for thinking about functional safety for road vehicles. And then we have something called the Panda. So the Panda in your Comet 3 doesn't look quite like this, but this is an external Panda for CAN FD cars. It's a secondary processor that directly talks to the car. So a common thing you might see about openpilot on the internet is that, I don't want a phone driving my car. Well, the phone isn't driving your car. This is the thing that talks to your car. I think it's an important point because this is one of the coolest parts of openpilot. You can have a fork and the Panda protects you. You don't touch the Panda and you should be in good shape. So the Panda has all the code that enforces the safety, and it allows openpilot to be something called QM. So there's this framework for thinking about safety called ASIL, and it stands for Automotive Safety Integrity Level. And then there's something below the ASIL ratings called QM. And this stands for Quality Management. And what that means is anything openpilot wants to do, as long as it's constrained properly by the Panda safety, it's at worst considered bad quality. It essentially has no safety implications in regards to the safety model. So when you're talking about openpilot safety, first you should read the safety model, and then you should go, okay, is the Panda properly enforcing the safety model? And if that's the case, then whenever openpilot makes a decision that you felt was unsafe, you have a proper way to think about whether this was actually unsafe. It provides some very specific language to talk about this, and we're quite strict about how we communicate this because it's really important to think about it in this way. And the Panda goes through lots of testing, and it has very rigorous code standards. We observe MISRA C and all relevant automotive safety guidelines there. And now I want to talk a little bit about testing. So you've got a system, but how do you continually ship it? So we ship openpilot updates to master several times a day, and we ship openpilot updates to our release users roughly every month. And you might be surprised to know that the releases go through very little specific testing. We have really great testing infrastructure that we try to get as early as possible. So that means when we're pushing code directly to master, we expect to find those failures pretty immediately on master. By the time something hits release, it's pretty rare to find a bug. You might have noticed we don't really ship hotfixes anymore. Things are getting quite stable on that front in the 0.9 openpilot series. So back in 2016, there's a fun quote. I found this commit. This was well before my time, towards the start of the company. And it says, one day we'll have CI. So today we do have CI. And the test suite looks a little bit something like this. We don't test in cars. This is the first principle. If you have to go down to a car, first it's slow. All the cars are different. It's not a good loop. So we run regression tests in the cloud with GitHub Actions. We have hardware in the loop tests that run on tons and tons of real common threes. And then we have dozens of common threes running openpilot continuously. But the CI is getting so good that these dozens of common threes really don't find anything. It's getting quite boring. You just see them driving and driving and driving. And it's really pretty incredible the way we can ship things now to openpilot master. And I don't know how many of you run master or try to run the bleeding edge. I suspect many of you do if you showed up here. But I think you haven't seen a regression in quite a while. So I want to talk a little about one of our tests. It's called process replay. And it allows us to deterministically replay all of our driving processes. So that means you have the driving model, for example. We give it the same video, and then we say, OK, what do the outputs look like? Do they look exactly the same for the same inputs? And this essentially outputs a diff in the outputs of the process given two commits. So you can say, I have this good known commit. This is good known behavior. And what is the deviation from that good known behavior? You get a green check mark if there's no difference. And if there are differences, it's really easy to go in and say, OK, this is an expected difference, and or this isn't an expected difference, and I messed something up. And the real power in this is it makes refactors essentially free. You know when you're doing a refactor and you're changing something, you're like, oh, I don't really know if this is the same. You run it a little bit, and you're like, OK, this looks roughly the same. With process replay, your coverage is only constrained by the inputs. If you want more coverage, you throw more data at it. You can generate data that'll be relevant for what you're doing, but we just throw in lots of segments from lots of different cars, and we get great coverage that runs on every single openpilot commit and gives you a diff from the last known good openpilot commit. So this allows, I think, research right before the release merged a fairly large refactored RAID-RD. They were able to run it through process replay and a larger version of process replay that they maintain. And it was, I mean, nobody was concerned about this before the release. It was just business as usual. All right, so this is kind of the most important thing in testing. Green check mark means good to go. If you don't trust your CI, then there's almost no point. So every time you commit, you should be very confident when you get that green check mark that you're ready to merge this, and nothing unexpected will happen, essentially. Sometimes there's good red X's. We have some cool tests like a power draw test that asserts that essentially every driving process doesn't use more or less power than expected. So we've had some fun ones like that where we've done some optimization, you get a red check mark, and it's like, okay, I lowered power usage. And then we can adjust the thresholds, and we can say, this will not regress in the future because we test this explicitly on every single commit. And it's similar with CPU usage, memory usage, all those kinds of things. All right, so this robust testing infrastructure enables us to ship openpilot updates extremely regularly. There's essentially no bottleneck on shipping to master. You have a green check mark, then you feel very confident. Sometimes you might ask somebody for a review, but really the machines are doing your reviews for you. They're enforcing essentially all the behavior we want to enforce. And this allows us to support all the 400 plus contributors we have now. It's nearly double since last Comic-Con. And it's pretty incredible. We hit 10,000 commits. Of those 10,000 commits, I think about 30% of them are from external contributors who, you can't expect an external contributor to do too much validation. It works on their device, works on their car, improves their experience. But it's always hard to expect them to do the validation when they're not the ones clicking the merge button. So we've really removed that burden on ourselves in the same way that they go through the same workflow that we do to validate our changes. And I think a really cool feature of this is we have 250 supported cars. This has grown, again, double since last Comic-Con. I think it was 134 last Comic-Con. And is a single engineer maintaining all those cars. We're expanding car support. We support all major brands now. We recently merged support for Ford. And it allows the community to really, the community is really able to leverage our CI, and we just, we're able to validate their stuff so quickly that we can have one person who just builds tests and infrastructure for them, and then we merge their car ports. And it's a really great pipeline now. All right, so now I want to talk a little bit about what's next for openpilot. Now that you have an idea kind of how we ship openpilot. We ship little boxes to you guys. I showed you a little bit about the procedure for that. And then, there's some unexpected hiccups. You need to do some safety. You need to do some testing so that you can ensure that you're continuously shippable. But what are we shipping next? So this is something from the Taco video. We had to bump up the low-speed torque. The way we implement the safety for our torque-based cars right now is it trades off some implementation simplicity for maximizing torque at all speeds. Because essentially for a given, you can only maximize your lateral acceleration for a given torque at a narrow speed range. So that means at the low end, you're not getting as much torque. So in the future, what we'll do is we'll be able to look at the speed, and the panel will say, OK, you can get a little bit more torque at the low end, and then we'll be able to give you a consistent amount of lateral acceleration across the whole speed range, rather than at one narrow point where we maximize on the highway. And then this is another interesting one coming up. A lot of cars are coming out as vision only. They don't have radars. So we've got to start doing comma AEB. This is a milestone that we need to hit for openpilot 1.0. This is a video from when we did our first AEB tests, when we were doing some more of our some safety work on. We wanted to validate that essentially we passed through the AEB messages and that it still works. So this is the first time we did that. We built this car. This is how we do it. And some systems are a lot better than others. You should go and read the blog post. I pulled this picture from there. It's really great. We analyzed the manufacturer AEB systems, and we We compare them, we benchmark them, and we can compare them even to openpilot's forward collision warning, which is really pretty good and really suitable enough to ship an AEB. But then again, there's a lot of safety work that's needed to ship AEB. You don't want to just trigger at any time. It also extends the safety model. We're going to trigger when you're not engaged. So there's quite a bit of safety work that goes into this. All right, and then we want to ship to more robots. Harald talked a little bit about this. This is going to require some brief factors to support cleanly. The comma body fit in pretty cleanly as a car, but we want to support more robots. You might have noticed the self-drive to system refactor in openpilot. We're going to keep working on that, and it should be really easy to integrate in any of your robotics projects. And then we're trying to make everything more plug and play. You might have had to fingerprint your car. I see there's a lot of users here. Hopefully you didn't have to, but this is a metric we're starting to track now. We refer to it as TTFF. That's a GPS acronym that stands for time to first fix. The openpilot team is kind of commandeered it to mean time to first fingerprint. So what this shows is how many users every day didn't hit a successful fingerprint who should have. Essentially, they bought a comma 3, they saw their Toyota Corolla was supported, they put it in their car, and it said car and recognized. So this is something we're fixing. It turns out we were very conservative in the beginning. We pinned to exact, like these firmware strings we get from the car. And it turns out, they don't change their APIs that often. We can look at these firmware versions a little bit more, and we can essentially, if we say we support the Toyota Corolla, you plug in a comma 3, it'll just work. So we shipped the first version of that for Hyundais in 093. Toyotas are coming up next, and we'll extend it to all the cars. All right, and now I want to shout out our external contributors. We have 474 as of this morning. So if we can get a developers for our external contributors in 3, 2, 1. Developers. All right, time for questions. So you can ask me questions about openpilot, the product, the production process, really anything like that. No. So we actually run these on the CPU in GitHub Actions. Yeah. Yes. So there's actually some brands where the EPS does this for you. So like the Chevy Bolt is like this. Yeah. You want to repeat that?
Yeah. So the question is, what's the best car brand or even model, specific model that has like the highest low-speed torque limit?
So there's some cars that are, all these APIs are different amongst the cars. The Chevy Bolt happens to be one that already has good low-speed torque because they already compensate for this when you request the torque. So that's one you can get right now that'll have really great low-speed torque.
All right, I'm back here.
Well, you have a Chevy Bolt.
Yeah.
Thanks so much for your presentation. I always love anything on CI. So in your replays, I guess you're kind of trying to see if the car or the new release does the proper behavior again. You don't have a regression. Mm-hmm. Do you have any, and I'm asking this because I'm kind of interested in this project called Vision Zero.
Okay.
Right. Do you have any testing techniques or know of any testing techniques for, say, reproducing adverse events like collisions? Like, can you kind of test for, hey, does a certain type of behavior in a car actually cause a collision?
So these tests are a little bit different. They're lower level than that. So what we test for is we take each individual process, and processes really only do, they have very narrow scopes. So we'll say, like, is the car parsing? We take in CAN messages, and we say, did we parse the same car state out from this? So it's much lower level. You probably want to ask the research team this question. They have really great tests for this stuff.
Thanks so much for that feedback. It's super useful.
Yeah, can you talk a little bit about your segments you use for testing and validation? You mentioned, are you kind of continually changing those out over time as you get fresher data off of more recent openpilot versions? Or is it kind of just one big list of segments that you're continuously building on over time?
So the big list we build on over time is the ones for cars. We have several test segments for each car we support. And we have like this 200-line unit test. It's really great. And it basically ensures the cars never break. This turned out to be a problem up until maybe a year or two ago, where there'd be some minor regression in all these cars, especially since we don't have one from each platform. So that one we continue to build on over time. For other tests, you generally get a pretty good coverage from. So we have to update them occasionally when there's new outputs and new inputs, but largely no, we don't have to. The next step for this is like fuzzy testing, and you want to really search over that whole space and make sure you get full coverage and generate the data.
Hi, I have a question. Which car brands are the easiest to support and the hardest to support? And do you have any thoughts on their software engineering practices and quality?
So easiest to support, this is really changing now, actually. The software platforms in the cars, at least for the ADAS, were pretty stable for about like 3-4 years. And we did a lot of this initial work maybe 3-4 years ago. And now we're in this cycle where Honda, Toyota, Hyundai, a lot of them are changing their platforms right at the same time. So that's the hard part right now, is we're getting kind of this influx that are all different right now. The hardest ones now are the ones that implement the AUTOSAR secure onboard communication. We haven't spent much time on it, but that'll be a little bit of a project. It just adds more overhead to porting a car. And I think you had a second question?
Software engineering practices.
Oh, I mean, we reverse everything. So sometimes we see some fun stuff, but largely it's, it's the practices of the tier 1. The worst part is sometimes the APIs just don't make any sense at all, and we have to hack around that.
Hi, I have a question on the community collaboration. So what's the expectation as far as for proper communication and also the quality of the PRs that we do? Like what's that like? And we have a lot of PRs that's being opened with openpilot repo, but always getting a lot of time, like the time to get them merged or get them even review, it's a long time. So what's the expectation that the external developers or collaborators should be expecting?
So as far as communication, we tend to merge the things that are pretty immediately mergeable pretty quickly, and then we have to prioritize essentially what is valuable to us right now. There's a lot of the ones that are open are maybe there's like a lot of refactors that are like of questionable value that maybe we should just close, and perhaps we should have some kind of auto close mechanism. That's we can certainly improve this, but for things that are like pretty immediately valuable, we'll try to provide good feedback immediately and try to get them merged. But it essentially goes through the same prioritization as the stuff we work on. It's really quite a small team that's looking at this stuff.
Hi, so for all the testings are being done on openpilot, what's the process like of developing a test case?
Developing a test case. Okay, so usually the way this works is you write something, and then you say, okay, I'm not sure if this is going to work quite the way I expect, then you write the test case. So generally, we have a lot of the kind of general test cases that are end-to-end written already, and then now it's more of specific unit test cases that get written. I mean, you can look at I was looking at the openpilot commit history this morning, actually, to get a nice picture for something, and it's like mostly tests. So that's what you see these days. Things that like regress a little bit, and we write a test for, and we say, okay, this is never regressing again.
Hey, just wondering if you could share any insights into your AEB deep dive. Which brands did well, which brands did not?
So Honda Bosch, I believe, was the worst performing. That was actually fun. When we were testing it, we had to put a license plate on it. I think we had to put a German license plate to get it to trigger. Yeah. So the funny thing is they released a testing procedure, so you can kind of engineer it. It's kind of like the fuel emission stuff where sometimes they engineer a sort of demo essentially for when they do the test. But again, we'd have to like fully reverse the systems to understand how it works. It might have actually been looking for something that was real. But it's probably time to redo that test. We support a lot more cars now, and we can redo that blog post.
I had a question on steer torque. Do you only use torque for rate limiting, or do you use steer angle ever?
So it depends on the car. We essentially want to limit the two things we want to limit are lateral acceleration and jerk. These are actually specified in ISO 11270. So we have to limit essentially what the car gives us. We develop a safety model, or an implementation of the safety model for each car as it comes. We recently supported the Fords, and those, they don't take torque. We give it curvature. We have to develop something around that. Fortunately, for a lot of the EPSs, don't provide enough torque that exceed the ISO 11270 limits. Some do, but we implement the safety nonetheless for all of them.
You spoke a lot about cloud testing with CI, but you sometimes do hardware in the loop tests. So can you elaborate more on how and when you do those and any best practices you adhere to? Yeah.
So best practice here is we do them on every single commit. If the test is something you have to run manually, it's just not going to get done sometimes. You're less likely to also make the change that you want to make. The best feeling about CI is like, when you're at home, you want to make a change, and you're like, openpilot's public. It's really easy to like go in the GitHub editor. It's like, oh, let me make this quick change. And it's like, do I commit to master the small change? You open a PR, and you see the green check, and you just merge it. It's like, I don't feel like it's gonna. You feel really good that it's not gonna break master. And I do this pretty often, where I go home at night, I'm like, oh, I want to make this quick change. I end up merging it that night, go to sleep, and I'm not worried it's going to break master. Because we do have like 400 users who run the very, very bleeding edge. So if it does break master, they'll let us know pretty quickly.
Hi. It sounds like you do a CI on pretty much every commit.
Yep.
Does that also go for hardware in the loop testing, or is that less frequent, rather?
Nope.
Okay.
On every single commit.
And in that case, how long do you run those hardware in the loop tests? Because I've seen openpilot bugs that don't manifest until the comma's been running for a few days.
Like what kind of bugs?
Like low IPC rate errors, failure to engage after being on. Doesn't turn off when the battery gets low, things like that.
Do you run a fork?
No, just regular release channel.
Oh, okay. We should talk about that after maybe. But so we have some different infrastructure for that. We call it the testing closet because it actually started in a closet in our maybe 2 offices ago when we were in a house. And it's essentially just dozens of Comma 3s running continuously. And the hardware and the loop tests are like normal unit tests that need to run on the real hardware. To validate some things that we can't reproduce on like cloud CI runners, like using the DSP and the 845.
So I had a question. What motivated the desire to actually assemble the PCBs and boards in-house? Like what problems did you guys run into from these like contract manufacturers? We
use this company called Circuit Hub, and we got boards.
Throw them under the bus.
What's up?
They were good for the Comma 2. They weren't good for the Comma 3.
Yeah.
Things got too complicated.
And now that we have this, it's really incredible for prototyping. We can like essentially have CI order boards every Friday, and it makes so much sense. It's like $200 for a bunch of boards. We just run them through the line. It's really fast and easy. Doing revs of the Comma 3 took forever. So it's really a superpower in that regard too. But we've been doing some really great tuning over the last couple of weeks on the line. And finding like the really littlest things. We catch it in production, we stop the line immediately, we go and fix the thing, and we're able to do the same things we do in production, but on the boards themselves.
Yeah, we can tweak every little detail.
Yes.
Faster reference time, better fall.
I just have a question on capacity. Have we ever have capacity issues ever? And when multiple users using the software or whatever, or something like that, does that ever cause peak and have to distribute it?
I'm sorry, what kind of issues?
My question is related to capacity. So.
Oh, capacity issues.
Yes, I will run out of capacity issues, and then how we distribute multiple users using the same time, like does that the peak, the peak values for that?
Multiple users using at the same time?
Yes.
Well, everything runs on your device, so there's no issues like that. You don't need to connect to the cloud except for navigate on openpilot, but that just hits like a tile server and a routing server. So the load is pretty low there.
Do you have any kind of special process to integrate tests for driving feedback you get from users for like consistent disengagement spots across openpilot versions? Like for instance, there's an express lane that I drive on, and it's consistently tried to take the exit across, OP 090, 91, 92. It did good on the way to the airport a few days ago on 94, but I had a lead car in front of me, so I think that definitely played into it.
Okay.
Yeah, curious about that.
Driving behavior questions are generally best asked for the research team. Weixing is going to have some really great stuff on this, on like disengagement analysis. We have a driving feedback channel in Discord where there's like a nice forum. You give it a route as long as you upload all your logs. So if you ever want something looked into by us, we love looking at the bug reports, but they have to be, you have to put in the effort to make it really high quality. I mean, just put in the effort and it'll be high quality. So don't worry too much about don't worry whether it is high quality.
So just continue to make the reports, because I've reported them all. I try to do the feedback, but just was curious if you had a specific process to prioritize those, or kind of make sure that there's no regressions.
So we do look at everything in that channel. We look at everything that's reported essentially, and if it's something that looks a little bit concerning or that looks like a regression, we'll evaluate whether it actually is or it regressed in some very minor cases, and we prioritize that way. We do look at everything that comes in. So
thank you.
It's not always easy to respond to, though.
Yeah, generally, I would just like to thank everyone who's made a good bug report. I think people don't realize how valuable. Yes, give it up for bug reporters.
Yeah, that slide really should have been bug reports, bug reports, bug reports.
Truly, I think people may not really fully realize how valuable the reports can be to the team. We're the team's so small, and we have about 12 cars ourselves. I feel like we don't talk too much about our cars, but so we're testing things, but I think people don't realize how many varieties of cars, how different each car is, and so it's super helpful to the team to have that information when they're doing bug reports. We have time for a few more questions down here. Great, I will come back over.
So I'm just going to reword a question I think I heard, because I think it was a really important one.
Okay.
So you have a closet or room of hardware that runs hardware in the loop tests. You might also have some infrastructure that can run tests, like unit tests.
Yeah.
When are times when that hardware or infrastructure sort of maxes out because you have too many requests to run tests? Or do you not observe that happening?
Since we're an open source project, GitHub gives us GitHub Actions runners for free. We actually upgraded our GitHub plan so we get more concurrent runners, and it was I don't know, a few $100s more a month. And we just get unlimited CI from GitHub every month because we're an open source product. So that's really cool. And then as far as the hardware tests, we have to scale those sometimes. And we just add more devices in the closet. That's a little bit hard to maintain because the team is so small, but we were generally able to keep up with that.
You guys, the testing closet is like a nightclub. It's very loud.
It's very important. Yeah, I keep it right next to my desk.
I don't know how Adeeb works around all the alerts.
Oh yeah, I just have a question about safety, which is related to total model failures. So I had a situation one day. It might sound just unbelievable, but a bird took a dump and it hit on right where the camera is looking, and it covered a lot of the camera, and then the car, the model didn't give any warnings, but it was a model failure, and the car just went straight, and I had to immediately disengage and turn on my windshield wiper.
Yeah.
And also others sometimes the model incorrectly predicts where the curb is and it rides on the curb and stuff like that, but when it does that, there's no indication that there is a model failure happening, and there's no loud beeps or anything. Like, have you guys considered maybe like putting in like a warning system for like?
Yes. So two things there. You use the word safety. We have to be very careful about how we talk about safety. So I talked a little bit about this. We have a safety model, and to recap that, it guarantees that if you press, you're always able to retake control by pressing on the brake or the cancel button, and it'll never do anything too quickly for an attentive driver to take over. So if that fails, that's perhaps a safety failure. But anything that the model does or openpilot does is essentially considered QM. So your events are considered bad quality. So it's just important to make the distinction there. And then as far as those things, we had this alert that kind of detected device falling, model uncertain. We just found there was too many false positives. You would be pretty annoyed if you got one when it was very clear you shouldn't have gotten one. So we can revisit this. This was maybe a year ago that we removed it. But I mean, I hope the bird one was pretty obvious for an attentive driver.
I do have a question on safety. So earlier you mentioned that we're going to increase or maximize the low-speed torque.
Yeah.
So there are some collaborators in the community, let's say for Subaru or for Hyundai, HKG, that they want to get involved in this the implementation of the low-speed torque.
Mm-hmm.
Now, we talked about that we have to do injection testing, and we're getting more data and more documentations on how the testings were done. So is there anything that, moving forward from the openpilot team that can provide some of that documentation publicly on how the community can get involved with that, so we can kind of speed up the process, or anything like that?
So the thing that's a little bit hard for the community to do is to get from 0 to 1 on this. So I would suggest that the community, waits until we do it for the first car, which will probably be our EV6, because that's what we did for the Taco car. There's the first implementation of it in the Taco branch for that car. And then the community is really good at taking from when we go to 0 to 1 and saying, okay, let's ship this on all 250 of our cars. So I think that's the appropriate time for the community to get involved. But the safety stuff is pretty accessible. If somebody wants to just get ahead of this, read ISO 15622 and ISO 11270. They're very readable. They even provide testing procedures. So yeah, that's what I say about that.
We've got a question upstairs.
Hey, thanks. Nice presentation.
Thanks.
I was curious if you guys also track the code coverage.
Yes.
While you do? Okay, cool. What tool do you use?
So we track it with CodeCov. That's at 70% right now, but it doesn't really cover everything. I mean, that 70% doesn't cover everything, so it's really quite a bit higher. But we really better code coverage than just like line count. That's probably a project that we should do soon. Because it's not completely obvious. It's something that like a few of us have in our heads, but it's not completely obvious to an external contributor, like, I'm making a change. Is this covered by the tests? Generally, the answer is yes, especially for the things that the community tends to want to change. But it's something we should drive up, and we should really communicate when you're making a change, whether it's covered by the test and how well it is. I think that's what you really want with code coverage.
Yeah. Cool. Well, thanks.
We've got one last question here.
Hey, general question. What does your system look like for learning from real-world edge cases?
So that's another question for the research team.
Okay.
All right. Thank you so much, Adeeb. All right, so last time you guys told me how many people are using openpilot. This time I want to know how many people have used Navigate on openpilot. All right, this is a number we got to drive up, new metric to drive up. No, the team is working hard on Navigate on openpilot. I can't express how much I love using it. And Mitchell, kind of the architect of Navigate on openpilot, is here to show you about the progress we've made since we announced this project 2 years ago. Please welcome Mitchell.
All right. Hey, everyone. My name is Mitchell. I'm a machine learning engineer at Comma, and I'm going to talk a bit today about all the work we've done to ship Navigate on openpilot. So this is a project we've been working on for a while. I think I started on this late last year, and then we showed off an initial version of Navigate in our Driving to Taco Bell video at the end of last year. The idea is, well, the driving model already takes the videos from the 2 cameras on the Comma 3 as inputs. So we're just going to add a 3rd input. That's a video of Google Maps. And this should just work, right? So the great thing about training our model end-to-end is we should just be able to pass the map in as an input. And since the model is trying to predict where a human would drive, and the map has a lot of useful information about where the human is going to drive, the model should just figure this out. It should learn to use the map, figure out where you're going to go, when to take exits, when to make turns, and generally do whatever maneuvers are necessary to follow the route and get you to your destination. So this is what we built, and it works pretty well. So I'm going to talk a bit today about how all of this works, all the little details that make it work better, and all of the work we've done to validate this feature and get it ready to ship for openpilot 094. So I'll start with how it works. The first thing we're going to need if we want to build this is a good map. So fortunately, there's a lot of really good open source tooling we can take advantage of here. OpenStreetMaps, Overpass to serve up sections of the OSM graph, Valhalla for routing, Mapbox.gl to render the maps. All of these tools have been really useful in building this. So we need maps. We train our driving models on a large data set of 60-second video clips. So we're going to need maps for all of those video clips. And again, the good news is openpilot already has navigation. The Comma 3 launched with built-in nav using the Mapbox.gl native library. And so we can just use this same library in our data center, and we can render as many maps as we want. Mapbox.gl is pretty nice. You give it a latitude, longitude coordinate, you give it a route, and it will render a map for you. So you can see this at work here in openpilot, and we're going to reuse this same system. These are the maps we're going to draw. They're intentionally styled to be very bare bones. We just draw the road in white, the route to follow in gray, and we just draw these as 256 by 256 pixel images, 2 pixels per meter, so this is half a kilometer on each side. And these maps are nice and simple and easy to reason about. So we want to render a lot of these maps. And like I said, we need 2 things. We need the latitude, longitude for each map, and we need a route. So the latitude, longitude is easy enough. The Comma 3 has a built-in GPS, so we can just get the GPS coordinates from that. The route is a little bit trickier. So you can see here a visualization of a little chunk of the OpenStreetMaps graph. The junctions are marked in blue, and we have some GPS measurements from a Comma 3 marked in green with the X's. And you can see here that the GPS measurements don't line up exactly with the road. So they can be shifted a little bit, they can be noisy. For lots of reasons, the GPS measurements may not line up exactly with the OpenStreetMaps graph. So we need to fix this to get a route. What we want to do is take a list of all of the GPS measurements from one of these video clips, and we want to figure out which roads were actually driven on in that video clip. We want to match these GPS points up with your clip to the OSM graph, and then we want to snap those GPS points to the right roads. So fortunately, we do not have to do this ourselves. This is somewhat complicated to implement, but there's lots of services that'll do it. Mapbox has an API for it, but there's also an open source routing engine called Valhalla that does exactly this. This is called map matching. So you give it a list of these GPS points, and it turns it into a proper route marked in red, snapping all of the points to the graph and giving you the exact route that you drove. So this is exactly what we want. We've got our lat long coordinates, we've got our route, and now we can draw our maps. So now that we have our maps, we just need to feed them into the driving model somehow. The problem is, on their own, the raw maps are 256 by 256 pixels, so that's like 65,000 numbers. That's way too big. So we can't feed these directly into the model. We're going to have to squish them down somehow to make them a little bit easier to work with. So how are we going to do this? Well, we already do this for the camera images. Those have the exact same problem. So we have a neural network running on the Comma 3 that takes in a frame from the cameras and compresses it down into a vector of numbers. This is called a feature vector. And this vector should represent all of the details of the scene that are relevant for driving. So this is about 2,000 numbers for every frame of the video, and these get passed into the driving model. So we want to do something similar for the map model. We want to train some kind of neural network that's going to take in the map. It's going to compress it down into a vector that has all the information the driving model needs, and then we'll pass that to the driving model. So the way we're going to train this map model is as what's called an autoencoder. So what this means is that the neural network is going to have two parts, an encoder and a decoder. So we're going to feed these maps that we render into the encoder, and the encoder is going to squish these maps down into this little feature vector of a couple hundred numbers. And then the decoder is going to take those numbers and try to get back to the original image. It's going to decompress it and try to get as close as possible to what we originally put in. And if we train this all correctly, this feature vector should be a complete representation of the full image. It should have all of the details of the map that the driving model needs to know about. So we train this thing, and then we can just throw away the decoder. We don't need that. We just need the encoder. The encoder gives us some features, and we just feed those features into the driving model. So now we've got our nice squished down format. We can generate these map features. And you can kind of see here what the autoencoder is doing. So on the left, we can see the original maps that we render with Mapbox.gl. And then on the right, you can see these maps after being squished and then decompressed by the neural network. You can see a little bit of detail is lost. It's not a perfect reconstruction, but it does a pretty good job at capturing all the high-level details and all of the information about the map that's necessary for the driving model to figure out where to go. So now we've got our maps, we've got our map features, and all that's left to do is hook this thing up to our simulator that Harald talked about, train a model with it, and cross our fingers that we did everything right and this will just work. So we do this, and it works pretty well. So you can see here, these are some videos from our simulator. The model's predicted path is in orange, and the real path driven by the human is in blue. So you can see as the model gets close to the exits, its prediction moves over, the model switches its trajectory to take the exit and follow the route just like it's supposed to. So this is great. We can do the same thing for turns. You see here, the model does a pretty good job. As it gets close to the turn, it adjusts its prediction so that it's going to try to follow the route. So this is fantastic. We have a driving model that's going to try to follow the route that we give it from the map. And now we just have to run this on the comma 3. So fortunately, this part isn't too complicated. We're going to add a few new processes to openpilot that'll let us do all of this stuff. So we'll add a process called mapsd and a process called navmodeld. Mapsd is going to render our maps for us using Mapbox GL native. And navmodeld is going to take those maps, run them through our encoder, and get our map features out. And then we just need to make a little change to modeld, which runs the main driving model. We'll just make a change so it takes in those map features from navmodeld, it passes them into the driving model as a new input, and then everything else works just like before. So we do all of this, we put it on a branch, and it works. You can see openpilot is taking an exit here, following the route on the right, and if we've done everything right, this all just works. It works pretty well. So to give you a sense of perspective, this is roughly where things stood for the Taco Bell video at the end of last year. So we've been working a lot since then to get this ready to ship. It always seems to take longer to actually get things deployed and test all of the edge cases than it did to build it in the first place. So I'll talk a little now about exactly what it took to ship, and specifically some of the details that you have to get right to make this all work better, and some details that uncovered some bugs. So one obvious problem that you run into right away when you're building this stuff is that if you look at Google Maps or Bing Maps or any of these online maps and you just pan up and down, you'll see that the scale at the bottom right of the map is changing. It changes from 500 miles in the middle of the US all the way down to 200 miles for the same length at the northern end of Canada. And the reason this happens is because the Earth is a sphere and maps are rectangular. And so you have to take a spherical globe and somehow project it onto a rectangular map. And you can't do that perfectly. You have to make some compromises. So the way that most maps these days do this is with something called a Mercator projection. So the Mercator projection keeps these nice straight latitude and longitude lines, but the problem with this is that the areas near the North and South Pole get way blown up. So you can see this happening here. And for humans, this isn't really that big of a problem. But for a driving model, this is a little bit inconvenient because this model is going to use the map to predict in 3D space where it's going to drive. So without any extra information, the model doesn't know if it's making a turn in 200 meters or 500 meters because the scale of the map could be totally different. So we need to take care of this. It's not too difficult. We can just dynamically adjust the zoom level of the map to get a constant scale. So like I said before, we're going to render our maps at a scale of half a kilometer on each side, and we'll change the zoom level as necessary to make that happen. Another problem we run into is that, well, we did all of this work to make sure that our routes were accurate to the road that were actually driven in each video clip, but we actually did too good a job. And so the problem is that sometimes when you're driving with your Comma 3, you maybe miss a turn, maybe you miss an exit, or sometimes you just don't want to follow the nav instructions. Maybe you think Mapbox is telling you to do the wrong thing, and so you just do something else. And the problem here is that with the way we've trained this model so far, it's basically never seen a wrong turn before. So the model is going to get super confused if you miss an exit. It might try to take an uncommitted lane change, or it might try to brake in the middle of the highway. All of these things are really bad. So we can't have this. We've got to fix it. So there's a couple different things that you can try, that we've tried. But what seems to work pretty well is we can generate these artificial routes that essentially have wrong turns in them. We can take the OpenStreetMaps graph. We already know exactly what route was driven in red. And so we can just pick one of the junctions in the video, go off in a different direction, and then do a random walk of the graph from there to generate these artificial routes. And we can train on a small percentage of these to make the model more robust. So there is a bit of a trade-off here. This is a delicate balancing act, because if you train on too many of these, the model will learn that sometimes it shouldn't follow the route, and so it won't be as diligent about doing the right thing and trying to follow the route when it can. But if you don't train on enough, the model won't be robust, and it can have bad behavior. So you have to balance these two things out. And we've found that training on roughly 5 to 10% fake routes maintains a good compromise between making the model robust while also not harming its performance at taking exits and turns. So now we have our model, we've fixed some bugs, and the last thing we have to do to get it ready to ship is write a ton of tests. We want to validate this behavior in all of the cases we can think of, in a bunch of edge cases, and we want to know exactly what these models are going to do when we deploy them. So, like Adeeb was saying, we have a saying at Comma that goes, "No testing in cars." And the reason for this is, especially for research, even though what we ultimately care about is that the model drives the car well, we don't want to test our models by putting them on an openpilot branch and seeing what happens. This is way too slow. If we have a model that we think maybe will be good, we don't really know, so we put it on an openpilot branch, we let some people drive on it, we drive on it ourselves, we gather a sample of data, and then maybe it turns out our model had a subtle bug in it, and now we've just wasted days or even weeks waiting for this data to come back so we can evaluate. So this is a huge waste of time. And so our rule, because of this, is no testing in cars. Instead, we try to write as many offline tests as possible. So before we ever put this on an openpilot branch, we want to have a pretty good idea of how it's going to behave when we do it. So these offline tests can take a lot of different forms. We can test by running the model on real driving data and seeing what it does. We can test the model in our simulator. We can test them in more traditional simulators like Carla or GTA. We can run a bunch of different tests in different cases and see exactly how this thing is going to perform. So what should we test for? Well, there's a few obvious ones. We want to make sure that the model takes exits when the route says to take the exit. So we can test that in our simulator. I showed some videos from that exact test earlier. We want to make sure that the model doesn't take exits when it's not supposed to. We want to make sure it takes turns when it's supposed to, doesn't take turns when it's not supposed to. We want to make sure the model doesn't misbehave if the route is incorrect, if you miss a turn or an exit, if the GPS location is a little bit wrong and it snaps you to the wrong road. We want to make sure that it doesn't misbehave if the bearing is inaccurate, so the map is like pointed the wrong way a little bit. We want to make sure that the driving behavior doesn't regress at all when you're not using nav, because we're just shipping nav in experimental mode right now, and so if you're driving in chill mode, we really want to make sure that behavior doesn't regress in any way, and if anything, it gets a little bit better. And we want to make sure that the behavior of these nav models is the same when we run them on the comma 3 compared to when we run them offline. So we do all these tests, plus a bunch more tests. We've spent the last few months just writing tests, and validating all the behavior we can think of, lots of different edge cases, and making sure that these models behave exactly the way we want. So we've finally written enough tests to give us the confidence to ship this for openpilot 094, and you can try it out today. It's available in experimental mode, and as we keep working on navigation and we drive the reliability up to 100, we hope to ship it in chill mode as well, so it'll be available for everyone that uses openpilot with Prime. So that's my talk. We can give time for a few questions.
All right. Jason over here.
I wonder if you could talk for a second about how speed limits figure in that you get from the maps. I know that you want the end-to-end model to function as independently as possible. You don't want to depend on map data, but do you foresee a future in using that as an input more consistently, especially when not navigating? I'm given to understand the Mapbox API doesn't really lend itself to giving you speed limits if you're not navigating, but I think there was some sort of way around that with the Valhalla server. I don't know much about it, and I guess my question is really, long term, do you see that as an input or a hint into the overall driving?
Long term, I think probably yes. Right now, there's a lot of situations where the longitudinal behavior still isn't perfect. That has nothing to do with speed limits, so we want to fix that first. Like if you're driving on a highway and the model is only driving 55, you shouldn't need speed limits to know it's driving the wrong speed. So we want to fix that behavior first. Like you say, Mapbox's API is not super conducive to giving you the speed limits. There's a lot of areas where speed limits just aren't even available. But long term, I think there's a lot of cases where you can't really tell how fast you're supposed to be driving without the speed limit. So I imagine we will eventually need to add this as a model input, yes.
All right, got a question in the back.
Along the same lines, any thoughts on future input for real-time traffic that would then allow for, changing of routes?
Sort of. So Mapbox already takes care of this. It has its own traffic tracking system. And so ideally, the routes that go into the map in the first place should already take into account the traffic. Now, Mapbox's traffic system is not perfect.
and it does sometimes over or underestimate the amount of traffic in a particular area. But hopefully this is something that'll improve over time.
Hey, have you put in any thought into like text-based navigation using like, I can see from your navigation that you have like take the next exit, for example. Like, do you guys use that as inputs ever?
Yes. So we have a branch right now that hopefully will ship for openpilot 095 after some more testing and validation that puts not just the map, but also the nav instructions into the model. And we find that this reduces the failure rate of the model to take exits and turns even further. So yes, this will probably be coming to a comma 3 near you sometime soon.
Thank you for your presentation. I just have a question. Have you ever considered using vector maps instead of these rendered BEV maps?
Could you say again?
Have you ever considered using vector maps instead of the rendered BEV maps?
Yes. So we do get the vector tiles back from Mapbox directly, and so we could consider using those. And there are some advantages to that, in that there can be a bit of ambiguity just with the rasterized maps in some cases where you have a lot of roads really close together. So this is something we may look into in the future. Mapbox's tools kind of make it easiest to just render a map normally, and then you can just use normal convnet, efficient net to process this and compress it. With vector-based maps, maybe you'd want something more like a graph neural net. And these are a little bit more complex, and so we wanted to start with the simplest thing that could possibly work, but maybe this is something we'll look at in the future.
I used this navigation feature like a few days ago, and I found a problem when I used it. That it works for the first maybe a minute, and then it just quit by itself. Any explanation on that?
I'm not sure. We'll have to look at your logs. Maybe this I can get your information afterwards, and we'll see if something weird is going on.
All right. Another question is, have you ever thought about using the map for the to the very original input? Maybe map it to the perspective view together with the image.
Oh yeah. So the autoencoder we train actually also predicts the trajectory that you're going to take, in addition to just compressing the map. It tries to predict in 3D space where you're going to drive. And so we could potentially use some of these additional outputs to show extra information on the driving view. But this is not a super high priority right now. This is something maybe we'd look at in the future as, you know, the main functionality of nav gets better and we have time to think about some cool additional features.
For the map encoder, is it trained primarily on a reconstruction loss, or is it trained jointly with the driving model so it can more intelligently like select which features are important?
It's trained separately. We do this for a couple reasons. One, because we want to run this model on the DSP instead of on the GPU. And so the map model has to be quantized. And so we train it with the quantization-aware hooks in PyTorch. Without this, it doesn't really work properly. And so in that sense, it sort of has to be trained as a separate model. And then also training full convnets with the sim is a lot of compute. And so it's a little bit easier to split it up. We have looked at doing it jointly as well, either with the vision model or with the policy model. But the autoencoder does do a pretty good job of capturing all of the details of the map. And so for now, at least, we think that it is probably doing just fine to just compress it to this feature vector and then have the driving model process it from there.
We've got one last question here.
So when you started the talk, you talked about how you at first wanted to just feed the video data of the directions into the model, and hopefully it would work, and then it worked pretty well. But I would think that there's like kind of an inherent conflict between the original video input and the map like directions input. Does the model just synthesize those two like magically, or do you have to really like weight them or like try to give inputs on which input is the primary to follow, or how does that work in the model?
You're talking about resolving like the video coming in with the map?
Yeah, the idea that the video tells one set of sort of inputs on how you should direct the driving output versus the map now suddenly might say, actually I want you to go this way. So I kind of feel like the two different pieces of information might give different outputs. How do you train the model to know which to follow and which in what circumstances?
Sure. So this is exactly part of the reason that we train on some percentage of these fake routes. We want to make the model robust to maps that either tell it to do the wrong thing or don't make any sense. And so when we always want to trust the video because the video is always right, or at least it better be, whereas the map could be wrong for any number of reasons. And so we do a bunch of stuff when we train these models to try to make them more robust to failures of the map if the route suddenly goes out or GPS suddenly goes out or any number of things that might happen, road closures, taking a wrong turn, all this stuff. So we really wanted to trust the video more than the map.
All right. Thank you so much, Mitchell. All right. Some of you may know DM to mean direct message. But in the comma world, DM stands for driver monitoring. The father of driver monitoring is here today to tell you about our improvements in the last 2 years. A feature I'm very excited about that we launched, that I worked on, the D-emoji. I think
this thing is hard.
Oh, I think, yeah.
Sorry. Can you go refresh my page? I just refresh it.
We did it.
Yeah. Is it? Can you go to the folder? I want to make sure it's new.
It's not good?
I want to make sure it's the latest. Let's check.
Thanks for your patience, guys.
Go to the folder and see the latest.
Okay.
Oh, what? It's not.
I'm going to provide some announcements. Weixing is the last speaker before lunch. Lunch will be served in the back area. We have trays passed around, so no lines.
So you refresh it, right?
You can feel free to eat down here or upstairs. And there's soft drinks and coffee and tea back there. And we will restart promptly at 1:45. If you bought merch ahead of time, on the 3rd floor and on the back of your badge, there should be she has a list up there. You have a sticker. If you bought merch, they have your name and a bag with your name on it for you upstairs. Feel free anytime throughout the day to pick up your t-shirts and hoodies. Didn't want you guys to have to carry them around, so. Thank you so much. Please welcome Weixing to the stage.
Thank you, thank you.
Hello, hello. Hi, I'm Weixing. I work for research at Comma. Today I'm going to talk about how we view driving with openpilot as a human-machine cooperation problem and how we use machine learning to improve things. So this is how we drive without openpilot as a human. Basically, the driver is the only actor here. But with openpilot, the driver's role slightly changes, and they will now work cohesively with openpilot, with the driving model specifically in some way. So today's talk will be focusing on different aspects of the dynamics between the human and the driving model shown in this graph. So we will cover how we use the power of machine learning to learn about the driver, and then learn about the driving model, and how we ship many impactful improvements along the way. As we know, openpilot as a driving assistance system requires the user to be able to take over at all times. In simple words, you need to pay attention. We already covered how driver monitoring works in openpilot from the last Comic-Con talk 2 years ago. So today we'll be focused on the progress we made since that time. So this is what the driver-facing camera looks like on the 0,2. It's a bit noisy, but mostly it only shows a limited view of the interior for the driver due to a very small view on the 0,2. To make things worse, due to limited compute on the 0,2, we had to crop the image and feed it into the model. It's not fun to build a DM on inputs like this, trust me. For the model, it was like watching a movie, like with all the people standing in front of you, like blocking the view. That's basically how it felt like. Moving to the 0,3, this is the initial model we shipped using the 0,2 data before we had any real amount of 0,3 data to train on. And this is the new model we train on the new 0,3 data. And the model we ship currently is shown. It's shown with the green box, which basically covers the whole interior instead of just some part of the driver. Now, as we can see the full body of the driver and hand and even the steering wheel. And then the same is true for also the passenger. With that, now we have achieved on the 0,3 almost 100% of face detection rate. With that, we can remove the wheel touch when the camera is not blocked and use vision only for DM. Yeah, because it's not the best idea to assume the driver is paying attention when they are touching the wheel, because that can easily be cheated, like in a Tesla. So another thing we can do was to remove the right-hand drive toggle, with the model now now being able to detect whether which side the driver is driving on. Say you're in like the US, you're on the right in this image, or you're on the other side if you're driving on the wrong side of the road. So with that, we can remove the right-hand drive toggle. One less toggle is always better, as Adeeb says. We'll come back to that passenger thing a little bit later. So in terms of true positive, we have achieved a net gain of almost 2x in true positives by using a bigger model box. And then now we also have the extra benefit of the extra context we have with the full interior camera. With the extra context, we are able to build upon it to do this. So last time on my Comic-Con presentation, I mentioned that we will explore moving to a more end-to-end approach, a more end-to-end approach for DM. Now I think is a good time to do that. So in a classic DM policy, we have the model that predicts some attributes of the driver, and then those are fed into some state machine to determine whether the driver is distracted. But in an end-to-end DM world, the model should be able to tell from the footage like whether the driver is paying attention or not directly. So here is an example of the Adeeb driving. As you can see, other than when he was looking right at the road, or when he was like straight distracted by his phone, there's also a lot of gray areas there. As a human, even as a human, it's tough to tell like whether sometimes he's paying attention or not. So we need to define attention to be able to like have good ground truth for end-to-end DM to learn from. Here's a hint. DM doesn't live in a vacuum. It's part of the system, part of the openpilot system. So what is attention really? So the answer really is quite simple. We already know that openpilot is a driving assistance system again. The driver should always be ready to take control. So with that in mind, we are ready to get our ground truth. With that in mind, it's simple that the paying attention definition should be whether the driver is ready to take control at any time. With that in mind, we're ready to get our ground truth for the end-to-end DM system. So we make two simple assumptions. The first one is the probability of taking control is higher when the driver is driving or taking control. That's pretty obvious. And the second one is the probability of not taking control is higher when the car is at a standstill. So it turns out we already have those things in the logs for a long time. Therefore, you can just use them to train the model to predict from the driver footage whether the driver is ready to take control or not. So with those naive ground truth I just mentioned, we train a vanilla end-to-end model that predicts whether the driver is distracted from some frames. And you can see that it sometimes reliably detects when the driver is really distracted, like Adeeb was looking out the window. He was definitely not ready to take control here. But the model also thinks Adeeb was not ready to take control here, where he was just chill driving. And so it's this. He was looking at the road while turning the radio, which in a taking control context is fine. So we need to fix those false positives. So we realized that the only way to fix all the ambiguity, which it's most likely a finite set, is to have the real human to label some of those difficult scene cases. Because of the fact that we already have a helper model that's trained on vanilla DM labels, we can use that model to help us find all the interesting stuff. And then only 2% of our entire data set ends up needing to be labeled. To get the perspective, we outsourced the labeling work to a third party, and it took them only one person in less than 3 days to do our labeling. We pay virtually nothing to gain a lot of improvements in our ground truth. So with that improved ground truth and our end-to-end DM model training on that, the model is now able to pick up additional subtle distractions like using phone without force triggering on chill driving poses, like in this example, in this example shown here. Whenever the timer drops, it means the system thinks Adeeb was distracted. So you can see this is fairly accurate because when the timer drops is where Adeeb was really not able to be ready to take control. So to put it in a number, with a number, we have metrics showing that the net result of adding end-to-end policy is to have a 15% gain in true positive with no false positive gain. So now let's change our focus onto the driver by looking at some behavioral metrics. Remember in full-frame DM I mentioned earlier, we are now able to detect from DM model if there's a passenger or not. So by overlaying that with the driving data, we came to the surprising conclusion that when people drive alone compared to driving with a passenger, they are 4 times more likely to take a corner over half a G. And 2.5 times more likely in hard braking. And twice more likely to tailgate someone. So that all that aggressiveness difference in driving from having a passenger or not inspire us to do a whole driving style analysis on our fleet. We basically classify driving style using metrics like hard braking, hard acceleration, or like hard turning, etc. And then those things are used as a conditioner to fit into the driving model. And as Harald mentioned, by using like the chillest profile, we actually make Taco Bell drive much easier by making it drive smoother. So another metrics that is super important to our company is that we need to understand the relation between making driving chill and potentially making driving making drivers more prone to distractions. As always, we talk with numbers, and we have metrics for exactly that. So the first conclusion from our metrics is that drivers generally pay more attention to the road when using openpilot than not using openpilot. So here, the green curve shows the distribution of segments with different percentage of distracted times when engaged with openpilot in green, or not engaged with openpilot in red. So essentially, the more left the curve, the less distracted the drivers are. So we can see that when engaged, drivers are generally less distracted. That number actually is around 40%. So that's a big improvement. So actually, it's actually not too surprising to imagine these things, because with openpilot, it first takes away the taxing stuff from driving and allows you to pay more attention to the surroundings. And also, it's hard to not pay attention when like it yells at you when you get distracted. The second one is actually more interesting. There's a common doubt that if you've been using openpilot for a long time, you start to lose attention and become complacent, and in the long run. So, but our long run metrics disagrees with that. This is an aggregate of the same bunch of drivers in the long term. Distraction trends, and the lines remain pretty flat for different percentiles of distraction durations. So we are confident that our users don't get more distracted as time goes by. So now with the driver out of the way, now let's talk a little about the driving model itself. So the model is an integral part of our human-machine system. And it's crucial that we understand how the driver can interact with it and how it can potentially interact back with the driver and make the experience more coherent. The human driver mostly interacts with the driving model by disengaging or overriding. Those disengagements give us strong signals of when and hopefully why the model doesn't do well. And therefore, we've been putting a lot of effort into building and looking into disengagement metrics. We've been tracking the longest time openpilot can be engaged, which is easily in the hours. It's good to know openpilot works, but this kind of stuff all look like this, and it can't really help us improve. It's like similar to someone who learned driving on the highway only, and they can't really learn anything. So the question we have been asking lately a lot is, where do openpilot users tend to take over? And we build this. This is our automatic disengagement reports. So it's a tool that enables us to do large-scale, up-to-date disengagement analysis. So it runs daily, automatically, and is shown on our biggest TV in research. Essentially, it gathers all the lateral and longitudinal override data, as well as the unexpected disengagements. And then with all the logs parsed, we are able to group all the disengagements by the disagreements between the human and the model, so that we can split them into different classes as shown here. And here are just some examples of different kinds of disengagements. So basically, we show a list of random examples for each kind of disengagements on the reports. And then everything is visualized with necessary data. Like in the GIFs here, we can see in this report, there's been turn cutting, and we can like go to the turn cutting person in comma, which is one person, and say turn cutting team, which is one person, and say, oh, there's been a lot of cutting lately. What's going on? And then hopefully we can have it fixed. So here is another example of how we use this report to fix a real complaint. So there's been, as people know, like there's a lot of noise about people asking, oh, we need to adjust the following distance. It's following too far on the highway sometimes, like this Discord user, Johnson. And yeah, we listen to that, but we need to back that out with data. So we look at the disengagement reports, and we saw this. There's like, so you can see there's more than 30% of our longitudinal disengagements is due to the model following too close or it's braking too hard, too early for a lead car. So we know that this is a real problem. And then by like giving this to the right person, we were able to figure out not only this is a real problem, but also we know how much we need to fix this problem. So we come up with the latest longitudinal personality toggle in our settings. So the last point I want to discuss is how the driving model can potentially give feedback back to the driver to communicate his uncertainty. So first of all, how do we know if the model is uncertain for some given predictions for a given amount of seconds in the future pretty well? So we can rely on the model itself to tell degrees of traffic at the traffic lights, which makes the model more uncertain. And on the right side, we have like things where scenes where openpilot would probably not work, like merging this UK narrow road or turning onto this busy street after a stop sign. So the first step we can do is to show uncertainty in some kind of confidence indicator in UI. This is actually a work in progress we're doing now. So remember that in 094, we shipped the always on border, which means it always communicates the engagement status. So we're thinking, oh, why not? We can use that and change that to something less green when the model is less confident. So say in this example, here it's just like one lane road, it drives fine. But here, then like 2 seconds later, it sees this potential divergence, and it becomes less confident and might need your attention. So it's nice to have that dynamic between the model and the driver. And also, like, say, when the bird finally poops on your car, it probably becomes red. So, yeah, that was my talk.
All right.
Hey, great talk. Couple of questions for you. What's your overall thought on the long-term time and investment that's going to be spent with DM as we actually every day get closer and closer to level 4, level 5, where conceivably you don't care that if the driver's asleep or in the back seat completely? What's your general thought on that? How that's going to evolve?
I mean, in the context of openpilot, we probably always require the user to pay attention. But in terms of level 4, level 5, I would say there will be, in the future, some interplay between like how confident the model feels and how the DM policy should adapt. I think that's the final goal.
Okay, that makes sense. So maybe certain times it might be needed, but other times it would be fine, and maybe alert the user to, hey, we need you to probably pay attention now to be safer, but in general, you're okay otherwise.
Yeah, we already have some adaptive DM policy in place, so that might be a good place to start.
Okay, and then just a quick question on the actual eye gaze and tracking on that.
Yes.
I know with like Teslas, you can just put on sunglasses and it says, yeah, he's paying attention, even though your eyes can be completely closed. Does this system have anything with like eyewear or glasses that, you know, that it's not detecting eyes, and does it assume that you're fine? I don't know if it's common knowledge of how that works or not.
I think whenever your eyes is invisible, it just falls back to head pose. And the end-to-end policy is actually really good that when you have some weird poses, other than, you know, just normal driving position, say you're sleeping when you're wearing sunglasses, it can probably pick that up and say, oh, there's an anomaly here.
Great, I got a question here in the back.
Hello, awesome talk. Do you think that near symbolic approach with something like propositional logic will be viable solution for deeper understanding of actors in environment?
Sorry, can you repeat?
Do you think that in future near symbolic approach with formal logic, declarative logic with sub-symbolic models will be viable to deeper understand the behavior of actors in environment to predict future?
I'm not sure about symbolic.
Near symbolic, it's like deep learning plus declarative logic.
Oh, I see. I mean, our end goal is to have end-to-end driving model that just looks at the scene and tells us where to drive and potentially like how confident it is about like doing this path. And I think in the future, as the driving model gets better, it should just be able to tell like naturally with our end-to-end approach. Does that make sense?
I wonder if you could share a little bit about how you classify and what breakdowns of data you get from classifying drivers as chill or not. It's a fascinating topic for me. I've gotten old and I use openpilot a lot, so I mostly drive chill, but every once in a while I throw my car on an autocross course and I use openpilot as a data logger. So is there a memory to that? Are you classifying per segment, per route, per device? And
it's a per route.
As a off-the-wall question, how many openpilot users would you say are good drivers?
I mean, we classify them into 5 categories, basically. But I don't think we track like specific dongle IDs. We more like focus on the route, I believe. Yeah.
Got anything else, Weixing? That was a lengthy question. You satisfied with the answer, Jason?
You kind of dodged the one where I asked how many openpilot users were good drivers.
It'll be opt-in to share this with your insurance company.
All right, we got a question upstairs.
Thank you. If you come back to like 2 slides back, in terms of like giving feedback to the customer about uncertainties, communicating, I'm thinking if it's possible at all, but yeah, not exactly that, but where you had like uncertain model being uncertain about specific and trying to communicate it back to the driver. Not this one, like the real like mock-up of the road, like with the vehicle, like the picture, like few more slides.
A few more?
Maybe like forward, not back.
Oh, the one with the driving behavior?
Yeah.
Here?
No. There's one of the last ones, like.
Which one?
The red and the yellow one.
Oh, this one. Okay.
No. With the road, like. With
oh, sorry. Yeah, sorry. It's, this one.
No. More. No. you're going to the right direction, but to the end of the presentation.
Oh, that. Sorry. That's
yeah, this one.
I'm
thinking, I don't know if it's possible at all, but it would be nice if it could also communicate some areas where it does not want to go, like for example, if there is like vehicle parked or like some blockage or whatever. So like maybe in I don't know, in the red.
Yeah, we can have a hard cutoff, like ideally for like some sketchiness of the scene, and say, oh, you should probably disengage here, and give you a super short timeout.
Anyway,
if that makes sense.
Yeah, cool stuff. Thank you.
All right, I'm coming over here.
Hey, awesome talk. You mentioned you make some assumptions to determine whether the driver is attentive.
Yeah.
Like if they're driving, they could be more attentive. If they're at a stop, maybe less attentive. So I was wondering, I assume these are neither conclusive nor do they always hold. So in the future, do you think it's possible to also use data from the driving model? Like maybe if someone's drifting out of the lane or if they stop more suddenly than the model was, do you think that can be used as a negative signal for the driver monitoring?
Do you mean when engaged or not?
I guess either way.
Either way. Yeah, I think that stuff is a little bit more far away from like what we're looking for. Because in here, although those things might not seem immediately obvious, you can see in the data there's a distribution shift from, say, taking control or not, or like being standstill or not. And we picked up that signal and we capitalize on that to determine whether the driver is ready to take over. I think that's good enough with some refinement.
I have like kind of a far-fetched question, but have you ever considered using driver monitoring to not just communicate like uncertainty between the model and the human, but somehow have the human communicate intent back to the driving model? For example, during a lane change, if the human is looking in the rearview mirror, you could use that as a signal that the human wants to is affirmative, that it knows it can turn left.
Yeah, but we cannot always assume that. There will be a lot of false positives, so whichever way.
All right, we got time
interesting
for
point.
one last question.
Do you measure the driver takeover or disengagement reaction time somehow? Like when model is openpilot is driving for 2 hours, and do you see that it affects driver's reaction time in case he needs to disengage?
What's the question again?
Do you measure somehow the driver's reaction time? Does it change if the openpilot has been driving for example, 2 or 3 hours without disengagements?
You mean the DM threshold timeouts or the model confidence / disengagements?
If there is an
we don't have metrics for that, but I think like the second long-term DM metric is pretty conclusive about like people using openpilot for a long time.
Okay, thank you.
All right, actually we got one more question. Someone over here have a question? We good? All right. Thank you so much, Weixing.
Thank you.
All right, live stream crew, you're good to put the virtual world on hold while we eat. As I mentioned before, there's a food station down here. There's a food station upstairs. Oh, I forgot to mention, we'll tune back in at 1:45. Sharp. For George. There's on the 3rd floor, there's a comma point exchange booth. If you use your same comma points email that you use to register, we have your points. If not, we will look them up live. So knock yourself out. That'll also be open after the talks this evening. We'll see you. Enjoy lunch.
Right on time, back by the beach. Still gonna bring the heat. Bring the heat. The heat. Doing all that I can for you. Like a flash from a gun, I knew that the more that I run, honey, won't help to make it better. Still, I can feel the heat, yeah. Don't let it catch you. I can't feel the heat. I know I can't get you home. No. I know I can't get you home. I know I can't get you home. No, I can't feel the heat. Yeah, I know I can't get you home. No, I can't feel the heat. No, doing all that I can for you. Don't you get on? To be a warm-blooded man, honey, so I can treat you better. acordaste de mí cuando viste a ese tipo. Y fue esa noche así cuando él no me dijo. Y ahora no me acuerdo, no me acuerdo, no me acuerdo de nada. Pero eso sí quise que no es él. Es el bandido, bandido, bandido del amor. Es el bandido, bandido del amor. Es el bandido, bandido del amor. Es el bandido. Fue una noche así, con el contigo. Fue una noche así, con el bandido. De Perú a Paraguay, el bandido. De Colombia a Brasil, el bandido. Bandido el amor, el bandido el amor, el bandido el amor. Bandido el amor, el bandido el amor, el bandido el amor. Fue una noche como así que te cultivo el bandido. Una noche como así como me viste con el tipo de bandido. If I can understand it,
didn't hurt me. That you wanna feel how it feels. That you wanna know that it didn't hurt me. That you wanna hear about the deal they're making. You. It's you and me. It's you and me. If I only could make a deal with God, not get him to swap our places. Be running up that road, be running up that hill, be running up that building.
Last call on burgers. If you didn't get one or want seconds, it's your last chance. Last call on burgers.
you should know you'll be sorry someday.
My camera on, I cut my fingers on the way, the way I'm slipping away. I turned my feelings on, you made me untouchable for life. Yeah, yeah, and you wasn't polite. It hit me like a ton. You hit me like a ton. I turned my feelings on. I turned my feelings on the side. Yeah, and like I'm gonna ignite. I saw them stars go off. I saw them stars go off at night. Oh yeah, yeah, and I'm looking right. Roll up, keep up, roll up, get up, roll up, keep up, show me like a tongue. It hit me like a ton. Oh, it hit me like a ton.
get an intro. Hi. Okay. Don't worry, it's a long talk. You guys know that Black Mirror episode where they have the ratings? It's my favorite episode. You know, that woman starts off with a very high rating and watches her rating plummet. And at the end, she has the 1 star and she's in jail and she's just screaming and she feels so liberated. This is what I feel the world's like right now. You know? Like the GPTs have made it so obvious that it's all bullshit. All of the niceties in language and all of the, oh yes, I'm going to write a 4-paragraph email to express a 2-sentence idea. Is it over? Is the professional managerial class over? I heard the Barbie movie described last night as post-woke, and I thought that was really cool. Okay, my talk is called 3 Stories, and we have 3 stories, one about the past, one about the future, and one about the present. So we will jump right into the first story about the past with the cruise automation. So cruise automation, most people don't know this, right? Most people see the weird orange hat branding today and like, look, we're building cars that are symmetrical. I don't even get it. But you know, Kyle was actually first building the Cruise RP1 Highway Autopilot for $10,000. And it sat on top of your car like that, assuming your car was an Audi A4. And it worked on the highway to drive. So Lex was guest 14. Kyle was guest 14 on Lex. And he gave up due to the technical challenge. He didn't give up because it was a bad idea. It's actually the right idea. He gave up because it was too hard. And he had 3 concrete complaints about why it was too hard. One is that there's a long tail of cars. Right, so they built it for the Audi A4. We're like, okay, we can make it work on the Audi S4, maybe the A6, and you realize that almost no one drives Audis. Right? We started with an Acura. Look, I made the same mistake. And it turns out there's this absurdly long tail of cars. So how do you deal with this? Well, you just do it. It's not that much work. Comma's a 20-person company, and we just did it, thanks to contributors. Thank you, contributors, but like it's doable. Right? You just do it. Okay, cool. Oh, but how do you handle failures? What if a car has a sensor that fails, or a GPS that fails, or a camera that fails, or a steering wheel thing that fails, steering wheel actuator? Okay, you just do it. OpenPilot has a great error detection and handling system. The alerts. Alex Roy drove in a car with the Comma 1, and this is what he praised. He's like, wow, this thing actually like communicates with you. So hopefully you guys have experienced that using OpenPilot. Like it actually, gives you errors that tell you what's going on. Then we track all of these on a back-end dashboard and we drive them down to 0. So again, you just have to do it. It's different in one version of the car. What if the car manufacturer updates the firmware? Okay, you do it. Fingerprinting. Yeah? We'll read all the firmware versions. We'll figure out which ones matter. We'll figure out which ones don't. We'll do this at scale. Right? These things are engineering challenges, but you can't fake any of them either. When you ship a product to people, you can't fake any of this stuff. Right? You guys probably mostly have OpenPilot. You guys probably mostly have Comma 3s, and it works in your car. And it handles failures. It deals with all the different versions of the car. You just have to do it. Comma was not supposed to exist. There is no sane reason that this company should exist. The second round, when we raised from Andreessen Horowitz, I pitched him a crypto coin. Hey, look, man, you want to hear? I'm telling you what you want to hear, man. I'll tell you what you want to hear. I know they're bullshit, but you want to hear it. Fine, I'll tell you that. I know enough about crypto to make it sound convincing. Our third round, we raised from much more aligned investors. Look, and it's not that even that Andreessen Horowitz is bad. It's just that, like, again, you have to think about what these people are optimizing for and what time horizon they're thinking on. Usually very short time horizons. But then again, you ask yourself, what's what's worth doing in the world? You guys know this scene from Back to the Future 2? If you're not building a company that looks like that line, what are you doing with your life, right? If the only thing that's going to be different, if you succeed with your company, this is to everyone in the audience, everyone out there watching, if the only thing that's going to be different is that the pile of money is in your entry in the SQL database instead of somebody else's, why are you doing this? Bro, it doesn't matter. Just update the SQL database. It's a lot easier. So yeah, build companies that look like that. Companies that are going to change the future. Not change the distribution of wealth in the future. Right? I'm not doing this to we'll get to that. This is a story about the past. So here we are. 6 generations of the hardware. 0, Eon, Neo, whatever. You play with the letters a bit. Comma 2, comma 3. I love when hardware companies just do that. Just make the number bigger every time so you know, right? It's easy. Yeah. That's it. 250 plus cars. Every major brand, except for the FlexRay ones. Mercedes, BMW, no, but otherwise with Ford, that's all of them. 25 employees. And open source. Right? So I think it's pretty easy from this to tell that all 3 of those numbers are going to go up. Begrudgingly on the 3rd one. Very happily on the first 2. And open source will stay. You want hardware to be good? Look at an iPhone, right? This is iPhone 13. You know why it's good? Because they built like 13 other ones. They built even more. Right? That's how you make something good. You just keep doing it. You just iterate it. Ship it, you iterate on it. You want to support more cars? Okay. Make sure you don't have regressions. Well, we'll get there. I mean, how do we do this, right? Let's start with some like that one, right? Did you hear Helion Energy is going to ship fusion power to the grid by 2028? Did you hear Cruise is going to have $1 billion in revenue by 2025? Like, can I bet against these things? It's fake. I hope that everything you saw here today, you got like a real sense of honesty. And part of the reason you get honesty here is because we don't have communications people. What are communications people in a company besides paid liars? Right? What is the job of a press secretary? Oh, okay. You murdered 30 orphans in Cuba. I make it look good though. Make it look good, right? No, like it's just honesty, and it's honesty because lying, if you tell the truth, you don't have to remember anything. You know, that's a good quote, right? Shipping. You got to ship. Shipping keeps you honest, right? You ship stuff, you send it out to people, and they'll tell you about whether it's crap or not. You know how they'll tell you? There's 2 types of ways to measure people's preferences. There's stated preference and revealed preference, right? Stated preference is things people say they want, like, well, wouldn't it be nice if we had cars where we could share the car so we could save the environment? And then you look at the HOV lanes on highways and the usage of Uber Pool, and you're like, wait a second. No, everyone wants their own car, right? Revealed preference beats stated preference. So how do we measure revealed preference? We sell something profitably and then see who buys it, right? So shipping. Iteration. You know how you build something good? You build it bad 3 other times, right? And that one's still not that good. That one is bad after you get to the one that's built 3 times later, and there's no way around this. The only thing you can control is your iteration speed, right? How quickly can you iterate? How quickly can you come out with new versions? How can you reduce the REPL time? But you have to iterate. And then the last one is humility. This guy used to call me ego hot. It's kind of funny, right? I do have a big ego. I think I'm better than a lot of people. I mean, that's a true fact. Right? I think I'm better than a lot of people. Now, look. You may disagree with me about that fact, and I'm open to having a conversation about it. I'm open to, what shall we challenge each other at, right? But that's not what humility means, right? That's like acting. Humility is saying, okay, there's an actual problem. How are we going to solve it, right? Like, it's humility not as some status game, but humility in the real face of nature. How do you solve these problems? Well, you have to have humility. You know, it turns out you think, oh, well, I'll train the machine learning model and it'll work. You know, I thought this was a comment. I'm like, well, I'll put in the output path and I'll put the image in and it'll work. This turns out to not work at all. You can look up behavioral cloning or imitation learning for why it doesn't work. And you just got to have humility, you know what I mean? Like nature doesn't care. Nature doesn't care, you know? And it's humility versus nature, not humility versus people. So yeah, you know, you got some values of a company, right? All right. So why haven't we won? Doing everything right? We can talk about what I'm doing wrong, we can talk about what we're doing wrong, but why haven't we won? And the truth is things take a long time, even accounting for things taking a long time. This is not the first Comic-Con. This will not be the last Comic-Con. All right? Humans live a long time. You know, this is something that a lot of people forget about in the world today. Like, a lot of people are so like, man, how can I get rich quick? How can I pull this scam? How can I ship fusion power to the grid by 2020? Bro, you can't even ship fission power to the grid by 2028. You know? So, you know, I'm 33. I'm going to be here for a while. All right? So you start thinking about that. I'm not trying to get rich. I'm not trying to retire. There is no exit. There's no exit. Okay? You know that book, Start? No exit. This is no exit. This is it. This is it. Hell is other people, right? Like there is no, well, we're going to get to this point and then we're going to stop. No. The system is going to get better, and the system is going to get relentlessly better. Right? This is Comic-Con 2. We'll see. This is about the past. Think about like climbing out of a well. So let's, you know, put it, self-driving, right? How long is it going to take to solve self-driving? No idea. But as long as every day you make forward progress, as long as every day you make a few steps climbing to get out of the well, and as long as at night you don't slide backwards, as long as you follow that algorithm, you are eventually going to get out of the well. Right? Avoid regressions and make slow and continuous improvement. This is how you make things good. It's like climbing out of a well. There's not another way to do it. No, but you don't understand. We're going to get a huge cash infusion and it's going to... No. It's not going to get you out of the well, man. What are you going to do? You got a number in a SQL database, right? It turns out these companies are scams, right? Well, it's Aurora, Too Simple, Luminar. They all raised way more money than Comma did. Which? Well, none of these are fusion. These are all self-driving cars and LiDAR. But, okay, so it's a question, right? What does it mean for something to be a scam? Does something to be a scam require awareness on the part of the creator that it's a scam? Right? If the answer to that is no, if you believe that intention matters, then what you're going to get is honest idiots to raise billions of dollars. Right? They're being honest, but they are idiots. Right? This was obvious to me. I've been saying this exact same thing now for 7 years. I could have told you. I did tell you. People don't listen, right? You know, people also thought that BitConnect and Luna weren't scams. Right? There's people honestly out there who shilled me both of those products. Right? And now, I mean, look, both of their founders are in jail, so, you know, we can all, like, there's a spectrum of scams, right? But, yeah. You know, we'll get to Cruise and Waymo later. Marginal utility approaches marginal costs. This is a true theorem of economics. And what is the marginal cost of openpilot? What's the marginal cost of openpilot? 0, right? So if openpilot provides any utility at all, marginal utility approaches marginal costs. A lot of times you don't want to measure success in value creation, because a lot of value creation is a scam. Look at GDP. Kind of want to measure success in value destruction. If you can destroy fake moats of companies, openpilot will continue to get better. openpilot will solve self-driving cars, and openpilot will be free. Did you know Linux is the fastest growing platform on Azure? Satya's a smart guy. Embrace, right? Embrace. The car companies that are smart will embrace. The car companies that are not smart will ship you the Sun Cloud or the Oracle Cloud or whatever cloud, you know. Oracle still exists. I don't know how they make money, but whatever. Linux is the fastest growing platform in Azure. Markets do approach rationality. You just have to survive. Market can remain, you know, irrational longer than you can remain solvent. Yeah. This is lifetime revenue, comma. See a nice R of like that, something. This is the amount these companies have made in lifetime revenue versus the amount they've raised. No, like, I don't get it. I don't know, man. Maybe I didn't go to Harvard and get an MBA or something. But like, bro, well, okay, look, man, we raised $3,700 million and we made 200. Okay, that's cool, man. Like, I don't get it. I don't like. I'm not even saying like, okay, obviously when you first raise for a company, this is true. But these aren't recent raises. Like these companies have raised after they were not even remotely close to making back their initial investment in revenue, not profit, revenue, right? You can look at other companies like Amazon and Uber and be like, well, I mean, Uber's hilariously unprofitable, but they make a lot of revenue. They have a lot of users. These companies don't. So this is the number for comma. 22.2 on 18.1 million raised. His Twitter followers for, all right. I told you I'd address Cruise and Waymo. Right? So I actually do honestly believe that Cruise and Waymo have larger marketing budgets than the operating budget of comma. Right? And soon, man, soon. All right, look, they use a linear model, but like this is what the website said, so. Employee retention. 4 people have ever quit over 7 years. It turns out honesty is a great draw. Sane mission-focused governance, a commitment to iteration and improvement. Come work here. Look, all this stuff, everything about openpilot, I didn't do any of it. I haven't pushed to commit to openpilot in 2 years. It's everyone else you saw talk here today. You know, it's not me. My sole job is to keep idiots far away. Right? That's really my only job. Right? Like it turns out, yeah. I promise the other parts are more upbeat. The past is always depressing, you know. But no, seriously. To anyone watching this, to anyone in the audience, if you want to come work here, look, the bar's really high, but what we ship hopefully is really good, and you'll get to ship things. Right? You'll get to ship things. You'll get to be a part of this process that makes things better in the world. And I think that's the real thing, especially as we approach this, like everyone, late stage capitalism, everyone kind of understands the economy's whatever, man, Fugazi, right? I think the thing that people really want is that. They want to make the world a better place. And like I said, if your startup looks like this, you know, you're just changing the distribution. But if your startup looks like this, you're changing the world. I did not realize I was entering such a dishonest game. I have never seen a more wretched hive of scum and villainy than I have in the business worlds. But, you know, we're going to win anyway. Just takes a lot more out of you than you think it's going to. Okay. The future. I'm excited about the future. I really am. So we'll start with a nice quote from Eliezer Yudkowsky. Plug in the numbers for the current computing speeds, the current doubling time, and an estimate for the raw processing power of the human brain, and the numbers match in 2021. Interesting. Not like that far off. I think we have a little bit of still work to do on the software, but like everyone kind of sees it, right? Like this is a lot easier. I've been talking about this stuff, man. I read this quote when I was 15. It's changed my life. My whole life, my entire life trajectory has pretty much been because of this guy in this document. I'm sure he incredibly disavows it right now. We got to nuke the data centers. Don't forget. But no, really. Yeah. So what is the future? I'm going to tell a little story, and my story is called Forward-Looking Statement. Let's see how much time I have. Ladies and gentlemen, welcome to Comic-Con 9. It is the year 2037. I am an AI-generated voice. Hiring real people to do PAs became way too expensive in the early 30s. We've grown quite a bit since the first Comic-Con in 2021. We have 44 stores in malls around the world. and 1 billion devices sold. In the top 10 biggest consumer electronics companies, and we did it without selling out. So let's look at a picture of a mall. This is a real mall. You guys should all check it out while you're here. It's up in La Jolla. It's called the UTC Mall. And I'm serious about the mall store. Like it's written on our boards inside. Like, come on. Isn't this where you want to buy a comma 3? Isn't this where you want to buy a comma body? You know, like come by the mall store. No, the metaverse is lame. It's going to be a real mall store. Go get a Cinnabon. No one has Cinnabon anymore. Get a bubble tea. Happy Lemon. So we're gonna have a store in the mall. Yeah, that's gonna happen. The mall store is real. It's hard to go anywhere without finding a comma. Remember, it's 2037. In its 3 form factors, cars, bodies, and puppies, it is versatile enough for everything. You'll find commas transporting goods, cleaning houses, cooking meals, and just being a lovable companion that will go anywhere with you. It's not rendered. Yeah. Now announcing the comma 7. Just $20 that many dollars. They have to be $20, $23. Look, I don't control the inflation. It's a 3rd generation comma ASIC. 50 pops of compute. That's 50,000 tera-ops. For reference, the comma 3 has about 5. So we're off by a factor of 10,000. Don't worry. The future comes fast. Slowly and then quickly. It's the first comma device to boot into TinyGrad. Well, no, really. Like, look at OpenPilot, right? Like, OpenPilot is kind of this. OpenPilot right now kind of means 2 things, right? It's kind of both this system layer and the self-drive layer, right? The self-drive layer is a policy model for driving on roads. The system layer is like a camera daemon. Maybe we'll even start to move things like the vision model into the system layer, right? But you have this system layer in OpenPilot which runs foundation models, right? And then you have, on top of that, a policy model which does driving, and then underneath that, you have TinyGrad. You have an operating system which can run all these models and schedule them appropriately. 50 pops is a magical number. Combined with the latest version of OpenPilot, our foundation models learned in the cloud, RL in the world, and a good amount of on-device learning, we expect a comma 7 to be able to do anything a human can do. This does not stop at self-driving cars, okay? Level 4, level 5, this is boring. Oh, but I heard the question before, not to pick on you, like why don't you focus on like an application? Oh my God. I'm trying to build people. We're trying to build people. That's what we're trying to build here, right? Self-driving is just a really cool, it's kind of a restrictive problem, right? You can refine your techniques in self-driving. It's like a game. But eventually, this all becomes general purpose, and sooner than you might think, right? I was trolling, you know, when we did the Taco Bell challenge, Elon replied to one of my things, and I was like, yo, our system's going to be so end-to-end that even our DM's going to be end-to-end. You guys saw it. Yeah. Anything a human can do is an interesting thing, too, right? So this is a My300. This is what we build the comma 3s on. You understand that it's being operated now by a comma 7, right? You understand that most of the employees in the company now are commas, right? It's interesting, right? I mean, how many of our, and you'll hear about this in a later talk today, how many of our workers, how many people worth of compute does comma have if you define a person as 20 petaflops? And you'll get an answer to that later today, right? How many silicon people work at the company? I'm not here to discriminate, man. I'm more progressive. So yeah, no, I mean, it was crazy. When we first saw comma 7 actually come over and like help build the other comma 7s, it was a wild. Your comma 7 is yours, just like your comma 3 is yours. The models we train in the cloud are foundation models, meaning they do not have opinions. They're not RLHF'd. They are true foundation models. And I want to give a thank you, even though I lost $80,000 in your stock and really regret selling it, I want to give a thank you to Meta for releasing Llama 2 as the foundation model and not just as the RLHF version. We want to do the same. And I will, whatever it takes, there's no cause I believe in more than open source AI. So the models we train in the cloud are foundation models. They do not have opinions. We do offer some pre-trained policy models. We call them custom software. Maybe some of you are familiar with that. Right? If you want a pre-trained policy model that drives a car, again, how it drives a car is a decision. Right? We make some decisions about how to drive, right? But that's when you get into opinions, right? Foundation models are unsupervised trained. Policy models are trained supervised in some way, shape, or form, with some RL, with some supervised, with whatever. But by default, the comma 7 is like a child. It will learn whatever behaviors you teach it, so teach it well. And it should pick up skills as quickly as a smart human. What's that? Yeah, I don't really know what's next. The comma 8 will likely be running the company. Let's look at it for a minute, right? It's got 2 eyes. It's got a mouth. It breathes air. It has 2 ears. I've pushed hard to keep those 2 ears. It has a spinal cord. See the spinal cord? I mean, yeah, all right, look, it's a comma 3. It looks like a little bird brain, right? It looks like one of them dumb dinosaurs, you know? But we'll get there. We'll get there. Robotics is all a question of intelligence. Right? Turned out, how many of you guys have robot vacuums? They're pretty good now, right? But how many of them eat quartz? Right? Why do they eat quartz? Well, because they're not smart enough to really understand. And like, the comma 3 has about the same intelligence as a bee. Right? It's not as smart as a mouse, never mind a dog or a human, but we'll get there. Robotics, and that's like, humans are so good at like moving. We are so dexterous with our hands. People forget like how good humans are. People forget how good humans are at driving. They have all this self-driving rhetoric, oh, the cars are going to be safer. And I haven't seen a car that's anywhere near as safe. Right? Now, ADAS systems can make it safer, because ADAS systems, you pay attention at all times. And I do believe that ADAS systems make it safer. But a system that completely takes control away from the human, you're forgetting how good humans are. Humans are really good. And humans are good because they're intelligent. They're intelligent. Robotics is all a question of intelligence. But now back to the present. It's 2023, and you are at Comic-Con 2. Thank you all for coming out. I hope the things you saw today were good. Mall store. All right, come on. I really went off in the weeds of the future there, but the mall store is going to happen soon, right? The mall store is going to happen soon? All right, I love it. All right, and the present, yeah. Present clip art. All right, I'm going to sit here for a minute so we can all decompress a little about the future, because we're really about to undergo a major tone shift in the presentation. The next slide is a major tone shift from this hypothetical future where robots are replacing, coexisting with humans. So major tone shift coming, and I'm just sitting down to prepare all of you, and now I'll go back to the presentation. All right, so we're going to start with some context. These are the failure rates of iPhones. All right, whenever we discuss failure rates, nobody is really Apple is never going to put failure rates on their website or in any of their marketing presentations, but I understand this is very important to a lot of you that buy the hardware. It's very important to me as well. So to calibrate, iPhone 6s were the worst and had a failure rate of about 26%, whereas you got down to like iPhone X's, iPhone 8 Plus, and they were like 3%, right? So the range for iPhone failures is 3% to 26%. And these are the real numbers, right? I could do it for game consoles too, but I like this chart for iPhones. So this was the failure rate of the Comma 2. Yeah. These are just real numbers. You know, like I said, we don't hire any marketing or communications people, so we don't have any people to make up fake statistics to lie to you. I just actually took these screenshots from our real, okay, how good is the hardware we're building? The Comma 2 failed a lot. You know, look, we honored the 1-year warranty, spent a lot of money honoring that 1-year warranty. And one of the biggest priorities for the Comma 3 was this cannot happen again. We are going to make these devices good. We did a lot better with the Comma 3. So you see orders of magnitude. We've shipped about 7,000, 6,000. We did a lot better with the failure rate on the 3. And the real story is even better than what that shows. So this is the Comma 3 failure rates by month. And you can see a jump discontinuity right here. It has nothing to do with 1 year or anything like that. It has to do, and that's when we moved to our new office. We built a real production facility for these things. People think that this is easy. People think building like high-end hardware like this is easy. Go buy an Owl Cam and you'll see that it has a crappy little screen and it's in this like overly dense plastic. It doesn't look like a sexy piece of modern consumer electronics. And it's because it's hard. Right? For however good you might think our software is or however bad you might think our software is, our hardware is pretty much the same. Right? Same processes, same ways of thinking about things. But we've put tons of effort into making this a lot better. So you can see the failure rates of modern Comma 3s are a lot closer to 5% than they are to 9%. And we are going to do even better. We dropped the price $500 in January. You can see we 2x'd our sales, which is nice. We do need a bit of growth. So you don't want too much growth, right? We don't need to reach the whole world. This isn't for the whole world. But we do want to make a product that is a bit more mass market. It's quite a bit more mass market. So where do we go from here? Refinement. The Comma 3 is great, but what do we do to refine it? Introducing the Comma 3X. So it looks pretty much the same from the front. See the IR LEDs are a little different. The case is so much better on the 3X. Like when we did the 3, it was the first thing we injection molded, and it was bad. Shiny black plastic. You know, Igor's in the garage trying to sandblast these things in our old office. Oh, come on, like they look bad, we gotta make it. It's stunning this time. And you see the down curves there? The road cameras are on the board. We'll get to some pictures of the board in a minute. I check time. Counter somewhere? 3X specs. Okay, Comma 3X. It's the same 845 platform and camera arrangement as the 3. So what this means is your 3 will not become obsolete. The 3 and the 3X are in the same cohort, meaning like the software is very close to interchangeable between them, more similar to how like the Eon and the Eon Gold were in the same cohort. Right? Like everything about the Eon and the Eon Gold were similar enough that we could keep the software supported at the same time. So the 3 and the 3X have pretty much the same support window. Again, no promises on this, but yeah. We upgraded the cameras, 3 OX OmniVision sensors. These sensors are a newer generation. They have 20 more dB of HDR. They have a faster rolling shutter. They can operate at real 60 FPS if we wanted them to. Yeah. Some of the late model Comma 3s have this too. So if you bought a Comma 3 in the last couple months, you have that. 128 gigabytes of storage versus 64 gigabytes. So I put that star there because we're going to start measuring our gigabytes the same way phones do. Some is taken up by the operating system and the software, but the real flash on the device is 128 gigabytes. So double the storage. CanFD integrated. Yeah. I know this is the one people were waiting for. This is the one people were asking about in Discord. So it has an integrated Red Panda. Same OLED, same spec OLED. In the last 5 years, the Chinese got good at making OLEDs, which is great. So the Comma 3 used a Samsung OLED. It was really hard to get. The supplier was, for anyone who had a screen problem with the Comma 3, they weren't all, I don't even think all the panels were new. Some of the wrinkled ribbon cables came wrinkly, and we did a lot of filtering on them, and it cost us a lot of money. Now we have a new supplier of the panels. We put in an order for a lot of them. And when you put in orders for lots of stuff, you get quality. So yeah, all new panels, Same OLED, looks great. Onboard road cameras versus flaky ribbon cables. If any of you guys saw a camera CRC error or camera malfunction, the cameras are on the board now. And actually, the CRC errors weren't even caused by the ribbon cables. They were caused by bad assembly procedures, which we fixed. And if we have time, I can go into more details on that. Stereo in-case sound. If you guys saw the Hubble Sphere video when the Comet 3 came out playing those sounds, it was bad. Those mono speakers, it wasn't well coupled to the case. Now we designed something with 2 speakers that are like coupled to the case. It uses gaskets. It's nice. The sound is good. Upgraded power architecture. How many of you had to wait for like supercaps to flakily drain on the 3? They would like kind of half drain. It's because the supercaps were connected directly to the power rail. Now we have a boost regulator in between the supercaps and the power rail, which lets us get more capacity out of them and never has this weird thing where you're putting 7 volts into the comma. Yeah. And about half the components. It's a lot more reliable. Let's take a look at the board. This is the front. The front looks pretty similar to the 3. A few things to note. No more GPS connector because it's using the GPS that's built into the Quectel. Those little antennas are actually better than the big antennas on the 3. You can see the pads for the speakers. You can see those connectors up in the corner. Oh, laser pointer. This is not a laser pointer. This is a laser pointer? Yeah. So you can see these connectors up here. They're the Wi-Fi antennas on the board. Yeah, these LTE antennas are smaller and better. Those are where the supercaps go. They weren't soldered in for this picture. Same 2 microphones. Fan, the GPS is using from the Quectel. We managed to get raw GPS out of the Quectel. The quality is the same. I mean, it's limited to the antenna. Yeah, same SOM. Where things really get good is on the back. I don't know if you've seen a picture of the Comet 3 back of the circuit board. I will show one in the next slide. Here you have the Red Panda integrated in this tiny little chiplet. Screen connects here, power stuff all underneath here to reduce noise. GPS is, actually the GPS is better in this one than the last one. I think we got like 2 dB of noise lower by shielding things and just doing a better job with the power architecture. Battery, you guys don't care about this, but it slides in and out, so we don't have to hand solder it. We have, to support CAN FD, we have chokes on all the CAN lines. You know, like, I paid $3 for this, so I hope someone appreciates it. These are the Wi-Fi antennas. We got a SIM card. We tried with eSIM. Adeeb will talk to you about eSIMs if you want to know why we don't have eSIMs. But and then I guess the main thing I really missed here is that the cameras are right on the board. So the cameras are just on the board. And part of the reason we can do this, and almost no one does this, cell phones don't do this, is because we have a lens focusing line in-house. Right? We can put the cameras on the board and focus the lenses, and we don't have to do modules. Right? Less ribbon cables, less noise, more reliability. Right? This is how you make things really, really good. I want the reliability. I want the failure rate of this device to be like 1 or 2%, and by the end, I think we're going to get there. So this is the Comet 3 board compared to the 3X. Right? Which one of these do you think is going to break? Right? Yeah. This is actually from, I couldn't find this picture. This is a screenshot of the last YouTube, so it's extra bad quality. We got rid of the NVMe. It just uses the onboard flash now. Again, it's enough. If you want more by Prime, we store it for you in the cloud, or you can set up your own cloud server if you want to do that, whatever. QR codes on the board. We like track everything through this manufacturing line. It even looks reliable. Is it a dev kit? I guess on my latent space, like the guys were like, comma didn't ship anything because of some like spat with the government or something, and I'm like, this is like, what year is it? Like, we've had plenty of interactions with NISTA since. They were fine. Like we report our accidents to NISTA, like it's fine. It had nothing to do with that. The only reason we called it a dev kit was to kind of set expectations. I mean, I don't know. I think it's probably time we stop using that word. So it's just the comma 3x. It's mass market. I'm going to sell a lot of these. I think this is it. I mean, I think this is the one, right? Like, it's not, well, I guess you haven't gotten to really why it's mass market yet. That's on the next slide. All right, so the comma 2 is 1099. With inflation, so what should we price it at? $3, $3.50, $12.50. No additions, just $12.50. You know, something I realized doing this is what, my 7th of these now, is that you always get so caught up in your head with all these, like, oh, we're going to name it the panda, the pigeon, the giraffe. Oh, man, there's additions. Why does the storage matter? Does the 1 terabyte drive better? What does cross-country mean? You know what? Guys, hopefully you'll read the questions document. There's a great document about questions. I hate questions. I hate when people ask. No, you guys can ask questions. It's cool. You guys paid to be here. You pay, you can ask questions. No, but like people ask questions. And you know how you get rid of questions? You just like, well, what does the 1 addition do? Said no one ever, right? If you give them 3 additions, they'll think they have like a choice, right? And it's not even like worth it. Like it's just like, it's $12.50. You can buy it. And I called it 3 stories because there's a line in house is 3 stories. You know how you know this one's good? Because the last one was good. It's just the comma 3, but better. Everything about it is better, and it's cheaper. So when can you get one? Order right now. Ships in 1 to 2 weeks, 1 to 8 weeks, 1 to 8 weeks, 1 to 8 weeks, 8. Depending on when you order. If you order right now, you get the 1. If you order on Tuesday, you get the 4. If you order on next Wednesday after, like way after the Tuesday, you get the 8. So, you know, order now. We have a pool in the office, and I want to win, so I bet a high number. So, you know, no, they're really good. This is the 3X in an EV6. No more red panda, no more 2 harnesses. Just buy the little thing, stick it on the, you know. You just look. We're not on the 13th generation yet. But if you handed an iPhone 13 to somebody in like 2007, like when did the iPhones get good? You know, what generation, around what number iPhone did they start getting like, wow, okay, this is just actually, what? 4, 5. 4, 5, by the way, is not the 4th or 5th. You know, they did 3, 3GS, 4, 4S. I hope we're kind of there, right? I hope we're kind of at the point where like, this one's good. Yeah. That's my presentation. I also want to, you know, I didn't build this. I didn't build the software. I didn't build these models. I didn't build the hardware. The team did. And you can be one of those team. Apply for a job, too. Apply for a job by Comma 3X. You know, it's a calls to action. Right? Look. You know what? Judge the team after buying a device and driving with it.
That's fair.
If it's good, I didn't do it. If it's bad, I did it. So.
The Comma 3X is live on comma.ai.
Oh.
And now we're going to take some questions.
Hello, thank you for presentation and congratulations with 3X. Do you see any value to run language models right on device?
Why do you want to run a language model?
like interaction with environment, with driver?
Yeah, sure. Check it out. It runs TinyGrad. It's pretty good. I don't know. Our mission is to solve self-driving cars while delivering shippable intermediaries. Maybe solve robotics while delivering shippable intermediaries. If language models help us do that, we'll do it. Otherwise, I don't see a reason to. But yeah, no, I think you can totally get like llamas and stuff to run. Maybe not 7B, but like little llamas.
Great presentation. I'm not a developer. I'm actually a marketing guy, so technically I'm a professional liar.
I mean, wait. Would you disagree with that characterization?
No. This is what we do.
Nothing personal, I mean.
So I got some just silly questions here. So have you done any testing or planning to do any testing on commercial vehicles like 18-wheelers and things like that?
I don't understand. Why? Why? We've done a lot of testing. This is the best tested comma device by far. How many people we get in Epot? Whole bunch of people have been driving around with these. We've made like 82 of them. This is the best tested one by far. The amount of, I mean, we control so much of the stack now too. You'll hear about this in our next talk, but like we built out a manufacturing line and we tested them well. Have I done any testing in 18-wheelers? I don't have an 18-wheeler. I have a motorcycle license. I don't have a CDL. Tesla partnered with Pepsi? Who's making money off this? Who's this delivering value to? Like, I don't get it. Is this like this is not self-driving. What do you mean? You got a driver in the seat. This just sounds expensive.
Sorry, just one more question. So, marketing is branding and telling a good story. Jobs sold good stories. Elon sold good stories until he bought Twitter. So, other than honesty, what is the story about openpilot that the common person, not developers, need to know about or want to be part of?
I mean, and this is what I mean about kind of the lying. And again, like where I'm attacking this is like, what is openpilot? Well, openpilot is a open source ADAS system. What is the Comet 3X? It's hardware that's capable of running openpilot. So you ask the question, what does the user need to know? Just those two things. And you can buy them in our store for $12.50. Right? If there's anything that's like the narrative, I mean, it's exactly what I said. It's like, you see, here, I'll show you the narrative. I'll show you the narrative in 2 words. Buy now. And you know what? If you don't like it, here's another part of the narrative. 30-day money-back guarantee. Buy it. Try it. Ships in 1 to 8 weeks.
Hey George, talk to us about how the Comma 3X will always be compatible with the cars we drive, and that the cars we drive won't somehow disable the use of the Comma 3X.
Don't let Sam Altman scan your eyeballs, okay? As long as you don't do that, I think you'll be good. I don't know, what are they gonna do? They're gonna update the car? This has never happened like before. Maybe they're gonna, I don't think so. I don't know, I can't promise you that. I don't know, man. Probably not, I've never seen it happen. You know what I mean?
Hey there, I was one of your hackathon contestants, looking for my next hackathon project. I was curious, is it possible for a Comma 3 to port a new model to a Comma 3?
It's pretty easy. I mean, it's TinyGrad now, so you don't have to deal with SMPE. You can just, the Onyx support is pretty complete in TinyGrad. Yeah, you can run whatever you want. Is it possible? Sure. It doesn't say dev kit anymore, but it's still a dev kit. Shh. No, it's not a dev kit. Don't worry, buy it. If you're worried about that word, I don't know, man. Yeah, but no, you can totally run other models on it. It's not that hard. I don't know, like, again, like, are we going to do it? No, but you can do it. I mean, I think we ran some. I think we got like a YOLO running for the body demo or something. Yeah, runs at 20 FPS. Runs at 20 FPS. We got YOLO running at 20 FPS. We can put boxes around things, right? We love boxes.
Okay, you're talking a lot about mass market, right? So, yeah. But I only have a C2, so forgive me if this doesn't work this way on C3, but like, you get the device, you turn it on, you still have to like download the software, right?
Have you ever bought like a PS4 and had to sit there while it updates for an hour? It's faster than that, don't worry.
Well, so the question is
the like, PS4 mass market?
But basically, this is like a tiny liability air gap, right? How do you feel like this liability like is going to be serving you in the future? Like that
Who said anything about liability? It's custom software. I explained to you what it was. It has nothing to do with liability and everything to do with the fact that our models are RLHF'd, right? And if it's RLHF, that's a policy model. That's custom software. The foundation models will come on the device, right? The foundation models, TinyGrad, Agnos, that comes on the device, right? That's what the device is. The software, the policy model that sits on top of it, that's custom software.
So in general, liability, you're not concerned? As far as like future...
What do you mean liability?
NHTSA stuff, like any of that?
I mean liability. I mean, pay attention at all times. It's level 2.
Well,
like
the one comment I'd say is like level 3 being shipped today.
I'm not shipping level 3.
I know.
Level 2. We ship level 2. Pay attention.
Mercedes-Benz has come
and I'm
out
not
and said,
joking,
like,
by the way.
We will cover the liability if our car
I'm not
crashes.
covering shit. Look. Look. If you want to not pay attention, do not buy our product. You must pay attention at all times. This is not a joke. This is not tongue-in-cheek. You must pay attention at all times. We put a lot of effort into making sure you pay attention at all times. Every accident I've ever seen with the comma device, no one's died, no one's gotten seriously injured. But I've seen a few accidents, and every single one of them would have been prevented if people were paying attention. Pay attention. This is not a joke. This is not tongue-in-cheek. Pay attention or don't buy the device. That said, if you want to pay attention, it's a great device.
Yeah. Hi, great presentation. And now we saw a large foundation model work pretty well. Do you think in the future or near future, the only very powerful hardware can power self-driving car, something like that?
Yeah, so it's a question. So the Comma 3 and the Comma 3X have an expansion port. They have a USB-C expansion port that can do full USB-C bandwidth. So we are capable of streaming out the full sensorium of the device. If it does turn out, we do need to run larger models, which we haven't seen better results with yet. Our recommendation is going to be buy a gaming laptop, connect the gaming laptop, and put it under a seat. No, and I mean it, because it's actually really hard to buy. NVIDIA's not going to sell you RTX 3060s. But you can go on Amazon, and for $8.99, you can buy an MSI plastic crap gaming laptop, stick it under a seat, and it'll run the model. And actually, I think we can make the experience with this quite good, because if it loses connection to the laptop, it can fall back to the model on device. So with a lot of these things, yes, more compute helps, but model, like, you can do all sorts of things with your student-teacher models to make it smaller. But are we going to need more compute in the future? Of course we are. Do we need more? Will more compute make the comma device drive better right now? No. Yeah. Also, the other question is, do you have to? Can you do like student-teacher to put a small model on the device that captures the policy really well? That's kind of where we're going right now. You'll hear more about this in our next talk. We're now training a driving simulator, and this is using like an autoencoder to compress the video, and this is a big model. So we're training a big foundation model, but we may not necessarily need to ship that to the device, because what we need to ship to the device is a policy model. But we have pathways. I don't know the exact answer. Are we going to need more compute than what's on a Comma 3? Yes. Are we going to need it in the next 2 years? Unclear. Probably not.
Thanks. We've got a question upstairs.
Hey George. Thanks. Nice presentation. A few notes there. First, if you look at those failure rates over time, I think there is like a spike if you look at it in like summer times, so which suggests that you know, they might be failing a little bit more in the summer.
That isn't when the devices fail. That's when the device was built when it failed, right? Those failure rates are not. That's not the month the device failed. That's like when the device.
But anyways,
was
there
built.
is some curious like time dependence that you might look at. But my main question is not about that actually. It's a little bit to reiterate on. I really like the effort you guys put into reliability of 3X, and I think it should be actually built even more reliable than like your normal car, because like if you look at like human brain, it's built like with all like sorts of protections around, and that should be probably should Comma strive it. Like it should like really build like a tank, so even in the event of collision, it can record stuff in like you know, like the last 50
Well, so
milliseconds.
the common device is not a safety device. It's not really we don't.
No, but just.
We don't use the word dash cam anymore,
forward.
right? Like our goal, again, we're a small company, and like I said, a lot of what my job is now is saying no to things, right? This is one of the last things I still do from the company. Like, can we build all these fancy features? No, we're not Tesla. Right? What we are trying to do is build the best possible highway and highway plus driving experience. And you can go on Reddit right now and see people comparing autopilot to openpilot. You go back 3 years, people would say they were similar. Now, almost all of them are like, look, it's cool what FSD and autopilot are doing, but day to day, openpilot is hands down better. It was just a post on the ComAI subreddit where some guy's talking about he has 2 bolts, one with Super Cruise and one without. Yeah, night and day. This is by far the best ADAS system you can buy, and that's what we're focused on doing, right? We start focusing on other things, the ADAS system gets worse, right? It's really easy to say yes to things, but it turns out it's saying no that makes things really great.
Who has 2 bolts?
Some guy on Reddit, I don't know, man. I had an English teacher and he had 2 Nissan Cubes. It's like, that's my dad's. I'm like, the car changed color. He's like, no, that's my dad's Nissan Cube. And I'm like, okay, why you'd buy 1 Nissan Cube, you know?
All right. Cube? Thanks to all the people who bought Comma 3Xs already. We're blowing up, George. Your high number, make it hit.
Yes, 555 in the first week's what I'm going for.
Up there. Thank you.
Look, this is the first Comma device that I would recommend to like my friends. I'd be like, this one's actually. What if I told my friends to buy an Eon and a giraffe and a panda? Like, all right. You know what I'm saying. They were all good, but some are better than others. This one's good. Thanks, everyone.
All right, so you learned about the 3X. Very excited. I can finally stop holding that secret in because I'm absolutely terrible at keeping secrets. So you saw we have a new device. Now you're going to see how we built it. Robbe, the genius behind the 3X, is going to show you our production. Are people into it? This is a serious question.
I hope so.
I just love talking about it, but I don't want to bore you guys.
Oh, is it the slideshow thing with the presentation? For example,
This is a perfect time to pull up your phone and go to comma.ai.
Oh, and buy one?
And buy a 3X.
This?
Oh, and then maybe drag that over there.
Yeah. There we go.
All right. Please give it up for Robbe.
Hi. Good afternoon. I'm Robbe. I'm part of the hardware team here at Comma, and today we're going to talk about how the device is built. So, first of all, I think a lot of people, when they think of Comma, they think of an AI company. Like, we do a lot of research. A lot of our people are working on software, on machine learning. But fundamentally, Comma is also a consumer electronics company. Like, I mean, we launched a new product. This is what funds our development. So this is a pretty important part of what we do. It's also not like we're selling like simple electronics. Like, we're selling electronics that's somewhat comparable to like a modern smartphone. Like, if you think about it, we have a high quality screen. We have high quality cameras. We have a bunch of compute to run the machine learning models. We have connectivity. We have network connectivity. We have LTE. We have Wi-Fi. So yeah, it's not a simple product to build. So we started out a few years ago with the Eon. Eon was a pretty simple product to build. I mean, we basically we didn't really care about all the advanced features. We bought a smartphone, like all the advanced features already in a box. We slapped the heatsink on it to manage the thermals, put it in a 3D printed case. Yeah, it's easy to produce, it's simple, it works, but I mean, it's not really a consumer electronics product, right? After that, I think it's about 4 years ago now, we launched the Comma 2. This is basically a refinement of the Eon product, so that the most advanced features like compute, sensors are still inside the metal box, so we didn't have to care about that. But we integrated the electronics that talk to the car into the case. We refactored the way that we connect to the car so we can support more cars. And things got a little bit more complex. Like we started to have to build more procedures in-house to like make sure that the changes we made were tested well, that the production processes were good. But then, 2 years ago, we launched the Comma 3. It was a pretty big step. George always talks about the fact that the Comma 3 is the hardest product that we'll ever have to build. And I do believe that that's true for a few reasons. For one, like all the sensors, all the display, the compute, the electronics, they're all custom built in-house, they're designed in-house. This is something that we'd never really done before on this scale. So it took a lot of engineering effort, a lot of time improving all the processes to get this to build. Not only to design all the individual customized components, but also to integrate them nicely into one like little box that looks nice, that functions well, that is a form factor that people actually want to use. So that's what we did back then. Then this year, like we've obviously launched the 3X that George talked extensively about already, which is just a refinement of the 3 with kind of D added. So we're already on the downslope in terms of complexity. So in the future, I think we can go even a step further. Once we get to larger numbers of devices sold, we can actually start talking to manufacturers to also get the modules that we still use to do connectivity. Like we still use the Quectel module for LTE. We still use a system module, as we refer to it, a SOM, for the compute. But we can start integrating that all into a nice device, and then we end up back to something that looks more like a smartphone. Again, like if we get to those numbers, we actually can customize these individual components more so that the integration will also be easier. So I think it'll only get easier from here. So how do we do it now? So there's actually quite a lot involved in the whole process. So to give you a sense of that, I've made up this little nice design of like the basic life cycle of a product within Comma. I don't think it's too dissimilar to other hardware companies, but it's good to go over it anyways. So we start with a concept. So we basically think about like what the form factor will look like, what features we want to have. Once we've got that nailed down, then we go over to a design step where we design all the electronics, all the custom parts, the mechanical parts, the case. Then we get prototypes built. Then we get them tested. If they're not good, then we go back to step number 2. Usually we iterate like 6-7 times before we get a prototype that's ready for manufacturing. Then we actually can put it into production. And after that, we can ship it out to customers. Now, if it would stop there, that would be nice, but we live in the real world, so we'll also get warranty returns. For the 3X, compared to the 3, getting the concept down was a lot easier. We basically have the exact same features except for the addition of CAN-FD. We still have the same kind of form factor. A lot of the components stayed in relatively the same position, so that part wasn't actually too hard. I actually found a picture of the whiteboard where we sat down and wrote down all the changes we wanted to make. And you notice there's a lot of times we mention the word no in the feature list. So we removed the PCIe lanes because we don't have the NVMe drive anymore. Removed the 3.3 power rail, so that made the power architecture easier. We removed the external siren. Like we used the speakers we already had in the device to do the siren part. We removed the USB hub because the Panda now talks over SPI to the main device. So we removed a lot of stuff. And as Elon always says, no part is the best part. So that's the general goal here. So once we know what we're building, then we get to the design phase. So the biggest part of the design, I would say, is the electronics part, so the main board, which starts out as the schematic on the left. So that's basically where we do all the, like we select all the parts that will make up the whole design. We get them to work all together, like we think of all the edge cases the device might be in, like when you shut it down after a while, like the power draw needs to be low, like that kind of stuff all gets integrated and thought of when we do the schematic design. After we're happy that and we think that we made all the changes that we needed to make in the schematic, then we move over to the board layout. This is actually a picture of the PCB layout of the Gamma 3. So you can see it's relatively complex. So this is the part where we place all the components down in a sensible location to make it fit in the form factor. We design the outline of the board, and then we connect all the components together with traces on like 6 copper layers to get all the requirements that we want. This is actually a pretty manual step still, because there haven't been very good software packages out there that can do this automatically, even though you might think that it's not that hard. Like you just connect stuff up together that needs to be connected up. But turns out there's a lot of design requirements that you need to think about. For example, all the high-speed traces that carry a lot of the data from like the cameras to the compute, they need to be impedance matched. They need to be on layers and far enough apart from other stuff that they don't have crosstalk with different lanes. You want them to not have any electromagnetic interference. You don't want to emit any RF noise that you're not allowed to, because that might also degrade GPS or other devices in the neighborhood. But it's actually quite complex. So this process, like if you start from scratch, it probably takes 1.5 to 2 months to get it down. And then future revisions are obviously easier because most of the stuff stays the same. So let's talk a little bit more about the part selection, because in the recent years that has proved to become more difficult because of all the shortages going on. And not only that, but there's also the thing where there are multiple parts on the market with a similar functionality. So getting an optimal design where you can actually mix and match parts to get the same features, it's pretty important. So how do we internally keep track of all like the substitutes that work together, of all the inventory that we have for production, like what components other designs use so we can reuse the same components? Well, we don't always need to reinvent the wheel. So we actually found this software called PartsBox. It's made by a Polish company. There's just one guy who writes this in his spare time. It's actually really cool. It introduced us to the concept of a customer part number, or CPN. I sometimes also think of it as a comma part number. But, so this is basically a part number that's not like an actual physical part. So that basically just specifies the requirements that we want for that part to be. So we just say, okay, we want like a 100 kilo ohm resistor. That's the one I showed now. In an 0402 package, that's like a relatively standard component. And there's dozens of manufacturers that can make parts that fits these specifications. So that's the parts you see on the bottom. So that's the parts that we can actually buy and that we approve to be like a suitable part for the CPN. And we can then order them to make sure that we have enough for production runs. The other cool thing that PartsBox has is API access. So we also do a lot of CI on our hardware designs, so we can automatically pull from our inventory numbers and that kind of stuff. And I'll go into depth a little bit more in the next slides. So this is a commit that I made to the hardware repo in the last month. Finishes rounding of one of the camera boards. Nothing too interesting, but this shows us like all the steps that are run automatically every time we make a change. So the first thing we have is it checks the CPNs. So it goes over the design that you just pushed and it makes sure that every part in the design actually has a CPN like allocated to it. So we don't push designs where we don't specify like what a part actually is, because that makes it harder for production. Like you have to go back and forth and like asking, oh, which part it is. So that's automatically checked that that's all filled out. Then the next step is one we added because on one of our earlier prototypes, we made the mistake of putting a capacitor with a lower voltage rating on a power supply line that was slightly higher voltage. So like in a few weeks, we would see failures with this. So now we actually have a check that goes over every capacitor in all of our designs and checks that the ratings are actually good enough for the use case we use it for. The third step is a fiducials check. For people who don't know what a fiducial is, so that it looks like this. It's a little dot that you put on a PCB. It doesn't have any function in the end product, but it's very useful in production because that tells the machine like where the board is actually located in the machine, so it can more accurately calculate where it needs to place the components. We tended to make the mistake sometimes where we would order boards without placing fiducials on them, and then we would get them into the manufacturing line. It would be a huge hassle to get prototypes out of them. So now we add an extra check. So every time we have a design, it at least has 3 fiducials on every board. Next one, generate GenCat files. So that's the file format that the machines use, so we don't have to manually make that every time we make a new revision. Then we also generate board diff images. So for every commit, it tells you where the copper was added, where it was removed, so we can easily like go back and see which commit actually changed which, what part of the design. Because I mean, the files look like XML code, so you can't really see what's going on with the actual design on GitHub. So this is a pretty nice sanity check to make sure that you actually committed what you wanted to commit. Then we have generating schematic PDFs, because not everybody has the CAD package installed on their machine, so we just generate PDFs from all the designs, so we can just pull the latest schematic as a reference anytime. We back up some stuff. That's an automated thing. And then recently we've also added the new parts bot. So every time we now push a revision to a design, it checks and it accesses the parts box API I just talked about, and it checks that all the components we have on the design are actually in stock, like locally. And if they aren't, then we just generate a message on Slack saying, hey, please buy these components when the PCBs arrive, and we actually have all the components to build them. Except for the electrical designs, we also have the mechanical designs, obviously. So we do the injection molded case. We do also all sorts of like holders for GPS antennas, for the T-cams, the mounting plates you see on the right. I don't go into too much detail there, because that's not usually what I do. That's Igor in the back there. But we generate these machine drawings that we can send off to the manufacturers. We do some simulation tests to make sure that all the things stay within the limits that we want them to be, etc. Cool, so we're done with the design. We get bare prototype PCBs. This one's blue. You've noticed in George's talk that the PCB was black. That's one of the ways we make it easy internally to track like which thing is a prototype, which one is a production device. Also, we tend to change the color of the PCB every revision we do. So if you have like 3-4 revisions on your desk, like you can easily check like, okay, this is a Rev B, this is Rev C. It's been quite helpful. So now we have blank PCBs. Obviously, they need components. So what do we do now? Well, some people have already talked about our internal production line that we set up a few months ago. So that's the part that will actually put the parts onto the PCB. The main advantages we've seen from bringing this production in-house, because people ask us, like, why do you bring it in-house? You can just pay somebody else to do it and don't have to care about any of this stuff. Well, it's 2 things. So first of all, it drastically reduces the cycle time. So with our old manufacturer, it would take like between 6 and 8 weeks to get a new revision. And you'd only get like 2 boards, and it's a whole back and forth. And second of all, it's way easier to fix issues. Like for example, we get a board made on our line. Somebody placed a component like 90 degrees rotated. We just literally walk downstairs, change the value in the machine, you walk back up, and an hour later you have a new revision on your desk with the required fixes. With the old company, it would be an email chain of 3 days, and then we might get it right. Okay, first machine. So the board goes into the machine, and that machine applies the solder paste. So to stick components down to your board, you need some solder paste that melts in the oven to create the solder bonds. Most mass manufacturing manufacturers, they use a stencil-based machine. So you get these stainless steel-based stencils with holes cut in them, and you have a big squeegee that just squeegees down your solder paste. It's very nice, it's very fast, so it only takes like a second or two to paste the PCB. The problem is it's very hard to iterate with. Like if you make a new change, you have to make a new stencil, you have to reload the stencil in the PCB every time you change the designs out. So that adds a bunch of time with switching designs and making new revisions. This one just has a tube with some solder paste in it, and it just dispenses tiny little dots on the pads, and it's just CNC controlled, so we can just put any design in it, and it works. It's also, the cycle time is not very important in this step, because the whole production line is pipelined. So even if, as long as this takes less time than it takes to populate the board, this won't hold down the total production rate that we can achieve. So there's actually not that many downsides to doing it this way. Next machine, pick and place machine. So the pick and place machine is loaded up with a bunch of reels of components, and it does exactly what the name suggests it does. It has nozzles, picks them up from the reels, places them down on the board. Our machine also has an extra cool feature that I really like. It does electrical testing as well of every component, of every passive component. So for example, if it picks up a 100K resistor, usually these parts have tolerances because we live in the real world. It'll place them down on the test board, it'll measure the exact value, log it to a database somewhere, like related to the serial number of a board that's in there, so we can, in the future, always look back and see exactly which value resistor was placed in there. It's pretty cool. Next up in the line, the oven. Pretty straightforward. So you just put the board in, moves over a conveyor, it gets hot, solder melts. That's pretty much it. You'd think. But then there's a lot of tweaking in the oven. So the oven has about 8 zones. They can all be set at a different temperature. And then the conveyor belt speed can also be modified. And it's a balancing act between like multiple parameters that you need to tune. For example, in the first 5 zones on this, this slide, you'll see that the temperature slowly moves up. And that's to give the flux contents that's inside the solder paste some time to clean off the oxidation of the pads, which makes it way more likely to get a good solder bond. Then it moves into zone 6 and 7, where the temperature rises up quickly to above the melting point of the solder balls that are in the solder paste. The bond gets formed, and then there's a controlled cool down in the next 2 or 3 zones to make sure that everything settles down nicely. A lot of the components that we use actually have limitations on, for example, the temperature rate, the temperature gradient that they can sustain. So for example, the image sensors, I think you have to heat up less than 3 Celsius a second and cool down less than 6 Celsius a second. And that's also something that you have to keep in mind when tweaking all these solder zones. Next up in the line, we technically have a functioning board if everything went well. The problem is we don't know if everything went well. Like what if somebody like bumped the PCB, some components moved, or we loaded the wrong part into the machine, or it failed to pick up a part and didn't notice. Well, that's why we have automated optical inspection. So it's that machine. It's basically a fancy camera with a bunch of lights that can move. Just flies over the board and checks out every component and makes sure that it matches a reference picture from a known good board. So this is especially useful in production, where if you're running like thousands of boards, you know that every board actually has all the components and it doesn't have any failures that would be easy to detect this way. There's another benefit of having the machines in-house is that we can do a lot of vertical integration with them. So we talked about Parts Box having an API. Well, the machines also have an API. So this is some software we wrote in-house to program the machines. Because if you're a contract manufacturer, you usually get like an Excel sheet of all like the parts and the mounts positions that the parts need to be placed at. Then somebody has to like sit there and manually enter like the hundreds of components that are on the design. Select from which CPN, like which MPN is actually in stock, which one's on the machine, which one is not. Well, I mean, we've built a software. It queries Parts Box, so to check which components we actually have in inventory. It checks which parts are actually already loaded on the machine. So if you have multiple accepted MPNs for a CPN, it can like prioritize the ones that are already loaded. And then we just throw in like the CAD file that we have. It automatically generates all of this. It's literally a 5-minute process, and we have programmed all the machines. So we have built prototype devices. Does everything work? Well, To verify that everything works, you need test plans. So we have very extensive unit tests for every single feature that we want out of the device. So this functionally tests that everything works that's on the board, like you expected it to work based on the design. It also checks for extreme environments. So we do a lot of tests in like thermal chambers to make sure that it goes up to that everything still works at the temperature that it might reach up in the car. It goes down to a certain temperature. It also does some minor stress testing where we like inject voltage transients into certain lines to make sure that the protection circuits we've built in work. We make sure that if you plug in a wrong cable into the wrong hole, nothing breaks. Like all that stuff is validated before we move on. Then if we think that's all good, then we have some more compliance tests. So those are actually mandatory if you want to sell consumer electronics. You have to bring it to like a certified test lab and then make sure that A, you're not intentionally radiating any RF noise on frequencies that you're not allowed to radiate on. And then there's the second part of the tests, which makes sure that the modules you've integrated that actually want to transmit don't transmit at a power level that's too high or that they don't create any intermodular effects. And then there's a third step. We do field testing. So we first put them in all our cars. So we have 12 cars in our fleet. It covers most of the platforms we support, but then there's some other ones that the community only has. So that's why we do the Apple program. So we have some few members here, I think. You guys here? Yes. And that's actually proven to be very successful. So in this round of Apple testing for the 3X, we've actually found 2 bugs. One of the bugs was a software bug with the new Panda that's integrated on the board. It was used in slightly different ways than the Red Panda was in the past, so we fixed some bug related to CanFD. But there's also a hardware bug that was discovered that we didn't discover with all the test plans we've previously done, which was with Jason's third-party long cables. VW users do all this weird stuff with their cars, I don't know. So yeah, we always use the official cables because they're laying around in the office. So it's good to get some coverage from the community as well. So once that's done and we're happy with it, it moves on to production. So we now buy all the parts in bulk. We select the cheapest components. We make sure we have everything in stock. And then we get the PCBs built in black, like mentioned before. We apply the QR code stickers. Actually, a data matrix, not a QR code. But same thing. So this adds a unique serial number to each board, such that we can later on, if it comes back with a hardware failure, we can double check that the oven was set at the right temperature when it was run, that all the electrical components measured their respective values. We can check the AOI images, like to see if that missed anything that it shouldn't have. So that's a pretty nice addition. Then, when it runs through the whole circuit spoke line, the exact same as the prototypes. So then we have assembled boards, and then we move on to all our provisioning steps. So first of all, we have initial provisioning. So this is a step we've added for the 3X. And it basically takes the bare boards that came straight off the line. We just put on the lens holders, the lenses in them, puts them in this nice jig, and it does a bunch of very preliminary tests. So it checks that all the voltage rails are in tolerance. It checks that we can talk to most of the components. It does an initial flashing round of the internal Panda. And then it has the focusing step. So it's very important that the lenses that we place on the devices are perfectly in focus, because it's fixed focus, so we can't change it in the future. And it would be a hardware return if they're not. So we made this UI thingy where you just turn the lenses, you try to get the green line to go as high as possible, and then we know that the devices are in focus. Now, obviously, on the bare boards, we haven't placed the SOM or the compute module on the board yet, so we needed to design something else for that. So we designed what we call a fake SOM, which is basically a separate module in the same form factor as a SOM. But that can be powered externally, so we can just keep it alive when switching between boards. This makes sure that we don't have to reboot Linux every time. before we run tests, so that increases cycle times. Plus it has like the voltage testing stuff built in and all that nice stuff. Then the next step is we build them out into full devices. So the heat sinks get placed on, the DCAM gets placed on, the GPS gets placed on, that they get put into the cases, the screen gets placed on. That's quite a lot of steps. In the case, we also add an NFC tag, and you'll see where that's useful for later. After they've been built into their final form, they move on to what we call final provisioning. This is a wooden rack we have set up in our production environment with some mounts. So they get connected up there, and then we run through like a full suite of hardware tests. So we make sure that every piece of hardware that's on the device, like the IMUs, the GPS, the Wi-Fi, the screen, all that stuff, that's all tested. So we make sure that we know that everything works before we ship it out to customers. This is also a place where, like, from time to time, new tests get added because we've seen failures from the field. For example, a few weeks ago, we had some returns of display panels where, like, the touch wouldn't work in like a certain area of the screen. So we just added a test where we just like wipe the whole screen, so we make sure that the whole screen works. And so that's like the procedure we follow to reduce failures more and more as time goes on. After that, we move on to the stress test. So that's another bigger wooden rack. This is only a small portion of it, where the devices are placed on for a 24-hour cycle test. So on this test, we put them under high synthetic loads. So we just max out the CPU usage, max out GPU usage, DSP usage. We run the cameras at full speed, run the fans at full speed, just to make sure that the devices actually stay working for like a reasonable amount of time, because sometimes like stuff works, but then like it heats up and then stops working. So that's the kind of failures we try to catch here. This is also the place where we do some longer running tests. Like we make sure that the GPS signal doesn't drop for 24 hours. We make sure that if we toggle the fan on and off once in a while, that it starts back up. We make sure that the camera doesn't drop any frames during the whole 24 hours. And those things have really reduced the amount of failures that we see in the field. After they've gone through that, they're ready to ship. So they move over to fulfillment, where we automatically test using the NFC tag, because we know where the device has been. So we put the device on there, on our reader, and then we know if the device passed all of our tests, because that didn't always used to be the case in the old Comma 2 days in the old office. Like, the device would get misplaced, or like not all the tests would have been run, and then we would get shipped out anyways. So now we explicitly confirm this. For the Comma 3s, we had to make sure that they were the correct type. Like, if you buy a 1 terabyte one, you get a 32 gig one. People will complain. The other way around, not so much, but still not great. Domestic orders, we include a SIM card for the Comma Prime trials. International orders don't, so that's also something that's verified. This also tells you which harness the customer bought, so we place the right one in the box. It also checks that we have the latest software flashed onto the device, because if it's been sitting in storage for a while, like if we have some excess inventory, it might be on an old openpilot version, and the first clone would take a lot longer. So this is something we try to prevent. And then there's the final cosmetic inspection before the box gets shut. There's also an AOI. It's not automated optical inspection. We call it Ada optical inspection, because she's the one that does the fulfillment. So yeah. And then the hardware failures. We used to get emails all the time that said, oh, my device doesn't work anymore. And I mean, there's not much you can do about that except for ask the customer to return the device. And then in most cases, it turned out that the device was fine, but it was installed wrong, or the software didn't support that car yet, or there was some other software bug that we didn't know about yet. So we recently changed that process and made sure that when there's hardware complaints, people actually provide us with a route where the issue occurs, so that an engineer first looks into the alleged failures, and if there's actually some anomaly going on, then we get it sent back. Otherwise, we tell the customer like what's going wrong, and we don't have to do any unnecessary shipments. This has actually reduced our inbound for influx, like the inbound for the failures by close to an order of magnitude. So that's been quite good for us. But then the devices that do come back, we have to take them quite seriously, because usually there's something we can do about it. For example, one of the earlier failures of the Comma 3 had to do with the SOM stoppers failing. And it turns out that we used to use a thermal pad on top of the main CPU. And with manufacturing tolerances and thermal cycling, that would put too much pressure on top of the die, which caused some solder failures. So then we changed the procedure to go with a putty-based thermal compound, which reduced the total pressure on top of the chip by 2x. And that practically resolved the issue overnight. Another thing we can do is add additional testing, like for example the touch issue I talked about before. Like we just add another test to make sure these devices don't get shipped out in the first place. Or we actually can also improve the design, like if it's an actual design bug. We had one a while back with the Red Pandas, for example, where we didn't account for people plugging in a USB cable with 12 volts on it on a port that wasn't supposed to get 12 volts, and then it would blow out the CAN transceivers. So that's just fixed. We made a new revision. Doesn't happen anymore. And that really translates in the failure rate. So George already alluded to this, but the all-time failure rate of the Comma 3 has been at 9.2% now. It's an interesting number, but it's actually more interesting to look at what failure rate's been over the last year. So we lowered it to 3.9% already, just by improving all these processes. And to put that into a little bit of perspective, George already did some of this, but iPhone 6s, 22%, recent iPhones, 3-4%, Xboxes, 22%, PlayStation 3s, was it 10%? We're actually close to a Wii. That's pretty good hardware, apparently. But we intend to do a lot better with the 3X. I think with some more improvements and with a more reliable design, I think we can probably get it down to like 1 or 2%. So that's pretty good. So I mean, George gets to announce hardware products. Why don't we also get to announce something? That's not on there. You guys know harness boxes? A lot smaller now. They're in the final stages of testing, so they'll come out in a few months probably. Injection molded case. It will be a lot easier to fit on the covers in most cars. And another one that we're coming out with soon, the new Panda Jungle. So it's a CAN FD variant. It adds SD card support. It adds per channel eFuses, per channel SBU line control, all that stuff that has been very nice for developers, internal and hopefully external as well. So okay, I've been talking for 35 minutes now. I only have 45 minutes, so there's still a lot more that we haven't talked about. There's part shortages, there's torque control screwdrivers, there's packaging, there's injection molding, BOM optimization, cable testing, suppliers, harness production, mounting plates, through-hole soldering, display calibration, laser depanelization, pandas, comma bodies, you name it. The hardware team has a lot to do. So if you're interested, reach out to us. We can definitely use an extra hand. Or if you have more questions, then feel free to ask him now.
All right, thank you, Robbe. We got a question up here in the front.
Thank you. You talked about compliance testing. Are you planning to do only FCC, or are you looking also European one like EC and others?
We've done the FCC one now. The European one's very similar, so we'll probably be compliant with that as well.
Great.
So the harness connector is changing because you've got a smaller box there.
Yes.
So how do you make that? What's that equation like for making the trade-off? Is it time to?
Yes, so I think the old one was a 24 pin, if I'm not mistaken. The new one is a little bit smaller. I mean, we had to, because otherwise the case wouldn't be smaller. The new connectors will just come with the new harnesses, so we'll have to move over that production a little bit. But functionally, there's not that big of a difference. It doesn't have a mechanical relay anymore, by the way, so we'll get rid of the little click you hear when openpilot starts, but it'll be a lot more reliable, hopefully. So that'll be good.
You got any other questions? Oh, in the back, I'm coming.
Hi. So I was impressed by your automated testing on commits to the repo. How is it that you do the diff between the old board and the new boards?
Well, it's not super efficient computationally, but we've gotten Eagle, the cat package we use, to run inside of the CI Docker container. So we basically just spin up Eagle, open the files, generate the Gerbers, then generate PNGs from the Gerbers, and then we just do an image diff on the two images.
Sweet. And we're also looking for hardware engineers. Are there any like networking events that you know of in San Diego where we can all?
I don't really know of that many, actually, no.
The truth is that Robbe is based in Belgium.
That's also true.
So he definitely does not know about the happenings in San Diego. Oh, we got a question back here.
I'm wondering, do you have any interesting stories about weird issues that took a long time to track down and ended up having an interesting cause?
We have so many good bug stories.
We have a lot of them.
There's much bugs, Nabil.
On both the Comet 2 and the Comet 3s, we've had a lot of GPS troubles. Apparently, like the 845s, the main chips, they leak quite a bit of RF across the whole spectrum, so you have to isolate them very well to not affect GPS. On the Comet 2s, we had an issue where the GPS antenna has this internal LNA amplifier. So it amplifies the signal, but then we had an issue where it leaked out after the amplifier into the heatsink, and then got coupled back into the antenna, so then we would get like a feedback loop. That one took a long time to track down. What other ones have we got?
How about last week when a vendor sent a wrong component and mislabeled it?
Oh yeah, that's another great one. So last week we were placing inductors on the boards, on the 3Xs actually. Don't worry, we fixed it. But so we ordered 1 microhenry inductors from a reputable supplier. They came to us, we loaded them into the machine, and then Igor, the hardware guy, he needed one, so he just took one off the line. And when taking it off, we looked at the reel and it was like, hey, there's 2 labels on here. One of them says 1 microhenry, one of them says 2.2. It turns out it was the wrong part. So yeah, got to be careful even with official distributors.
So we heard George talk about custom ASICs. Where does this stand on the hardware roadmap? Have you guys thought about it at all?
I think George has some architectural plans, but I don't think that's going to be concrete anytime soon. Yeah, we're quite far off from the budgets needed to spin out ASICs.
So people frequently express concern over the thermal resiliency of the devices.
Yeah.
Can you speak about the steps that you take during production for both the C3 and now the 3X to mitigate that?
Yes. So I mean, the basic process we follow is we just test them at extreme temperatures, and then we make sure that the parts don't fail at those temperatures. We just cycle them lots of times, and then we fix the issues that arise. The second part of the thermal issues is also not necessarily for failures, but also for like user experience. For example, when it's like sitting on your windshield, when the sun's blasting on it, the device can get quite hot, and you want it to cool down as fast as possible. So you actually want to reduce the total thermal mass in the device. So yeah, there's quite a lot of consideration going on in that regard. But so far, with like all the improved soldering processes, we don't see that many thermal cycling failures anymore. So.
Hey, I'm curious about the root cause process. So, are you? So your team is manually doing that, the root cause, about different bugs or occurring hardware, or there's like automation inside of that?
Well, when we get failures back, we often just run them through the provisioning tests again. And that usually gives us, like that narrows down the component that actually failed. And then we disassemble the devices, look at them under microscopes, and then trace down what the actual issue might be. So it's mostly a manual process, but we use some of the production tests to guide it.
All right. We've got time for a few more questions.
I had a question about the GPS module in the QUTEL. How does that compare to, I think you were using a Neo M8P?
Yes.
What do you think, like, is it worse, better?
I think performance-wise it's pretty similar. I think we gotten the QUTEL into a mode where it sends us the actual raw measurements and turn off all the processing that it does inside. But the QUTEL module uses Qualcomm chips inside, and phones have pretty good GPS these days, so the hardware level is quite good. So we get about comparable performance with the uBlocks modules as we do with the QUTELs now.
Robbe, what's your favorite part of the 3X process?
The favorite part?
Yeah, which one brought you the most joy?
Ooh, that's a difficult one. I really like the new image sensors. Like they're nicer, they're easier to route, they have better specs. Yeah, they're cool components.
We got any additional questions? All right.
How do you manage being in Belgium while they're here? If you're the hardware guy.
Well, you get used to it. It's I used to be in San Diego for a year, so I know the team very well as well. And then we communicate over Slack, so I make sure when the US is awake that I get all my questions answered and I can continue working the next day. Sometimes it's nice as well, like you're sitting by yourself, quiet, and you just plow through it.
Robbe is our only remote employee. That's how talented.
Also, he comes in about once a quarter.
Yeah.
Every Wednesday, Robbe and I have a lunch meeting.
Yeah.
And every Monday, we do a team meeting. Comma's super low on meetings.
Yeah.
We have an all hands, and then a team meeting every week, and that's about it.
Yep.
All right. Thank you so much, Robbe.
No problem. Good luck. Yeah, well, you have to click through all the...
I'm very excited to welcome Vivek to the stage, notably reminding me that Vivek came to Comma through a hackathon, and I think it's the perfect time to show our September hackathon. September 29th, that weekend, we will be hosting a hackathon in our office with our friend Billy. Who's Billy's new friend? Oh, sorry, Billy and Silly. Billy recently learned how to take pictures and print them as part of another local hackathon, so Vivek, our resident hackathon. Anyway, please welcome Vivek.
Hi, my name is Vivek. I work in the research team. So my talk today is going to be about, can you tune my car? This is a question that I get at least once a week on Discord. So we have a Discord. I'm sure, how many of you have been on our Discord? Okay, and we have a development tuning channel. How many of you have been on the tuning channel? Okay, great. So if you go to the tuning channel, you see a lot about good tuning, bad tuning, and ugly. Maybe not ugly, just good and bad. So if you're new to OpenPilot or new to Discord or new to the channel, you might be wondering what exactly needs tuning, right? So everything that we spoke about today, we never really spoke anything about tuning something. So what exactly needs tuning? And for that, you have to understand how is your car different when it comes to OpenPilot? Like how are cars different with respect to OpenPilot? So these are some of the brands that we support. So some ways in which cars are different are, the wheelbase is different, and the wheelbase is the distance between the front and the rear wheel. So as you can imagine, different cars have different sizes, so the wheelbase is different. They also have different widths. And as a consequence, they also have different masses. Like some cars are light, some cars are heavy. We support from like tiny cars to like the Ram, and they're quite different in that way. Cars are also different when it comes to other things like steering ratio. Steering ratio is how much your car turns with how much steering wheel turn. And that is different in each platform and also different across brands. Your tire stiffness, which is like, again, like the quality of your tire, how much like torque your tire provides while turning, stuff like that is also different. The center of gravity is different in all cars. Depends on how many people are in the car and stuff like that. And then actuator lags. So each brand and each platform have different ways of processing the signal that we send to the car. So when we say, okay, do this maneuver or do this turn, there is like some internal processing happening in the car, and then it actually actuates that in the final actuator, and there is like a lag, which is also different for different brands. So all of these things are different. So to understand how like these differences in cars manifest, let's look at this example. So these are three cars: the Honda Fit, the Toyota Corolla, and the Ram. All of them are like quite different, as you can see the images. So let's focus on lateral movement, right? So let's assume all cars are moving at 20 meters per second. All of them have a 10-degree steering angle, and they're all traveling on a flat road. So this is the trajectory that these cars would take. So this is the Y versus X. So if you start at the same position, this is what the cars would do under the same instructions. So I guess right now it's clear that we need to really understand what exactly happens when you give instructions to cars. So how do we actually learn these things? We learn these things using something called the vehicle model. So to understand the vehicle model, let's look at some high school physics. So you're turning, you're in a car and you're about to go to a turn. So this is the front view. So let's assume that the road is banked, and let's also assume there is some wind, because why not? So this is the top view of your car. So your four wheels and your front wheels are turning. So I don't know how many of you are familiar with car dynamics. So this is something that we call a slip angle. The angle between your direction of motion to your heading is called the slip angle, and that determines a lot of the dynamics of your car. So you can see that there are forces that act on the tires. So this is basically something called a bicycle model, which is you assume that your car is a bicycle, which is not a great assumption, but it really works. It's a simplified assumption of your car. And then this is where the center of gravity is, and then you have if you draw all the free body diagram and the forces that act on this object, you end up with something like this. So let's quickly go through this. It looks quite scary, but it's not. So what we have is the desired curvature that we get from the model and from the planner. We know the car has to do something, right, at some curvature, at some speed. So we have the yaw rate. If we make some very generous assumptions about cars and about our dynamics, we can find out from the state space equation, we can find what the slip angle is to achieve this particular yaw rate. And when we know the slip angle, we can find the steering angle that you're required to turn to achieve the maneuver that you want to do. So this is called the vehicle model. So we have a daemon in openpilot called params-t, which learns all these parameters inside that we spoke about, and then it learns the dynamics of your particular car. So it learns things like the steer ratio, the tire stiffness, the road roll, the steering angle offsets, and all of these things. And it learns all of these things about your car, about your particular car. So the interesting thing is that the steering angle offsets is basically, to go straight, you would assume you should keep your steering angle at 0 degree. But that's not true. All cars have some offset. You have to keep your steering angle at 2 degrees or -2 degrees or whatever. And that depends on your car and how long you've driven it and stuff like that. So this is also something that we learn live while you're driving. A fun fact is that as a consequence of learning all this, we also know when you have a bad wheel alignment, which is if your wheels are aligned badly, and then if you want to go straight, you have to hold your wheel at like a 10-degree angle or something like that. A lot of people come on Discord and they're like, hey, I just installed openpilot. It drives fine, but it it tries to go, when the wheel is straight, it tries to go right, and when it's going straight, the wheel is slightly to the right. Is my device broken? And then we tell them what the problem is, and then they come back a few days later saying, hey, about that, I went to a mechanic and he said my wheel alignments were wrong, and then they fixed it, and now my car drives perfectly. So this is something that from your logs and from the tolerances that we know, we can tell you if your car has a bad wheel alignment. Okay, so now we learned all of this stuff. So where do we actually use it? So as you see, we have sensors, which is car agnostic. We have models and planning, which is also pretty much car agnostic. But the actuators are specific to cars. So this is where we convert the car agnostic stuff to the car specific stuff. So we started with a maneuver that we wanted to do, which is like a steering angle. So to achieve the same thing, so we used a traditional PID control. So we have a steering angle, and the car gives us back the steering angle. So we're like, okay, go 10 degrees, and we have a classic PID control to make sure that the car is driving 10 degrees, and then everything is good. So this is the distribution of the lateral acceleration error when you're doing these maneuvers. So it's very important for us to understand how well the car is performing the maneuvers that you're asking it to do. And for that, we have a whole bunch of metrics. But one of the most important is absolute lateral acceleration error. So what do we mean by this? We mean that so when the instruction is to perform some maneuver with some lateral acceleration, and the car is doing something else, so what's the difference between these two? And we have to drive this number down. So as you can see, the straight is, the distribution is like the average is much lower than in turns, which means that while going straight, you're pretty much, it's like error-free, but in turns, it's slightly worse. So this is a metric. Just remember this metric. We'll keep coming back to this again and again. So we had all of this, right? But then we realized that in our fleet, the way we actually give instructions to cars, we don't actually give the steering angle. For like overwhelmingly most of our cars, we give the torque. We give the steering torque that you have to apply to the car. So we realized, wait a minute, we were going about this whole roundabout way of we have the curvature, we do all of these equations, and we find the steering angle, and then we close the loop on the steering angle, and then finally send torque. So we can just like circumvent that and then try to find torque. So this was a whole effort called torque control, which we released in 0815. So let's revisit the same maneuver that we did earlier, which is this car doing this turn at this angle. Now if you focus on the tire patch that is in contact with the road, so this is like the free body diagram of this tire patch. So you can see that these are the forces that develop on your tire during a turn. So you can see the wheel is heading is this, the wheel is moving here. So this is the slip angle. So what this effectively says is that the wheel torque is, you have a resultant force that is like X behind the center of the wheel. So basically, the wheel torque is this resultant force F times this pneumatic trail. And for a particular configuration of your car and your vehicle, this is constant. So the key insight here was that the wheel torque is proportional to the lateral acceleration that you want to achieve, adjusting for gravity. And from data, the second insight was that the wheel torque is directly proportional to the steering torque that you apply when you account for some friction. And friction is, when you're turning right, and immediately if you want to turn left, there is like a bit of friction in your steering column that you have to account for. So basically, we can get the wheel, we have a lateral acceleration that we want to achieve, and all we need to do is learn one proportionality factor to directly, to know what command to send to the car. This was great news. So we can find one value which for each platform, and everything is good. We implemented this. So you can see this is the lateral acceleration that is desired. And this is the steering command that we send to the car to achieve this. And this is for a Toyota RAV4. And this looks pretty linear to me. So this is what we implemented in 0815 and torque control. And then this is the result. So again, the same metric, absolute lateral acceleration error for some cars, Toyota Prius, and you can see that the torque control was much better than the simple PID tune for this PID on directly the steering angle. So this was great news. And this is even great because the subtlety is that these higher errors lead to other things that are undesirable, like they lead to more ping-ponging, they lead to like wandering in the lane, they lead to other things like that, which we don't want. So this was great news, and everything looks good here. But then, okay, let's revisit the assumptions that we made. The assumption was the pneumatic trail was like constant for a given vertical load, which means for a given configuration of your car. But then, like even among platforms, even among like Toyota Priuses, like each Toyota Prius is slightly different depending on like how long you've used it, what you put in your car, and stuff like that. The contact tire patch is also quite different. It depends on your quality of your wheels. It depends on how much air you have in your wheels. It depends on which road conditions you're driving on. And the steering column friction depends on the wear and tear of your car and etc. So this is also corroborated by the fact that when we do the same calculation to find the single factor for each platform on every car of that platform, we see that there is like a big difference in the big distribution in the value that is learned. So these are this is the distribution of the factor that I spoke about. And you can see that for even one platform, there is a wide range of values. So we set the value somewhere here in between, and then it's great for people whose cars are like here. But then if people's cars are like here or here, I mean, it's not that great. So this was like the motivation for us to go down this route of, we're not happy with platform averages. We want something tuned for your specific car, the car that you drive. So this inspired this effort called TorqueD, which is auto-tune. So basically what it does is the same thing that we were doing offline on like all the data from a particular platform like the RAV4. Now we do the same computation on your device while you're driving. So when you start driving, we collect data, and then once it meets certain conditions, we use the algorithm that we were doing offline in your car, and then now we have one constant that is learned on your car. And the great thing about it is that if you change your tires next week, or if you refill air, or whatever, if like you put some stuff on top of your car to go somewhere, like it learns live and it adapts live, and then your performance becomes better as a result of that, which is great. So going back to the same metric, so this is for Toyota Highlanders. You can see that the torque control was red, which was already an improvement over the previous generation stuff. But TorqueD was an even better improvement over that, which is great. This means that if your platform has like a bunch of versions where like the versions are different, but they somehow called it the same platform, it's still fine because we don't care about that, and we learn it for your particular car. So let's revisit the assumption again. We assume that the wheel torque is linearly proportional to the steering torque. So we assume that you apply some steering torque, and the wheel torque is some factor of that, and then we forgot about it. But turns out that's also not true. We assume that there are effects like backlash. So when you're turning left, and when you're turning, and immediately you have to turn right, there is some play in the steering column. There's like a backlash that you have to overcome, and then your car starts turning right. While driving, we don't really realize this because humans are really good at driving. But when you're controlling the car through instructions, you realize there are all these effects at play that you have to account for. The other assumption was that we didn't care much about speed. We assumed that everything works the same at all speeds. Like that's fine. But turns out this is also not true. For some platforms, at different speeds, your car behaves very differently. And this also needs to be accounted for. So for example, if you take the same plot of the lateral acceleration that we desire versus the steering command that you input, this is for the Chevrolet Bolt. I mean, this looks pretty nonlinear to me. If you remember in the RAV4, it was pretty linear, and in this, it's not. So we had to do something about this because if you apply the same algorithm that we used earlier, people have like not nice experiences, especially at the extremes where it's like it gets pretty nonlinear. So we implemented a nonlinear algorithm where we have a nonlinear fit for the relationship between this lateral acceleration that you want to drive on and the command that you give. And then this was out in 093. And you can see the effect of this change. So the nonlinear is better than the linear, which is also great. And a fun fact is you can see that there is a difference in the left turn and the right turn. This is like an idiosyncrasy of GMs. And all these are super interesting things because we can see this at scale. And it's very hard to see this if you have one car. But you can see that the errors are slightly higher for left turns than right turns. It's because in Chevrolets, the left turn is slightly different compared to right turns. And I mean, I don't know why, but it just is. And this also we need to account for. This was like a great improvement for the people using, people who have Chevrolet Bolt. So where do we go from this, right? We've seen that, over time we keep improving this stuff. We keep making sure that we move from move from fleet averages to platform averages, and from platform stuff to each individual cars. So a big effort for that was we released this data set called Comma Steering Control. And this data set is the largest data set of its kind. So what it has is it has the actual command that you give to the car, which is the steer command, and all the other metadata like the lateral acceleration, the road roll, the velocity, a whole bunch of other stuff. Now this is excellent because this data is something that probably nobody else has. Like, we are in a unique position to have so much data about so many different platforms across different driving conditions, different weather conditions and all of that stuff, and different usages. Like, the cars have different wear and tear. So this is a fantastic data set which with all this data. So what you can, and this is 12,500 hours of open-pilot driving, 10 plus car models and 10 plus brands. And we have plans to add more data to this. We have plans to add non-open pilot driving. So when I spoke earlier about the vehicle model, that vehicle model is valid for small slip angles, which I mean by small steering on a highway. But if you want to do a rapid 180-degree turn, the vehicle model completely breaks down. You can't use the same vehicle model for that. In OpenPilot, we are not there yet to do 180-degree turns, but we will be. And at that time, we will have to dive deeper into the data and figure out how we can improve our algorithms to cater to those maneuvers. So this data set has all of this information. So some people on Discord have already started using this. So they have some obscure brand that not many OpenPilot users use. So now they have access to a whole lot of data that they can dive into, and they can see if they can improve the performance of their own particular car, which is great. So what is the future for tuning and controls, right? So we want to use more neural techniques to learn the complicated feed-forward functions. So you saw we started with a simple linear model. And then we went to linear model on device, and then we went to a nonlinear, but with still we sort of reverse engineer the function and then we learn it. But we want to move to a totally learned function. So what this means is there will be irrespective of what the input and output is in your car, we should be able to learn the response of your car to the instructions that we give to the car at all ranges of speeds. There are some cars that do automatic roll compensation in the car and all of this stuff. We want to be able to learn all of this stuff live in your particular car. Not sure what happened there. Yeah, so I mean that was I was about to end. So so that's the. That's another plan that we have. The final goal is to move to a target audience of 1. So basically the target audience of you, and everything is tuned to your car and it drives perfectly. The output of the model and the planner is perfectly implemented on your car, and there is, and then the final goal is me not getting any more messages on Discord saying, "Can you tune my car?" So that's it. I just had a couple of call-outs. So. Do check out this data set. Do come on the Discord channel, and we keep discussing a lot on the Discord channel. So hopefully you can improve your own car much better, and then we can upstream it. That would be great. And a call out to openpilot user Twilsinker. He's been like at the bleeding edge of a lot of this stuff. I just wanted to call him out and say that's like great work, and we keep watching it, and we're very inspired. And I hope this also inspires more people to check out what's happening inside their car. That is great. Awesome. Thanks. If you guys have any questions.
All right, we got lots of questions in the front.
So are all platforms using the TorqueD already for the automatic tuning, or that still needs to be fleshed out?
So all Toyotas, all Hyundais. So I think it's about 80% of our fleet uses it. The Hondas don't, because there is a little bit of problem with the Hondas. I mean, they also work really well on traditional PID control. Yeah, I mean, most cars use it, and the plan is to roll it out to all cars.
Great.
Hello. So is longitudinal going to be in the foreseeable future for auto tuning?
Yeah, so that's a good question. So the thing is, the lateral tuning was very much a function of, like, it's very much defined by the vehicle model and the physics behind it. And a lot of the issues that we used to have was not handling the physics properly. But the thing with longitudinal tuning is that it's not much as physics as much as there is a lot of lag, and we don't handle the lag compensation properly in longitudinal, and it's like a bit tricky to go over that. So the problems that are with lateral tuning is very different from the problems with longitudinal tuning. So, I mean, yes, to answer your question, yes, we will have all the parameters learned live in the car, but it won't be part of TorqueD. Like that's like separate. I mean, it's like doing something else. There will be something else like that, which will learn all the parameters required for longitudinal.
Gotcha. Thank you.
Great.
I think my question is kind of similar to the last question, but how do you deal with like hysteresis, which is like basically actuator lag? Like for longitudinal, you said there's not much been done yet, but for latitude, like is it compensated for in the motion planning, or like?
Yeah. So so what we call friction is like is a manifestation of this hysteresis effect, which we already handle in openpilot. In TorqueD, we already compute what this the hysteresis component looks like, and we already handle this. So if you see the plots, I don't know if Greg can pull something up. So we have oh yeah, if you see these plots, so this is from our from the data set. Can I just go 1 second? I think it's fine. Yeah, so if you see this, so this is from the data set that we released. So the effect there is all hysteresis. I mean, you see the width in the plot, right? And this is already accounted for in TorqueD. And you know, I mean, we have more effects like that, which are not exactly hysteresis, but they have this like sort of discrete jump type of effects, which is more stuff for us to handle. But yeah, I mean, hysteresis is handled in TorqueD right now.
What is the optimal model of tire for openpilot 0.9 according to the data?
I mean, yeah, that's a good question. So I guess to answer that, there is an optimal model of a tire, and there is a simple and useful model of the tire, which is what we follow. If you ask for the perfect model of the tire, I mean, you can find many textbooks on this one topic on like what is the
sorry,
optimal.
I meant like the make and model. Like
I see.
Like,
I see.
should we be using Michelin or?
Oh, I see. I get you. I got you. I'm not sure. The thing is, we don't from logs can get the model of a tire, so I guess that's something that we don't have access to. But we certainly understand what sort of like which platforms have like what sort of effects in following our instructions. And that's something that we can comment on, but yeah, we don't have access to the make and model of the tire.
All right, I got a question up front.
Is it on the roadmap to replace the current controls and tuning system with a completely end-to-end machine learning system?
Yeah, there is. But I guess it's not to replace, but to build on, which is, as George said, as everybody's been saying, I think iterative improvement is something that is like a core tenet at Comma. So we had something very simplistic, and then we moved to something a little more complex and a little more complicated, and then that's, I guess, the direction it'll be going in. We will have much smarter techniques that learn everything that needs to be learned, like while you're driving, and then yeah. So it won't be like a replacement as much as just building on what we already have.
All right, thank you. Give it up for Vivek. All right, if there's one thing working at Comma has taught me is that it's infrastructure all the way down. I'm excited to bring to the stage the king of infrastructure at Comma, Greg.
All right, who wants to talk about servers? Are servers exciting?
Woo!
No, I don't believe that for a second. They're boring. Although we do have a really hot data center, so. All right, it's all downhill from here. All right, so at Comma, we train models, machine learning models for openpilot, and we always want to train bigger models faster, iterate faster, and so we need lots of servers to do that. This is a picture of our prior office. We moved to a new office recently, and this is what we used to have for servers for training models. And you can't really see the servers because this is in a really dirty garage. And the only way to really filter the air with a giant garage door and all kinds of stuff going on in there was to put filter media right on the front of the servers to try to keep the dirt from going into the servers. So you can see here, this is a 4-car garage. There's room for 4 cars, and the servers take up less than 1 car spot. So really not a lot of space here for our servers. This is about 5.68 petaflops of bfloat 16 performance. We measure everything in bfloat 16 because that's what our models are, and so that's all we really care about. This whole room, or this slice of the garage, we spent about $500,000 on the servers, getting power in here and the ventilation and everything. So in the old office, we ran out of power. We couldn't handle the amount of heat we were generating. The whole building only had about 200 amps of power. That tiny panel in the picture on the right there is all the power for the whole building. The ventilation was the best we could do. We had a skylight up in the top, and we had an intake and an exhaust fan that were up in the ceiling. You can see the skylight on the left there. I kind of propped it open because I needed more airflow, because the skylight's pretty restrictive, and for a good reason. We don't want rain coming down in on our servers, but when it was really hot, I would maybe try to prop it open and get a little more airflow. So it wasn't great. We ran out of power. We didn't have enough airflow. We wanted to train models faster. We wanted to buy more servers. We didn't have the power. We wanted to buy more servers. More servers means more power. More power means more heat. So we moved to a new office. A big criteria for the new office was way more power. We found a place with 8x the power of our previous office. And for the first time, the servers are not in a garage. They have a room. So this is the room that we chose. It started out empty. It was not, obviously, wasn't for servers. The first thing we did was we ran 800 amps of power into the room. This was pretty expensive. We spent, for all the electrical work in the room, we ended up spending about $125,000. The power was kind of on the wrong corner of the building for the servers, so it was quite a ways we had to run the power and stuff. But thank goodness we had a place with lots of power, so now we can run lots more servers. So in this room, we added a couple short walls. These walls are basically to help with hot aisle, containing the hot aisle. Some partial walls. The racks obviously go in between those walls there. We have these 42U racks that we use. We knocked out some windows. So I guess I didn't really explain it, but just like in our last data center, we only had fans. It was a garage, no air conditioning. We're in San Diego, and we can potentially save a ton of money not using air conditioning. So what we do is we just use fans. You can see the windows boarded up here, and then we installed some really big fans. These are, oh, thanks. Yeah, I guess the fans are more exciting than the servers, huh? The fans are 3 horsepower. Each fan does about 28,000 CFM. The room's pretty small. We can exchange all the air in the room in less than 10 seconds. So these are quite powerful. Then inside the room, this is one of those hot aisle containment walls. We also have some fans that recirculate air. So we can basically take the hot air and bring it back to the cold aisle when we need to, because sometimes we need to raise the temperature on the cold aisle. I said our data center is hot. We run a high temperature data center. And I'll get into that a little bit more. So sometimes it's not hot enough in our data center, and we make it hotter. And then the last thing was we just use a strip curtain, anti-static strip curtain, to kind of seal off from the front side, from the ceiling to the top of the server or to the floor, if there's no servers in the racks in certain racks. Then the last thing is we want to make sure that the air temperature from the ceiling all the way to the floor is a very similar temperature. I'll get into more the humidity and why, but basically we need an even temperature, so we have even humidity all the way from the floor to the ceiling. So these are called destratification fans. They just suck air in from the ceiling and they push it back down to the floor to even out the temperature. So this is what the room looks like after we built that all out. There's 2 intake fans on the ends that bring in air from the outside. The air goes through the servers, through the racks, and then there's 2 big fans that shoot the heat out the back. And then on the sides, there's 2 recirculation fans, and you can see those recirculation fans are kind of pointed at the intake fans, or where the intake fans blow in. And I thought I was going to have to do something way more complicated. It turns out you just point fans at each other, and the air mixes amazingly well. So in our data center, our intake temperature goes up to 43 C. Why? Well, we always want to keep the cold aisle at the outside temperature or lower. And in San Diego, it can get up to it can get up around 110 degrees sometimes, rarely. And so that's kind of the max temperature that we design everything for on the intake side. Exhaust side, we try to keep it below like 55 C. It generally stays around like 53 at the most. So this is a picture of we buy a lot of used servers, and it's kind of funny to see we have like temperature history in the BMC of the servers, so you can see like, oh well, what was this server? What was the temperature this server was like in its previous life before we bought it? And you can see, it runs around 21 C in some beautiful climate-controlled data center, and then we have a peak temperature of 42 there once it starts running in our data center. So we abuse them. You can find data on how much power data centers often use on cooling, and it's crazy. Like, I don't know if most people realize this, but it's not super uncommon for a data center to spend more power on the climate control, basically on air conditioning, than they give power to the servers. So that's not great. Like, power is expensive, especially in California. We want to use as little power as possible for the climate control, and as much as possible for the servers. So we do way better. If all of our fans are running full power, we're using 8 kilowatts, and that's less than 4% of all the power that our data center uses. And we don't always use that 4% or that 8 kilowatts of power. In our old office, we had fans that were just on or off. They were either full speed or they were 0. And that made the climate control a lot more difficult to to reach a desired temperature and stay stable and so forth. So now we have variable speed control fans. This picture on the right here is a VFD. We just have, they're just 3-phase motors, and you can use a VFD to basically scale the voltage and the frequency up, and then we can run the fan at any speed based on that. There's one other big benefit to this, which is if you have big fans, when you turn them on, they draw like huge power initially. So each of these fans, if you just like flip a switch and they suddenly get power, for a period of time, they're going to draw 80 amps each. And so when they're running, once they get up and spinning full speed, then they only use like 5 amps or less. So the problem is if you don't have something like a VFD controlling your fans, then what happens is you have to leave all this overhead power that you can't really give to your servers because, well, what if the fans need to turn on? So these VFDs were really important in maximizing the amount of power that was available to the servers so that we didn't have to leave all this power overhead available just to turn on the fans. So these VFDs basically limit, you can configure how they work, but we basically limit them to the max power that the fan uses at full speed. So if our fans are using 5 amps when they're running full speed, we don't let it draw more than 5 amps as it ramps up to, as it gets started and ramps up speed. For the climate control, we wrote custom software that does the climate control. We have these temperature sensors. This is a picture of one of the temperature sensors here that we have throughout the room. Basically, the inputs to the climate control system is the temperature and the humidity. So what we want to do is we want to maintain a humidity of 30 to 40% inside the room. We actually don't directly, it's kind of unintuitive, but we don't try to control the temperature in the room. We try to control the humidity. And since we're in San Diego, we don't have any problems where like it's both high temperature and high humidity. So anytime it's really hot, it's not humid outside. So since that's the case, I guess this works for us. It obviously wouldn't work for everyone. And so, yeah, so we're just always trying to achieve a 30 to 40% humidity. And the reason that we're so focused on humidity is because we've had a lot of problems in our garage data centers with humidity, because when the humidity gets really high, especially if it's dirty, that dust holds some moisture. And moisture on metal is going to cause corrosion. So we need to keep the humidity below the point where corrosion will happen. And so that's why we manage the humidity and try to keep it down below that 40% line for sure. So the way we have a pretty darn simple climate control algorithm. Basically, it takes the input of the temperature sensors in the room to get the humidity of the room and the temperature of the room currently to figure out like the relative humidity. Then we know we want to target this 30 to 40%. We come up with a temperature that will achieve that 30 to 40%, and then we vary the speeds of the fans to using a PID controller until we reach that target temperature. So yeah. It's pretty basic. Basically, if the relative humidity is too high, we need to make it hotter, because as you raise the temperature, the relative humidity of the air will come down. And if it's too cold, if it's too cold, the relative humidity will be too high. We need to raise the temperature. And so we recirculate the air in that case. And then, yeah, if the relative humidity is too high, then if the relative humidity is too low, well, generally the outside air has higher humidity than what's in the room, so we're exchanging the outside air and bringing that in. And then obviously we have like the mixing going on so that we can basically take the high humidity air that's coming in, shoot hot air at it from the backside of the servers, and get our desired relative humidity on the cold aisle side of the servers. So this is it. This is what it all looks like now. We now have approximately 55.88 petaflops of bfloat 16 performance. So we basically 10x'd our with all these fancy new servers we bought, well, a lot of them are used. I shouldn't say that. New to us. We now have about 10x the throughput. And we ended up spending about $1.5 million. So I mentioned, I think, that all the electrical stuff cost us like $125,000. All the ventilation stuff cost us like another $75,000. Some of the equipment that I'm counting here is like money we already spent. So like that's included in this total. And then we bought, you know, additional servers up to this number here, basically. So how does that compare to other supercomputers? So since all we care about is bfloat 16 performance, it's not exactly straightforward to compare it, but we can come up with something relatively meaningful. This top 500 list, maybe you've heard of it before, it's like the top 500 supercomputers in the world. It's not like a comprehensive list. You submit to be on it if you want to. We don't, and part of the reason why is because, well, this is FP64 performance, which like, who uses that? But if you look at this list and you find, I looked through this list and I found some systems with modern GPUs. And if you find systems around like 4 petaflops of FP64 with modern GPUs, they have around 60 petaflops of bfloat 16 performance. And those are around like the 175, certainly above the 200 mark. So in terms of bfloat 16 performance, we're somewhere comparable to like 175 to 200 on this very narrow axis at least. And just for bfloat 16 performance. And if they have modern GPUs, some of these are like all CPU systems and just, you know, not really comparable at all. So the high-level specs, we use about 205 kilowatts of power when all the servers are running full tilt. We have 5,088 CPU cores, which is actually a very small number. We have 640 GPUs. Some of the GPUs, we've got all the hardware. Some of the GPUs are still being installed, but that's what we have in the room, just not quite. Some of them aren't in the servers yet. And 2.1 petabytes of solid-state storage. So we have kind of 2 classes of servers in this system. We have servers that train the models, and then we have what we call rollout servers that feed the trainers. So the trainers, they each have 8 GPUs. That's 2.64 petaflops of bfloat 16 performance combined for all 8 of those. They have 100 gigabit Ethernet and 400 gigabit InfiniBand. So the 100 gigabit Ethernet is basically feeding data into the servers, and the InfiniBand, that's to sync across the servers. So one of the things that we do now that we didn't really do before is we often train models on multiple, like train the same model on multiple servers at the same time. So we have this massive bandwidth to sync data between the GPUs on our trainer servers. So yeah, we spend about $25,000 on each of these servers, and for the trainers, we generally buy new hardware to get us you can actually generally get the most dollars per flop buying some newer stuff. So the rollout servers, they are these 2 EU servers that look like this. We shove 2 GPUs in them. For running models, they have 238 teraflops of bfloat 16 performance. Then we have another 2 GPUs for decoding frames. I'll talk about that more a little bit later here. They have 20 gigabits of Ethernet. We have 100 of these, so they don't need massive Ethernet connectivity. And then some of them are part of our distributed file system that stores all our driving data. If they do, they have this 40 terabytes of storage currently. You can kind of see in the picture here, up high they have some disk drives in them, down low they don't. So like those top ones there we have dual purpose rollout servers. They're both part of our distributed file system and also for rollout. So the 2,500 that we spend per server on these servers doesn't include the storage. That's just everything else that's in there. We build these so cheap because we buy all this. I think everything in these servers is used, except for the disk drives, I guess, which isn't in that 2,500 anyway. So that distributed file system that I was talking about, it has all of our driving data that we use for training the models. So currently, I looked and we have 3.84 million segments. What we call a segment is a 1-minute clip of driving. It has both some video files and a log file for each segment. And we store it in the key value store. Our distributed file system is this key value store called mini key value. I talked about it in great detail in my talk 2 years ago if you're interested in how that works. But yeah, it's basically a key value store that we wrote that's super simple. We looked at all the other options and they're like crazy complex, and we just needed something super, super simple. It's less than 1,000 lines of code. That driving data, it's from 11,000 unique devices. So we've got a pretty good amount of data diversity now. We generally have, I don't think we've ever been limited by data diversity up to this point at least. So 11,000 devices is basically like 11,000 vehicles, 191 platforms or types of vehicles cover those 11,000 devices, and 66 countries. There's a lot of data from a lot of different countries. When we build our training lists, we kind of pick a slice of this data, like the best slice, because we often do things like say, oh, well, most of our data is from the US, but we also want data from other countries and so forth. We want to keep things like balanced. So, yeah, we kind of slice and dice and take a subset of all this data to build our training lists for training models for openpilot. So the first step, or kind of the start of the data flow through the whole training process, is reading those video files. Those video files are, recorded on real people driving their comma devices. The comma devices encode that video in H.265, and one of the first things we need to do is decode those frames. And so part of the reason that our rollout servers have both 2 GPUs for running models and 2 GPUs just to get more decoders is because we need to do so much video decoding of these H.265 files. So that whole rollout system that we have can decode 300,000 frames per second. And then, so that's mainly the 2 GPUs used for decoding. Then those frames feed into the models that are, for example, our simulator. And those GPUs in the rollout servers, they can output 200,000 FPS once we get all the GPUs up in all those servers. The models that we train for openpilot, that actually output the plan for openpilot, it's a kind of a 2-step. We train 2 models, basically, is what I'm trying to say for that. The input to those models is like the road camera, the frames. The first model, the vision model, takes in those frames and outputs a feature vector. So that's one model we train, that vision model. Then that feature vector is input into the policy model, and the policy model takes in the feature vector and outputs the plan that openpilot executes. So just to give you an idea of what the size of these models are, the vision model, which takes in frames, outputs features. It's 2 efficient nets at 21.47 million parameters. And to give you an idea of the speed up we achieved by moving from the old office to the new office, basically we went from 12 hours in the old office to 4 hours in the new office. So quite an improvement. Really increased our REPL time, which is great. So that was the first model. The second one, the policy model that we have to train, that one is an MLP with 5.3 million parameters. It used to take us 21 hours to train. Now it only takes us 7. So now we're like 11 hours now to train the models that we need to train to ship openpilot. So that's pretty cool. So we did a pretty good job. 1.5 million is pretty cheap for everything we built. The supercomputer that was like the closest in that top 500 list that gave similar performance, that's like at minimum a $3.75 million computer for sure. And that doesn't include like the building or, you know, like all the power and ventilation and so forth that I included in, you know, what we spent on ours. So we did pretty good in terms of dollars per flops, but we can do a lot better. And, you know, maybe in 2 years, my next talk is going to be talking about the tiny boxes in our data center. We'll see. Tiny box. Yeah. Any questions? What's up?
So the hot data center model that you're running, is that something unique that Colin has come up with, or is it unique to San Diego's climate, or is this something that's done in a lot of other, it seems very DIY, it seems like it works. I've just never heard of other like hot cold data centers, or heard of things in Iceland, but is this something that is common, or?
Yeah, so the question was, are we like unique in running a high temperature data center? And he mentioned that like in Iceland, they like do stuff, different, you know, kind of different setups. I've definitely heard of like high temperature data centers before. I don't know like what, my background is not data centers. I was a web/application developer before I worked at Comma, who migrated a big company into the cloud, worked on cloud infrastructure at Comma and said, wow, this is expensive and stupid. We should buy more servers. And that's how I kind of fell into this. So, so I don't have like industry experience on this, but I've definitely read about other high temperature data centers. What temperature that is, I guess I'm not really sure. And I'm sure they do it for dollar reasons. But yeah, it definitely works. I mean, I don't know why people baby their servers so much, I guess. Like our reliability in terms of temperature, I don't think we've had anything fail due to temperature. If anything, all our failures were due to corrosion, and the only way we get corrosion is if it's too cold in our data center. So yeah. Go ahead, yeah.
You're so awesome.
I agree.
Thank you.
Hello, I have a question regarding word usage. I noticed that you mentioned the word data center quite often, and I was watching the Hotz podcast with Lex Friedman a few days ago, and I noticed that he was reluctant on using the word data usage because you guys don't have air conditioning, you guys have fans. And yeah, so he said it's not a data center because you're using fans. So my question is, what are your thoughts on this? But also, second case, did you do any cost analysis on fan usage? Because you use really big fans versus air conditioning.
Yeah, so I mean, I did some cost analysis to know, like I knew what it was going to cost to buy air conditioning units that were going to do 205 kilowatt cooling, 205 kilowatts of power consumption, because that all turns into heat, and that's like crazy expensive. Now, we bought big fans. I found like some models that said like, if your temperature difference is this many C, you need this many CFM, exchanged to, bring the temperature down this much and so forth. So I kind of ran some rough numbers, bought fans considerably bigger than that, I think, and then felt safe that it was going to work, and yeah.
Is that your only server room, or what do you have for backup solution in case like there's no power in San Diego for like 3 days?
Yeah, so I didn't really talk about our production-facing infrastructure. This is all for research. So anything production-facing is in a cloud provider. We use Azure for our customer-facing infrastructure. This stuff, it'd be really annoying if this stuff went down, but we're fine with some reliability issues, and basically we exchange. Part of the reason that we can do this so cheap compared to the cloud, one of the reasons we don't run this in the cloud and we can do it so much cheaper is because we're not striving for some crazy number of 9s uptime. I mean, we are, but we'll accept some downtime to save massive, massive amounts of money. But we can, I don't know how much downtime we've had. I guess I haven't really calculated it, which obviously means it hasn't been a problem. So yeah, I guess yeah, we don't run it in the cloud because it's too expensive compared to what we've done, and we know that like our return on investment is, you know, if you include like the cost of the room and everything, just for the servers, it's like 6 months or something like that that we are better off. So with the room, it's longer, but still, it's we know it's way cheaper than the other alternatives.
All right, we got a question back here.
I have a question regarding the vision model. What do you use to supervise this efficient night?
I don't know the answer to that, but the research people would. You should find Yassine or someone, or Harald.
He's speaking next.
Okay, yes. You should ask that question to the next person.
I have a question regarding the GPUs that you use.
Yeah.
It seems the server is very cheap.
Yeah?
Yeah, so what's the GPU used for the training and what's for the inference?
Yeah, so for training, the cheapest dollars per flop, whatever that is, that's what we buy. For training, we need the most dollars per flop. You know what, you tell me, because if you find something better, I would love to know, and I want to buy them. And then, you asked also for the rollout servers. Yeah. So that we actually need the highest memory bandwidth per flop because we run much bigger models, and so the models don't fit in cache. And when the models don't fit in cache, you end up memory bandwidth limited because you're running batch size 1 on your rollout. So for those, it's the cheapest memory bandwidth per flop.
Yes, I also have another question regarding the training of the model. It seems like there are 2 models, the perception model first, and then there's a policy model.
Yes.
And I thought it's end-to-end training should be. So how do you train these models separately? Shouldn't you do this end-to-end?
Great question for Yassine, the next person.
Okay, thanks.
Save that one.
We got a few more questions.
So you mentioned it takes 4 hours to train the vision model. Do you mean the whole training process or just one epoch of the model?
What was the first part?
You mentioned it takes 4 hours to train the vision model and 7 hours to train the MLP model. So does it mean the whole training process or just one epoch?
The whole training process.
Oh, the whole training process?
Yeah.
Oh, that's cool.
Yep. Those models are fully trained in that many hours and ready, like potential candidates to ship. Well, I guess they have to be merged and tested and all that stuff, but.
Hey, first a quick comment on the hot data center thing. Why don't more people do that? I did actually ask this question by happenstance to one of my old tech leads, and he said, well, it'd be too hot for the people in the data center.
Yeah.
And that was his answer.
It is hot in there.
Yeah, it's pretty, yeah.
Yeah. Sometimes it's cold in the rest of the office, though. It's actually, it can be refreshing when you walk in there. I mean, yeah, I'm not really sure. I think it's becoming way more common. I swear I've read about some Microsoft data centers that are all fans, and if you look up like fan walls, you'll find data centers that have like a giant fan wall. I feel like that's like kind of gone by the wayside now, and that was like a multi-year ago thing now, and they're doing something else, but it definitely, I don't know, I might even be like a generation behind. There's like better stuff now probably.
Wow. Well, I do have an actual question for you, which is, that was very interesting. I will look up a fan wall. I want one, but better than a plant wall. Has anybody that you know of achieved a lower all-in cost per petaflop for training than you guys?
Again, I don't really have any experience in like industry infrastructure, like server data center building stuff, so I really don't know.
I think a lot of this information is just not public either.
I promise you the answer is no.
Okay.
I'm working on this at TinyCore. TinyCore is going to go 2x under comma. Comma's already 2x under anything else.
Okay, so we're 2x under anything else George has seen. I guess we did a good job. I just did the best I could do. And I always tell people I don't really know what I'm doing. So I guess you know why it's so good? It's because this is our 3rd data center, right? So we iterated. Yeah, we think this one is good, but 2 more, and we'll be saying this one was horrible, I'm sure.
Going back to temperature, so you said 50-something degrees Celsius was about as hot as it gets. Do you have any idea like what you're seeing on the actual die? I imagine it's some number higher than that.
I mean, the GPUs, they throttle it somewhere around 88 C on the GPUs, something like that. I'm sure the exhaust gets above 60, but then it expands out into the room. So, yeah, I'm trying to think of any other temperatures I know. Yeah, that's the best I can guess.
We got time for one more question? Anyone?
There's someone up here.
Oh, thanks, Greg.
So thanks for the talk. How long does it take to boot up a supercomputer? Do you have to do it in stages or just?
How long does it take to what, the supercomputer?
Boot up.
To build it?
No, boot.
Oh, to start?
If you power everything off and then turn back on, how long does it boot?
Most of the servers boot and are ready to run things in, I think, under 3 minutes. We're actually talking about like saving even more on power by shutting off like 40% of them and then like turning them on when they're needed. So individual servers, they take like 3 minutes or so, and yeah, they all start in parallel. So it should be on the order of minutes, single-digit minutes.
I don't know where you see one. Oh, we got one more question.
Real quick, percent-wise, like let's say on a 30C day, what percentage were you running your fans at? And do you run the exhaust and intake fans at different speeds?
So sometimes we run the exhaust fans and we don't run the intake fans. And so part of that is because you saw like there's like baffles on the fans, and they're just like mechanical baffles. So we need to run the fans fast enough that the baffles open up. So there's kind of a minimum fan speed that we need to run the fans at. So we don't run them all at the same speed. We kind of support using them in a staged manner to get like a lower airflow than if they're all running at low speed. So for example, like sometimes we run the exhaust fans and we don't run the intake fans, and say they're running at like 30%, that's somewhat less airflow than if we run the exhaust fans and the intake fans at that 30%. So yeah, we kind of do that. But generally we're doing that because the humidity is getting too high, and then we also have the recirculation going on that's helping raise it at the same time, basically.
And then real quick, I know y'all said I know years prior you had a data sales thing, like for like $200,000 a month. Did anybody actually buy it?
I'm not aware of anyone, no. As far as I know, no one's ever taken us up on that.
We do sell a lot of meetings, though. All right, thank you so much, Greg.
Yeah, thanks a lot.
All right, we've got 2 more talks for you guys. We started you out in our big achievement last year, and we took you through openpilot. You saw our new hardware, how we build it. You learned a little more about tuning, and we're going to round out the comma side in research. And then Jason, one of our most prolific community contributors, is going to talk about the work that he's been doing. Sometimes they say hard problems need a lot of PhDs. This is Yassine. He's our PhD. Dr. Yassine, everyone.
All right. Hi, everyone. My name is Yassine. I work in research here at Comma, and I was excited about some machine learning. Woo! Yes. I heard that I haven't started presenting yet, and I already have some questions. So I guess I'll answer them later. Don't forget. So today I'm going to talk to you about our progress in learning a driving simulator. So it's been a few months of this project, and we have some exciting results, and I would like to talk to you about them. Before I start, I would like to show you approximately where we're heading after this presentation. So as you might have guessed, none of these videos are real. All of them are imagined. All of them are predicted using a machine learning model of which we give a few frames of context and then ask the model to predict the next few frames, in here about a minute of frames. And yeah, as you can see, the videos look pretty good. The temporal consistency is pretty good too. So this is a minute of rollout, as I said. They exhibit some really nice properties. You can see that some physics is learned, some great dynamics is learned as well. For the night videos, you can also see that the lighting looks pretty good, which is something we really care about. And I will come back to this slide after we're done, but pretty much by the end of this presentation, you should pretty much understand how we built this and why is it useful to us and what are our next steps. But before, let's go back to the basics. Why do we even need a simulator? Harald talked about this morning. We talked about this 2 years ago in the previous Comic-Con. Why even a simulator? Without a simulator, the driving model will never be exposed to any kind of significant noise or any kind of significant deviations, especially the noise introduced from its own mistakes. So if we train a model outside of a simulator, without a simulator, what's going to happen is if you end up outside of the center of the lane, the model will always say, just keep doing whatever you're doing and recover later, recover in a few seconds. And the next second, it will also do the same thing. It will also say, yeah, you're pretty good, just keep going and then recover to the center in a few seconds. And the result of this is what you see in the bottom video. It's basically a model that doesn't recover to the center of the lane and just drifts outside of the lane. So this is a problem, and we need a simulator for this. Now, a good question to ask ourselves as well is, why not a classical simulator? Why do all these complicated things? Why not just build a Unity or an Unreal Engine simulator, a GTA 5 kind of simulator, and why not just do that? Well, I'm not saying that this is a bad thing. These simulators are good for testing. We want them. We want them for testing because they're good for, they're deterministic. They're fully, you can build whatever you want. You can build whatever scenario. But we want to use this for training. And training it is a whole different beast. First of all, you need to match the training distribution. You need to match the real-world distribution of driving data. And what is even that? How do you even quantify that? And how do you even know that you matched the real world? And even if you tried to do this, you would actually need to hard code a bunch of scenarios, a lot of them, and every day you'll just be building a simulator. You never do self-driving, you'll just be building a simulator, and that's not really a business that we want to be in. So as you might understand, this is not a scalable solution. You don't want to be hard coding simulators for training, at least. So we came up with this thing called the small offset simulator, and Harald talked about this morning as well. It's basically a simulator in which we shift the image a little to the right, a little to the left, a little to the forward, and a little backward to simulate little movements from the original position. And when we train the model in this simulator in closed loop, we actually see driving. We see a model that recovers, we see a model that stops for stop signs, we see a model that stops for red lights, and this is quite amazing. So this is a small offset simulator, and that's what we've been running with for a few years now. But as you might have guessed, we're trying to go past it. So why are we even trying to go past it? What's wrong with it? Well, Harald hinted at the problem this morning, which we call cheating. So in order to have a very good simulator of the sort of this small offset simulation, you want to have really good ground truth. You want to have good height estimation, good road plane estimation, good pose estimation, and so many good things. They need to be pretty much perfect. And the problem is, as soon as you start to get some imperfection, some error, you will have simulator artifacts. And those artifacts can tell the model which way you came from, or how to drive, basically. So the model will learn how to drive just by looking at the artifacts instead of learning how to drive like a normal human being. And trust me, the model knows how to cheat. So this is the first problem. The second problem is, well, it's in the title. It's a small offset simulator. It's not a big offset simulator. So as soon as we try to do some kind of big offsets, you can see that the images look very funky. And they really don't look that good. You don't want to drive in this world. And that really doesn't matter for lateral that much because you don't deviate so much left to right while driving laterally. But in longitudinal, this makes a big difference. At highway speeds, plus minus 10 miles an hour, it's really a big distance. So you really want big offset simulator for longitudinal. So this is it. This is our state right now, and why do we want to go past it? So how do we do this? Well, I'll tell some history here. In 2016, Eder and George wrote a paper called Learning a Driving Simulator. And I stole the title of my presentation from this paper. You don't have to read the paper. You can read it if you want, but I'm going to basically explain what the paper is about today. The paper basically describes what we're doing now. It's just read 2016 tech. You don't want to be doing 2016 machine learning. We want today's machine learning. 2016 machine learning sucks. This is what 2016 machine learning give you. And as you saw in the first slide, 2023 machine learning is a lot better than this. So what's an ML simulator? So we're trying to build an ML simulator. An ML simulator is basically 3 parts, 3 components. And I'm going to go into each component separately and explain what it does. And yeah, by the end, we'll go back to our first slide. So 3 components: image tokenizer, a post tokenizer, and the dynamic transformer. I'll explain every part separately. So an image tokenizer is basically a fancy image compressor. It's an ML image compressor that takes in images and compresses them into a set of tokens. Now, what's a token? A token is just a fancy name for a discrete number, a number that can only attend a small set of values from a dictionary. So take in images is a lot of pixels, then encodes them into this set of tokens that are discrete. Usually these tokens are not too much, 128, 512 tokens. And then with this tokenizer usually comes a detokenizer or an image decoder that can bring you back to image space, and in which you can see what you actually compressed and then compare it. This model is trained with a GAN loss, with a generative adversarial loss, and this is what is usually referred to as a VQ GAN. So yes, this is our image tokenizer. And in this slide, I show from left to right a source image, an image compressed to 5,820 bits, and an image compressed to 1,280 bits. So I want to point out a few details here that are pretty interesting. Do you notice this EVS logo here? Notice how it's a little funky around here, but it's still some red things around that area. But notice that the 1,280 bits just completely forgot about the CVS logo. You don't really need that. Why do you need logos in life? You can also notice that the building a little at the distance here looks okay for the 5,120 bits image, but the 1,280 image looks pretty funky. The traffic light also looks a little funky. So yeah, these are completely classical compression artifacts that we get here. So the image, this image there's a lot happening. There's a traffic light, there's a logo, there's buildings. So it's a complex image. For a pretty classic highway driving image, you really can't see the difference. This looks really similar to me. And so for highway driving, either 512 or 1200, that really doesn't make that much difference. And in order to iterate fast, so we want to iterate fast, and we know we can improve the quality of our simulation by just scaling up the number of bits. in order to iterate fast, do some good experimentation, we're working now with this model. But we know that in the future, as our models improve, we can always scale up and get better simulation. So for now, 128 tokens, 10 bits each. Now, what's a pose tokenizer? What's a pose to start with? A pose is basically 6 floating points numbers. They're 6 degrees of freedom, basically your x speed, y speed, z speed, and then your roll rates, pitch rates, and yaw rate. So we also need to tokenize these numbers just because of the next component that I'm going to talk about. But trust me, we need to do that. And we tokenize them with a very simple tokenizer. We basically need to digitize them or to quantize them. So we just digitize them with the uniform binning, very simple, nothing fancy here. Now to the beefy part, the dynamics transformer. Who knows what a transformer is? Yes. Who's used ChatGPT? Same people? Some people? More people? I see you. Cool. So yeah, a transformer is basically the same architecture as a large language model, ChatGPT, Llama, these kind of models. For large language models, a token is, roughly speaking, one word. A sentence is a set of tokens, and a document or paragraph is a set of tokens. For us, an image is a set of tokens. A video is a set of images, so a set of tokens. And we train it with the same way the large language models people do. Very nice loss function, cross entropy, predict the next token. So very similar to large language models. This is the architecture of a transformer. For those who don't know what a transformer is, it's basically a fancy machine learning architecture that's a stack of fully connected layers and attention layers. So just a black box of a machine learning architecture. So we use this dynamics transformer one token at a time, so it's autoregressive sampling. At each time we ask the model, what do you think the next token will be? We take that token, plug that back in the inputs, then ask it again, what would be the next token? Plug that back in the inputs, and do this until we reach a number of frames. These number of frames will give us this number of tokens will give us a frame. We take that and then do this as many times as we want until we reach whatever number of frames we want. So this is what people usually refer to as autoregressive sampling. Autoregressive sampling. So predicting each token at a time. So in theory, doing this is really powerful because you could cover the whole distribution of your training set. So you could cover the whole distribution of possible rollouts given a context, given a few frames. This could imagine any type of futures, which is really desirable because you don't want to restrict whatever happened next, whatever the driving model that will be trained in this simulator, you don't want to restrict it to something specific. You want it to be as general as possible, and this is really desirable. We tried a few things to speed up this autoregressive sampling, so it's a little slow. We're trying to speed it up. We tried something like diffusion-like sampling, some fancy techniques with mask git and things like that, but we didn't really succeed at anything like that. But we'll keep trying, and something will work. And we basically want to speed up the autoregressive sampling, which is a little slow. So we do all this, and it works. This is our dynamics model. This is our simulator. So in here, we just show it. We just tell it to drive straight. And as you can see, drive straight. It's a pretty nice highway drive, straight driving. But we can also ask it to do some things like yank the steering wheel to the right. Turn right as much as you want. And as you can see, turns right, changes lanes, even goes out of the road, even drives on the grass. That's pretty impressive. I guess some people did that in the training set. Who did that? You can also tell it to turn left, cross the median, drive to the opposite lane, even get close to oncoming traffic. Who did that? That's okay, I don't want to know. You can also tell it to accelerate. So notice the lane lines, it passes the traffic, it passes some traffic. So as you can see, there's some acceleration happening in this rollout. You can also tell it to brake. So again, notice the lay lines, they will slow down. So as you can see, successfully brakes. And as a side note, we open sourced all this. We open sourced a data set of 100,000 minutes of driving, tokenized. So these are all tokenized with the tokenizer that I've showed before. We open sourced the image tokenizer and the image decoder, and we also open sourced a transformer that's very similar to the one I'm showing you today, and that can generate rollouts that look like the one that I showed you today. We also have 2 $1,000 bounties. So if anyone feels like a weekend project, we want to decrease inference latency. We want to make this model run fast. Today they run at 2 FPS, so we want to run them really fast. So if you improve the training latency, the inference latency by 50%, you get $1,000. And if you decrease training loss by 5%, you also get $1,000. So if anyone wants a weekend project, really fun. Another side note, so I've been showing you all these images that went back to image space. So these videos that look good, it's always good that we can go back to image space and debug these dynamics models and see what happens. But in order to train a driving model, we actually don't need to go back to vision space. You don't need to go back to the image space. You can train the model directly on the tokens, which is interesting. So these images are compressed to these tokens, and these tokens have everything you need to know to drive, which is pretty cool. So instead of having like a convolutional neural network that takes in an image and predicts the plan and predicts the ley lines and such, now you have a transformer, and then you have a plan and the ley line and all that. And as you can see here, it works. It predicts the ley lines, predicts the plan, predicts some reasonable outputs. So we don't technically need to go back to vision space in order to train a model. We can directly train it on tokens, which is pretty nice. Another side note is that you've noticed that the images are a little flickery. So they jump a little bit, the clouds jump a little bit, the cars jump a little bit. So, and we were aware of that. We know that our encoder is not smooth, and that's because our encoder is frame by frame. There's no temporal consistency because there's nothing that's trained temporally. So we want to fix that. Then there's multiple ways you can fix this. We really want to have a tokenizer that's video-based, that's not image-based. What we're doing now is a little naive. You don't want to do this frame by frame. You really want to do it for a set of frames to get some more quantization. You can get more compression if you compress multiple frames. But there's a technique that people have been trying, and we tried that as well, is to have just freeze everything and then put a recurrent layer in your decoder, which essentially gives the decoder like a state that gets passed from frame to frame, and the decoder can use that to smooth the rollout. So as you can see here, in the left is the raw rollout, and to the right is the smooth rollout, so much smoother. So this works. Another side note is, okay, how do we use this to train? How, why, and what was missing for us to use this to train? We need a new loss function. And why do we need a new loss function? Well, for sufficiently long rollouts, the simulator is going to imagine things that were never in the context, right? It's going to imagine traffic lights, it's going to imagine turns, it's going to imagine curves on the highway. And these are going to be very far from the context because we don't condition on anything. We just tell the model to imagine something. So the human path that we have been using so far to train will be irrelevant for sufficiently longer rollouts. So we need to come up with something new. We don't exactly know what to do and how to do it, but the idea is going to be something close to like a value model that like either a GAN loss or something like something to minimize disengagements, or something to basically another model that's trained separately that quantifies whether your rollouts, whether your driving is good or not, based on the rollout that you're showing it. So something like a value model as a loss function instead of just MAE that we've been using for a long time. So what are the next steps? A few weeks ago, we tweeted, sorry, we X'd a video of our simulator, and the response, some of the comments were funny, but most of all, they really show what we need to work on and what we actually work on. So I'm going to show some of the comments on the comments. Harrison really wants to play this. He says, please let me play it. We want to play it too. It's really fun. But as I said, it's at 2 FPS. We don't want to play a game at 2 FPS. So we really want to make this faster. And that's something we're currently working on. We have bounties on it. And yeah, we just want to make this faster. John said there is a left turn on red. And this person said, oh, this is a green light. And we know this. We can see, we have eyes too. This potato quality image. And as I said, this is 128 tokens, 10 bits each. So we know there's compression artifacts. But in order to move fast, in order to experiment fast, we're using this now. We'll scale up for when we have either better video tokenizers, better sampling strategies. So we will scale up. We just need to work on these problems first. Leo said, I feel like building the simulator is not that hard. Trust me, Leo. Leo, we do things not because they're easy, but because we thought they were easy. So this is basically what I've been talking about. The autoregressive sampling, actually using the models, scaling the bits and scaling the transformer as well. And we need better video tokenizers. So going back to this slide, these beautiful rollouts, I'd like to point out some nice properties. Look at this lead car here, where the headlights turn on when it stops, and then they turn off when it goes on. So it's pretty nice. Some of these rollouts are actually really good. How do you know if this is a fake video or not? This looks really good. This one as well. It looks quite nice. In this one, the model takes an exit. In this one, the model does a lane change, then takes an exit, which is quite interesting. The night videos also look good. Look at these light halos that look really, really realistic. Again, fancy buildings, weird-looking buildings, as I've shown in the tokenizer slide, and this is really because the tokenizer is terrible. But yeah, you can see the building move, like it's really good physics understanding. The prompt of this image has the cables. Some people don't hide the cables from in front of the cameras, which is not a big problem, but you can see that the cable stays there, pretty consistent in the frames. This one here, it's a snowy road, and the snow persists after the rollout. So the snow is still there at the end of the rollout, which is really interesting. In this one, the model just wants to stop and takes a picture, I guess, of the surrounding. I don't know, maybe a mountain road or something. So yeah, this is it. This is Drive GPT. Any questions?
Wait, Yassine, we know there's lots of questions.
Oh yeah, I forgot.
Should we start with those? Who are the people who had the two Yassine questions before? Over here. All right, start back here.
So you mentioned that you can get like an initial image, and then you can also say that move straight or like move right. So are you conditioning on language at all, like the tokens?
Okay, so we don't condition on language. I was talking about the pose, which is the 6 numbers. 6 numbers are essentially moving, so your speed, lateral speed, longitudinal speed, and z, the z-axis. So those are the numbers that we use to condition the model to go left or right, or to go faster or slower. So we have those numbers baked in the model. So those are special tokens, call them the pose tokens, and those are used to condition. So we can either let the model go free falling. So the model also predicts those tokens. So the model knows which are the most likely next pose. So we can either run the model with those, and the model will be unconditioned. So we just use those from the model. Or we can just go in and tell the model, no, this is not what we want. We want to go right. And then put those tokens in, and the output of this thing will be a conditioned video. Does that answer the question?
We have a question here. Oh, well, great question. Come through here. Can I squeeze through?
Awesome talk.
Thank you.
I have a question about the bottlenecks in your pipeline. What's the top bottlenecks in pipeline to inference it for real time?
So these models are quite big, even though they're not as big as ChatGPT and Llama. They're a little big, and we're currently bottlenecked by software. We're not reaching RAM bandwidth or not even reaching flops bandwidth. So we're just really bottlenecked by good software, inferencing GPT models, transformer models. Currently, we just use Onyx, which is a pretty standard inference engine. And there are some fancy ones that are coming up. And yeah, so currently we're bottlenecked by software. When we reach the limits of the software, we'll probably need either to do some tricks on the architecture to make it faster, or just use more GPUs.
All right.
Thanks for the talk. So eventually, maybe these rollouts will be at least human indistinguishable from real rollouts, yeah? What applications open up when you get there?
So the first application we see here is really learning in this driving simulator. So we want to use this, completely replace our small offset simulator, and the driving model is basically going to live in this world, and it's going to drive around, go grocery shopping, go to the movie theater, and just learn how to drive in this driving simulator. I mean, other applications might pop up. I don't know, like a game or something. but for now, we're focused on learning a driving model in the simulator.
Are you worried about using too much of this learned simulation in your models and causing a model collapse?
A model collapse. So I guess you're referencing iteratively training on models, and that would cause a model collapse. Well, that happens when the models are. We have proof that this happened for models that are similar. So let's say you train ChatGPT on ChatGPT data, and you do this iteratively, the model will collapse. It also has been shown to exist for image generation data as well. But the models that we will train here are very different. This model, that's a simulator, is going to basically learn how to imagine driving data. But the model that we'll train on it is a completely different model. It's a model that learns how to drive. So these will be very different, and we're not going to do this iteratively. This is going to be just a one-step process, and we will improve both of the models independently, but there's not going to be any iterative process. So we are aware of the model collapse, but we don't see it as an issue for now. Yeah, does that answer your question?
I have two questions. One, do you consider use mask autoencoder that can compress about 90% of the image? And the second one is, you talk about a video encoder. If you use a video encoder, then forward to the transformer model, it should be output also a video as well. Is that correct?
Mm-hmm. Yeah, so your first question was about masked autoencoders, and that's what I was referring to as masked GIT or similar approaches to train image tokenizers and such. We tried. It didn't really work that well. But yeah, it didn't really work that well. What worked well is the cleanest solution. The most obvious one worked well. We tried to go fancier, and it didn't work. So I guess there's something to learn here. Then your next question was, can you repeat your next question? I forgot.
If you have a video encoder, that means if you put this audio encoder, the code to the transformer,
Okay.
If you go to the forward, it should be generate every token is a video. Is that correct?
So what I've was referring to as a video decoder is something close to like an I and P frame kind of tokenizer. So some different types of tokenizer. One would be like a general I frame, and then a P frame that's a smaller set of tokens or smaller basically more compression in the diff frames. So this is what I was referring to as a video encoder. But again, this is something we haven't done yet, and I guess we'll see what will work, and we'll see what other people are trying, and try to navigate in this research area.
Is the is the output from the simulator only used to train the policy model? Because the way I understand it, there's two models. There's the vision, which is like efficient net B2, and then the policy model.
Okay, so you're one of the questions from before, right? No? Okay. So I guess I will answer both questions. There was one question before about why we say there's two models while we also say that we're end-to-end. So there are two models, and when we say we train end-to-end, it's because these two models really have the same loss function. These two models predict the same thing. These two models predict what is the plan, and then they just predict the plan. And this is the only thing we use. We use the plan from the model. The vision model predicts the plan, and the policy model as well predicts the plan. Now, why do we need two models? We need two models exactly because we need a simulator. So these two models are living in two different worlds. The vision model lives in the real world, and the policy model lives in the simulated world. So we did the split because these two models need to be trained in different worlds, and yeah, so we're still end-to-end because we're not using any bounding boxes, we're not using any perception kind of layer that says, oh, these are traffic lights and such. So yeah, I hope this answered the first question. And the second question, yes, this simulator so the policy model will be trained on this simulator, but not the vision model.
All right.
Hey, great presentation.
Thank you.
My question as a researcher, I'm sure you know there's been so many advancements in AI. So my question is regarding how do you balance researching, testing, and playing around with all the recent developments in, for example, tokenizers. That's the topic that I want to focus on. All the new tokenizers that come out. How do you focus on testing out and working, playing around with all those new developments from other teams, but also clearly developing your own stuff? Since you're a researcher, you want to build your own stuff. So how do you balance?
So keeping up with state of the art is pretty hard. There's a lot of things that are happening right now. Machine learning is growing very fast. But there's one signal that I've noticed is that, I mean, you don't want to be the first one to replicate a paper. It's kind of a useless thing to do, unless you're doing it to learn, or unless you're doing it to practice, or you're interested in this personally. But being the first person to replicate, it's not that good. So you want to wait for other people to replicate and feel the waters and see if something looks useful or not. And usually this takes about a week or two. People are very active. And then pushing the state of the art. Again, you really want to balance being at the edge of state of the art or pushing it a little far. And I come over trying to push it where we need to push it. And there's a lot of researchers outside of Comma. There's a lot of people, a lot of labs that are working on the same problems. And it would be good if they did the work for us, but sometimes they don't. So we try to leverage their work as much as we can. And we also open source our stuff, so it's not like a one-way highway here. We open source our findings, we write blog posts, we publish data sets. So when we see the need to push the state of the art, we do it, and then we share with people. It's just a little line that we need to balance, but so far it worked great.
My question is, where do the model names come from? What do Nicki Minaj and Nicolas Cage have to do with driving?
Great question. I don't know if I'm allowed to say. Am I allowed to say? It's a trade secret.
We don't have a lot of secrets, but
trade secret. Sorry.
We're gonna keep these.
I had some questions about just the tokenizer aspect in general. Like, what motivates to stick to like these discrete tokens
I'm
instead of?
I'm sorry. Repeat. Can you
What's the motivation between sticking to like this discrete token representation versus like maybe a more regressive, like doing regression? Is that just because like cross entropy loss is so simple and nice, or is there something else? And then a couple more questions about the tokens. Is there like some position dependency on those? Have you tried looking at like the have you tried interpreting what token 95 means, for example?
Oh yeah, great questions. So we tokenize because cross entropy is the best loss function. Everyone knows that. Whatever else is just a scam. It doesn't work. But yeah, cross entropy is the best loss function. It's really simple. Yeah, I can talk a lot about why cross entropy is good, but it's not really the talk today. Your next question was about interpreting the tokens. So these are like visual tokens. So you can like feed an image of just token 111111, and then see what the decoder says. And these will be like basically colors or basic the patterns, or zigzags and stuff like that, edges and things like that. So these are visual patterns, and they do have positional information. And the transformer has a positional encoding, as most transformers. I heard that we don't really need these positional encodings, but we still have it. But yeah, we can interpret them. We can see what each token looks like. We can see if our tokenizer is efficient or not. We can see if like all the tokens have been utilized, and all tokens mean different things. So you can somewhat interpret these tokens, and they have positional information as well.
Say driving is very different around the world. I was wondering if you looked into conditioning on geolocation.
That's a good question. There's multiple ways we can condition these things. We can condition them on weather. We can condition them on geolocation. We can condition them on type of car and so on. We don't even want to go in this detail. We just want to build the most general simulator possible. If someone wants to condition them on country, look, the data set is open source. They can condition them on countries and look at data from Venezuela or from Uganda or anything. So yeah, we just want to build the most general simulator. We want to condition it on the least possible things.
Thanks for the talk. I was curious. I know Harald mentioned the long-term goal of Comma being going from just cars to broader areas like robotics. So I was wondering, first of all, if you plan to use the same like GPT-style simulator, and just how you think it scales to something like robotics, where you have more degrees of freedom and maybe a different like distribution of output spaces.
Yeah, great question. This is one of the main motivators of using this simulator, is that it can scale to any type of robotics problem. It has more degrees of freedom, but we use the very simple post tokenizers, which is MP digitized. If you have more degrees of freedom, you just use a more fancy tokenizer for that. This really scales to any type of robotics problem you wanna do. And as you can see, most recent robotics fancy looking solutions now use something that looks like this. So we're really excited about how we can extend this to something outside of driving as well.
Hey, thank you. So yeah, kind of related. So I'm thinking about this scenario. Say this is for the input for the driving model, right? So right now, I'm saying, okay, I want to drive from A and to B, for example. Please give me the scenario of driving to the nearest Taco Bell. But this is a language, right? I'm just curious why we don't put language as the first input and generate the actually the driving video scenarios.
Yeah, we don't really need language. I mean, we can condition anything with floats, with floating points numbers. Language is very inefficient. Why not use something that has a lot more bits than words? We can condition it on text. Some people are doing it. We really can do it. You can just connect this to an LLM, connect this to Llama 7B, and then put the text and get the embedding and then plug it back into the GPT. That's something we can do. We haven't been doing this. I mean, these are really cool demos, right? They're cool for papers. They're fun things to do. We've really been trying to make something as general as possible. And yeah, again, if someone wants to do this really easy, just plug it back with the Llama 2 and see what happens. Could be a cool project.
We got one last question here in the back.
Cool. Could you speak a little bit more about the temporal consistency aspects? In particular, I mean, the training data is temporally consistent, so kind of what's the intuition behind why the predictive model is unable, like has some flickering, and why it's not able to learn temporal consistency, and then what are the core ideas between, like I know you had a slide on it, but I didn't quite understand the core ideas that enable the loss of flickering.
Okay, so let me go back to it. It's going to be light mode. So why does the model not predict smooth video on its own? Well, because the data is not smooth. The data it's trained on is tokenized frame by frame. So the data that the model is trained on isn't good. It flickers. So even the ground truth data of this model flickers. And it flickers because the tokenizer is frame by frame. It doesn't have any temporal memory. It doesn't have any smoothness to it. It's just frame by frame. It flickers. And I mean, a good question would be, why does it flicker? Why does it not predict smooth? And it flickers because just compression, right? We're asking this model to really compress this really hard. So it will flicker. And we notice that the more bits we use, the less flickering we see. So this is to answer your first question. Why does it flicker? Then the smoothing decoder basically is just sticking an RNN layer, just sticking a layer that has a memory. And at each step, we share that memory to the next step. And then doing this, we have like a running state. And doing so, the decoder has more information now and knows how to smooth. The decoder didn't have that information before, didn't know what happened a second ago, didn't know what happened a frame ago. So it couldn't even smooth. Now it can smooth, and as you can see, it works. Does that answer your question? Okay.
All right, give it up for Yassine. Thank you. All right, we got one last talk. Some of you may know him as Jay Young. His name is Jason. He's going to give you an update on a blog post we wrote called How to Port Your Car. And there's probably no one better. And Jason, how many cars have you ported this year? He's been working all week porting a Golf GTI. What would you say how many total you've done? All right, almost 40. So I think that deserves a round of applause in and of itself. Kind of amazing. We really appreciate all the great work you do. I'm going to give you guys a few updates. After Jason's talk, there's going to be a happy hour. Soft drinks are included. If you want a harder drink, that's on you. There's a bar down here. We have games. We will have dinner. There's snacks in the back. If you still haven't picked up your merch, it's upstairs waiting for you. If you'd like to buy a Comma t-shirt, find me. Thank you all so much for coming and listening to these talks and asking great questions. We really are so happy that we have such a great community and contributors, and we want to continue to talk about how great you are at 7:30. We'll be hosting the Kami Awards. Adeeb, Shane, some of you may know him, Shane of Shane's Fork. We will be talking and rewarding the wonderful contributors of the community. So I'm looking forward to that. And then I was gonna call it giant chess, but it's actually medium-sized chess on stage. Some competitive chess, some games upstairs, hanging out. Find Comma team members if you have more questions. I know not everyone's questions were answered today, but if you can find everyone, I'm sure they're happy to further chat and go into more detail. We also have some wonderful contributors here. Sunny, of Sunny's Fork is here. If you have any questions, I'm sure he'll be around. So thank you so much. What's up? I'm sorry, what? We can do whatever we want. When the live stream's over, after Jason, there'll be a lot of secret stuff that's only for in-person people. So. Yay! All right, and now I expect a lot of carports after this talk. A lot of people say they can't find this information. It's now available, so you have no more excuses for not porting your car.
All right.
Give it up for Jason!
Hello, everyone. I'm Jason Young, JYoung8607 on Discord. You may have seen me, and you may know me as the Volkswagen guy. I have a very good friend who tends to go all in on technology hobbies. He got us into quadcopters back in the day before they were popular. He went all in on home automation. He's trying to get us all to build combat robots, which I don't know if I'm going to do unless we're going to get Billy and Silly to duke it out here. But back in 2018, he handed me an Eon, a giraffe, and a gray panda. And he said, I bought this, but I can't make it work on my car. He had like a 08 Acura, something or other. But do you think this would work on that Golf R you just bought? Because in the repository, there's this file called VWMQB. Do you know what that is? And I'm like, no, but I'm going to find out. 5 years later, I'm on the stage at Comic-Con, so as you can see, that one kind of spun out of control. So in my day job, in my corporate life, it's a habit to introduce myself with a couple of personal facts. Usually that personal fact is I drive my car with a cell phone. But that doesn't really move the needle in this room for obvious reasons. And we're kind of past cell phones. So my random fact is the 8607 is my Cisco CCIE number. The guy in my Discord profile pic is a famous actor that's played in an old Volkswagen ad campaign probably 20 years ago. And I've had 5 total strangers approach me in airports, restaurants, whatever, and tell me I look like Tom Hanks. I don't see it, I don't get it. I love Tom Hanks, I'm flattered, but it's just a thing that happened to me. So that's my random personal fact. So today we're going to talk about how to port cars. This will be very generic. I'm going to use some examples that are drawn from a Volkswagen world, but this is not a Volkswagen specific talk. We're going to start off and talk about, is a car a good candidate? This doesn't mean we can know in advance if your car will work. You're going to have to go kind of all the way through the process to verify that, but there's some red flags that we look for. We'll talk about what you need for a dev environment. We'll talk about connecting to the car for the first time, reading data, and translating that into something that openpilot can use. We'll talk about sending messages for the first time, finding the actuator commands that your car's factory lane assist camera and ACC radar use. And last, we'll talk about the process of upstreaming cars. So, 3 classes of cars here. It's a good sign if your car has lane keeping assist and adaptive cruise control. Those are really minimums for supporting openpilot on your car. Yeah, you can hack around it, but it's not a good openpilot experience if you don't have adaptive cruise, and lane keeping assist is a minimum. And the other thing is we want to make sure it uses standard CAN or CAN-FD networking. Bad signs, some higher end cars don't use CAN, they'll use something called FlexRay. And FlexRay is, in a way that's hard to explain, and actually I'm not qualified to explain, it is hard to split openpilot in the middle of. Comma did a hackathon type thing that actually made this work on an Audi Q8, but I I think they decided it was going to be a mess and hard to bring to market and didn't really proceed with it. It is difficult, and right now there's really no way on the market to work with it. If there's automotive Ethernet in the car, that's starting to become common in new vehicle designs. Right now, we don't have transceivers for that. It's something you can buy. It's not hard to get on Ethernet itself. The trouble with automotive Ethernet, as manufacturers refresh to that, is it has a strong tendency to come with secure onboard communication, which is a euphemism for there's cryptographic hashes on messages that stop you from messing with things. FlexRay is just challenging to intercept. If your car has SecOC, as unfortunately Toyota and actually certain VW are starting to have, you actually have an adversary. Someone's trying to stop you from having fun, and that's going to be a little bit difficult. So I think both of those will be surmounted eventually, but they're going to be very vehicle specific, and they're not something I'm personally working on, and that's going to be a task for someone else. If your car doesn't have any of this stuff, you might actually have an easier time. There's some folks that actually bolted an electric power steering rack and a bunch of microcontrollers and some other things into a late 70s Volkswagen Vanagon. Now, after that was done, that Vanagon kind of identifies as a Toyota Corolla, but it works. So in some ways, that car on the right is actually easier than this car in the middle. So let's say you have a car that's likely to work, in this case mine, or whatever car that you might have. And I want to be clear that what I'm talking about here today is actually not that hard to do. If you can spell Linux and SSH, you can go through these journeys that I've gone through. It used to be a lot harder than it was, but it's gotten pretty easy. So first thing, workstation, something running Ubuntu, VMware, or WSL is fine. I'm about half and half bare metal Ubuntu when I'm working from home. This laptop running Windows 11, I do the other half on under WSL2. Next thing you need is a comma 3. I missed the memo on it not being a dev kit anymore. Comma 3 or 3X. And when you order it, you'll order it with a developer harness, which I'll show you in just a moment. The return window for these guys is normally 30 days. I'm not sure what the process is, but if you're working on a new car port, they will give you a little bit of extra time. And then you'll need a few basic tools. You'll need a diagnostic tool for your car. It's a must. You're going to tick off your car during this process, and you'll need to be able to clear faults, and you'll need some visibility into what's going on. And you'll need some other basics, multimeter, wire cutters, crimper, etc. So when you order from the Comma store and you get a developer harness, that's what it'll look like. It looks like any other harness adapter that they sell you, but there's no ends on it yet. You get to put the ends on it because whatever ends that it needs, the connector shells and the terminals, are going to be unique to your car. You can figure that out by looking at the connector cars on your car. There'll usually be a part number on it somewhere. The one end will usually be easy to find. The other end is sometimes rough because that's not something the manufacturer ever has to supply in a harness form. It's always built into the camera. In a pinch during development, you can make do with generic card edge, pin headers, but one way or another, you need to take that and adapt it to your car. And this is how you do it. Every auto manufacturer in the US and really worldwide will have some way for you to get access to repair info. It's not going to be free. You generally have to pay for it. If you go to irwin.vw.com as an example, but you can do this for any auto manufacturer, you can get a wiring diagram for any given car. And you can't really read this and you don't have to, but that will tell you how your camera is wired up, what's on what pin. You take that together with Comma's open harness wiring diagram, and that'll tell you where you need to put constant power, ignition switch power, ground, can high, can low, an optional second can, and any pass-throughs that you need for like a camera heater or a fusion bus, so on and so forth. So let's assume we've made that harness and we've connected it to our car. This is what we need to figure out for openpilot to work. This is a subset of what goes into car state. We need to know how fast the wheels are turning, what the steering angle is, what gear you're in, all that good stuff. And in order to learn that, we look at Cabana. I promise the next slides will be easier to read. I wanted you to see the whole window this time. But what you're looking at right now is a pile of numbers. And this looks intimidating. But it'll clarify pretty soon. By the way, before I forget, this tool was made by another comma external contributor named Dean Lee. I think Adeeb asked him one day, hey, do you want to do something about Cabana, because web Cabana is getting really crusty, and then he just banged this tool out in like a couple of weeks and has been growing it from there, and it is a game changer for reverse engineering CAN networks. So Dean Lee, if you're seeing this, you're the man, we love you. So I'm not going to step through every single one of those signals. I'm going to take you through 3 examples of some of the more complex ones and a couple tricks of how to find them. So Cabana, that Dean Lee wrote, will show you and highlight bits that are changing. To find wheel speeds, you're looking for 4 signals that scale with how fast the car is moving. They stand still when the car is parked, and they move linearly when the car is driving. So somewhere in that pile of numbers is Cabana is going to highlight ones that change in about the same way times 4. So we now know 4 wheel speeds, but where do they go? Get in your car, you'll take a test drive in a parking lot. Set your parking brake, and then take off from a stop, drive a figure 8, stop, and look at your logs. Front and back will identify themselves because when your parking brake is set and you're driving a front wheel drive car, as most folks are, particularly with the parking brake set, the front wheels will start rolling first. So now you know front and back. When you drive that figure 8, the outside wheels will turn faster. So as we're making this sweeping tight right turn, the outside wheel is turning faster. And that tells us left and right. So now we have front, back, left, right. We know where all the wheels are. Next, you'll do a simple test log for gas and brake. Usually I press the gas 3 times, press the brake 3 times, take it in, look at it. The accelerator will have a curve that goes up and down. It's pretty obvious. It's not an on and off. You'll find a percentage somewhere. You may need to scale it. You'll find a similar signal for brake pressure that'll be some sort of curve, and it'll match when you're pressing the brake. And by the way, there's some features within Cabana that you can say for all those signal changes that it's highlighting, you can say kind of freeze those and clear those for this little 10-second time window and just show me the ones that changed within there, and that'll start making things like this pop out. And then it's nice to find a signal for brake pressed. You can do that in a pinch by just showing brake pressure above 1, but that doesn't work for all cars. Sometimes the signal's a little noisy. This ends up being the source of a lot of bugs. Common chased a lot of these out when Adeeb and Shane were doing improved testing for cars and chasing down controls mismatches and so forth. Brake pressed can come from a lot of sources. There'll be a switch on the brake pedal. Often there's redundant switches. So you may be seeing those. You may be seeing something from the ABS controller that says brake pressure over a certain threshold, and those are all good. But you might also be seeing something that says open the brake shift interlock, or if you're driving, this might actually be a brake light signal, which sounds cool until you remember that your ACC, when it's slowing down, also fires off the brake lights. So you want to go ahead and flag all the signals that are potentially brake pressed, but come back and look at it and make sure it's actually only flagging the ones that the driver presses in. Now for steering inputs. I've got a particular way that I like to do this. Get in the car, start it up, and you'll turn the wheel to 45, 90, 180, full lock and hold it, let go, and then turn it back to 0, 45, 90. And that gives you a steering angle. Unfortunately, my laser pointer doesn't show up really well against this screen. That'll give you your steering angle and the scaling, since when you turn to 45, you know the value you should get is 45, 90, 180. Sometimes you have to watch this on progressive ratio variable steering racks, but this one happens to be pretty easy. So that'll give you the steering angle, the direction if it's separate. Sometimes it's combined in an assigned value, sometimes it's separate. In this case, it's separate. It'll also give you the amount of driver input torque. This is important for torque blending as you're driving with openpilot, so that openpilot can back off the guidance that it's giving you if the driver's providing input, and also so it knows which way you're nudging for desired inputs like lane changes. So it'll show you here, as we're steering, that EPS link moment. It'll show you that we're providing some input, and then high input, when we're holding it at lock, it'll go to 0 when you release, and you'll see that the direction sign is different because as we're turning the wheel back, we're providing pressure, torque, going left, even though the total steering angle is still right. We haven't crossed 0 yet. So with that simple test procedure, that gets you all the scaling that you need, all the directions that you need. So we take that, plug it in with Cabana, and that outputs a DBC, which goes into an openpilot car state and tells openpilot everything that it needs to know about what your car is doing, how fast you're going, where the wheel is, et cetera, et cetera. There's a lot more signals you'll need to hunt down eventually, but those examples should kind of show you how to use Cabana. The next thing we do is figure out how to send messages. There's very few that we want to send. The ones that we do want to send are the factory lane keeping assist messages. And we're just talking about lateral for now because I have 20 minutes to get through this. This is usually, from the factory camera, it's usually a torque signal. They're usually sending a command saying, turn the wheel this hard in this direction. It's not a direct command to follow this lane, whatever. The camera is saying, turn the steering wheel this hard. Sometimes the camera does send an angle. I think Tesla does this. I think Nissan does this. I haven't looked lately. Recently, we had one come up that sent a path curvature. I know this drove Cameron nuts for a while when he was bringing Ford on board, but he got that figured out. He had to do some clever reverse engineering to turn that into something openpilot could use. So take note of what your factory camera does to actually control your car, what type of signal it sends, and what the maximums are. And then we teach openpilot to do that. In order for the car to actually pay attention to this message, we got to talk about payload, checksums, and counters. You may notice in most or all the messages that your car sends, there's a counter. There's some field somewhere that just rolls over and over and over, counts up one every frame. Sometimes it's 2 bits, sometimes it's 4 bits. All the VW ones happen to be 4. Some other makes are 2. You also see a payload checksum of some form in a lot of messages. This can come in the form of literally a checksum, add up all the byte values and take the remainder. Sometimes it's an XOR over the message payload. Sometimes it's an actual CRC. In the case of Volkswagen, it happens to be a strangely modified CRC that took forever to figure out. In some cars, it's completely random. I've seen the algorithm for Chrysler, and I have no idea what they're doing there, but somebody figured it out. The key thing that you want to look for and hope for is if you see on the left side of the checksum there, if the message payload remains the same and you get the same checksum for that every time, there's something there that you can replicate. And you just have to figure it out, and there's tools for that now. There's a tool called CRC Beagle that you can get off GitHub that you feed it whatever byte value you're getting and this payload, and it will figure out, it may not figure it out completely automatically, but it'll do a lot of the drudge work that I had to do manually 5 years ago. If on the other hand you see randomness, if the payload and other values aren't repeating cyclically, if it's fully random, you might be having a bad day because that might be a cryptographic hash you might have run into SecOC. If that's the case, you might be leveraging that return policy. Let's hope we don't see a ton of that, but that's what to look for. So let's assume we've got the steering message figured out. Cabana is going to write out that DBC for you. You're going to go into openpilot and have the car controller actually send out a torque command. And by the way, you actually don't have to take care of figuring out, at no point do you have to worry about where the car is in a lane, what direction to go, how to turn the wheel. openpilot takes care of all the path planning for you, and it already has a built-in controller for how much we want to turn the wheel. You just have to kind of figure out, you have to develop that Rosetta Stone of here's how to express a torque command to the car. And that is what we want to do. We want to send a torque command with that direction and match some other stock values that were used. And in this case, deeper levels of the OpenDBC library are handling the checksum and counter for us. And that takes us to what is hopefully good news. This picture was taken on an early, icky January morning in 2019. On the first day I made that thing work. Let me tell you, that was a good day. That was a fight to make that work. I think it took me something on the order of 3 months. And that was with several people helping me and providing hints. And there was still a ton of time in the driver's seat looking at TMUX, fixing typos. Oh my God, I can't believe I made another typo. Controls crashed again. Wait, why isn't the device starting anymore? It's back in the day, openpilot was a lot less testable, verifiable. That infrastructure that we have today didn't fully exist yet. But once you get it running, that first time that you feel openpilot engage and provide some guidance to the wheel, you're having a pretty good day. If your car makes it an entire minute down the road, and preferably more like 10 minutes, you're having a real good day. But sometimes you can get all the way into this process and find out you've got a lockout. And that's bad news. Sometimes there's workarounds for that, but every car that has a modern level 2 ADAS system will not let the driver go hands-off indefinitely. The difference is who enforces that. Some manufacturers drive that entirely from the camera. And if it's the camera that's deciding whether there's driver input and whether to disengage, openpilot can replace that. A few manufacturers, I think some varieties of Mazda, not recalling others offhand, but Old Ford, okay. Sometimes that 15 or 30 second lockout is enforced on the EPS. In that case, well, that's a bummer. Sometimes there's workarounds. There's things you can play with. Don't give up immediately. Reach out for help. But it's not a great sign if it consistently breaks after the same number of seconds. But hopefully you get down the road. And if you do, that's fantastic. You've got a lot of cleanup and quality work to do after that to make it good. Don't worry if it doesn't drive well at that point. You can fix that as long as openpilot can take control for 5 or 10 minutes. This is going to work. So that was my day in 2019. This was Wednesday. What you're seeing here is the next generation of MQB called MQB Evo. This is a 2022 GTI. We rented earlier this week. We modified a harness that's not unlike one of the ones we use on VW right now. We moved a couple of pins around. There actually is automotive Ethernet in this car, but we don't care about it. It's used as a replacement for the fusion bus between the camera and the radar, but we just pass it through, don't listen to it. The stuff we do care about is CAN FD, and they rototailed some of the messages, and we had to go through a process of reverse engineering again. But openpilot is a very different product today. The car ports have been massively cleaned up and standardized and templated. There's CI tests that mean you can take a log and play it back through controls and verify that everything works the way you think it should and doesn't crash before you get up from your desk. You're not doing this from the driver's seat anymore. You have tests that will check all this stuff out. And then New Cabana will help you out with this. And the whole thing ends up being a lot easier and faster. Last time this took 3 months. This time we had it done in 9 hours. To be clear, it's not upstream yet. This is probably the worst possible week to ask Adeeb and Shane to look at upstreaming a PR. But it's in progress. So, guidelines for upstreaming. It needs to be safe. It needs to comply with all of the guidelines that Adeeb and the rest of the openpilot team laid out earlier today. It needs to be passing tests. You need to verify all the checksums and counters, not only for sending, but also for receiving. And you need to make sure, if you're using stock ACC, that openpilot can reject engagements if there's something wrong. Then it needs to be supportable. It needs to work like other openpilot cars, and that means torque blending. That's one of the reasons Tesla isn't listed as officially supported, because the steering API doesn't work quite like we want. There needs to be no visible faults. It needs to drive in a way that would be acceptable for a person. And if there are faults, you need to log them and upload them so they can be analyzed later. This comes into play as part of all the work that the openpilot team has done to improve quality in MTBF and autopilot, to the point where the last couple of times that the openpilot team has had me look at routes that experienced faults, we tracked them back to a bug in the car. One of them was a retrofit that somebody had retrofitted ACC to the car. They didn't have it from the factory and they'd used the wrong software. The other one was genuinely a software bug in the ECU. A certain model year of Atlas had engine ECU firmware that if you did the wrong thing in the wrong order with remote start, you wouldn't have cruise control for the next start. So you want to get to the point where everything works. And then it needs to be actually marketable. In order for it to be upstream and actually appear on Comma's website and shop, you got to figure out how to make that harness manufacturable. It means you got to find the other connectors on the other end. It needs to be something somebody can reasonably install, and it needs to be fully plug and play, fully reversible. It needs to work like the openpilot experience in other cars, because it's one thing when you are working on your own car, but when this is upstream and in a store, it's not you that's taking the support calls or the RMAs or the angry emails, it's those guys. So it needs to be dialed in order for it to appear for actual sale to actual customers. So that's my talk. There's obviously a lot more that goes into it. I hope to actually do kind of like a blog series later. I don't know when that will fully come to pass, but hopefully that should be an overview. Anyone got questions?
Jason, we're going to do questions. We're running a little over.
Oh, are we? Okay.
I'm going to give you a little spot in the back, and everyone can come up and ask you questions back there.
Okay.
Get their specific questions answered. The comma team upstairs, if you guys want to come on down, we're going to say goodbye to the live stream. Thank you guys so much for tuning in. The streams will be live. Well, we'll put the recordings on YouTube in the next few weeks, so you can rewatch. Thank you again for tuning in. Have a great night.